Hello everyone, in this video we're going to explore topic 10.1 defining convergent and divergent infinite series. Alright, let's take a look at the list of the following numbers 1, 4, 7, 10, 13, 16, etc. Alright, the first number right here is called the first term. We're going to denote this one as a sub 1. The second one right here is called the second terms. We're going to name this one as a sub 2, right, etc. This one a sub 3, right? So basically, we just write this sequence as a sub 1, a sub 2, a sub 3, all the way to a sub n, etc. Right? Another way to write this one is you're going to put a sub n inside the curly bracket, right? When n goes from 1 to infinity. Or you can write like this, alright? The number right here, 1, 2, 3, 4, or n like this, is going to be index. And it indicates the order of the terms in the sequence. Alright, so normally the sequence always starts with an index n equals 1. Sometimes it's going to be with n equals 0. Alright? Now we're going to define a sequence. Now we take a look back at this sequence right here. Observe that the next term always equals the previous terms plus 3, right? In order to get 4 from 1, we're going to add 3, right? We add 3 every single times to get the next term, right? So the first term I'm going to name this one as a sub 1 as 1, right? And then a sub 2 is going to be a sub 1 plus 3, right? A sub 3 equals a sub 2 plus 3, right? Etc. all the way to a sub n plus 1 equals a sub n plus 3, right? N plus 1 is the next term of n, right? Now we're going to put these all together. Formally, we should say the first term a sub 1 equals 1. A sub n plus 1 equals a sub n plus 3. Now when it comes to explicit definition, each terms in the sequence can be represented by the order pairs, right? So if we look at this one right here, the first term right here, I call this a sub 1, right? A sub 1, you have 1, right? A sub 1 equals 1, a sub 2 equals 4, a sub 3 equals 7, right? Etc. So I'm going to use this guy right here, 1 and 1 right here. I get the first order pair, right? This guy right here, I get the second order pair, and the third one right here. So it could be 3, 7, etc. Right? Now I'm going to find the slope using the two order pairs, right? So it could be right sub 1, remember? So it could be in order to get 4 from 1, I'm going to add 3, right? In order to get 2 from 1, I'm going to add 1, right? So 3 divided by 1 is going to be 3. That's why I get the slope is going to be 3 right here, right? Using the point slope from formula, I'm going to use the first order pair is going to be 1, 1, right here. And the slope is 3 right here. So I substitute over here, so y minus 1 equals, the slope is going to be 3 times s minus 1, right? Now I'm going to replace y with a sub n, right? Minus 1 equals 3. Now I'm going to replace s with the subscript n right here. So I have n minus 1. And this is called explicit formula, right? Now if I simplify this one, it turns out to be this guy right here, right? Now example number 1, explicit formulas. Use the explicit formula given for each sequence a sub n to write out the first 4 terms of each sequence. Alright, first 4 terms right here. Now if n equals 1, so you have a sub 1 equals 1 over 2 part 1 is to be 1/2, right? N equals 2, you have a sub 2 is to be 1 over 2 squared is going to be 1 over 4, right? N equals 3. You have a sub 3 is going to be 1 over 2 cubed is going to be 1 over 8. And n equals 4 is going to be a sub 4, and 1 over 2 power 4 is going to be 1 over 16, right? Now question B, n equals 1. You have a sub 1 equals negative 1 altogether raised to the first times 1 over 1 squared plus 1, right? So it's going to be negative 1/2. N equals 2. A sub 2 equals negative 1 squared times 2 over 2 squared plus 1. And it's going to be 2 over 5. N equals 3. You have a sub 3 equals negative 1 raised to the third times 3 over 3 squared plus 1. It's going to be negative 3 over 10. And the last one, n equals 4. You have a sub 4. It's going to be negative 1 raised to the 4 times 4 over 4 squared plus 1 equals 4 over 17, right? So if you graph these two sequences, it's going to be something like this, right? Now example number 2, working with sequence. For each of the following sequences, find the next two terms of the sequence. A recursive definition that generates the sequence. An explicit formula for the n terms of the sequence. Now let's take a moment to review what we learned from AP Pre-Calculus. Now for the recursive formula of the arithmetic sequence, the n terms equals the previous terms, which means n minus 1 plus the common difference, right? For the geometry sequence, the n terms equals the previous terms times the common ratio, right? Explicit formula for the arithmetic sequence, the n terms equals the first term plus n minus 1 times common difference. For the geometry sequence, the n terms equals the first terms times common ratio raised to the n minus 1. Alright, so keep that in mind. Now, go back to question A. First, we need to find the next two terms, right? So we have the sequence A. It's going to be negative 2, 5, 12, 19, n. And we look at this one right here. In order to get 12 from 5, we need to add 7. Right? This one we need to add 7. Right? And of course, to get 5 from negative 2, we add 7. Right? So basically, we're going to add 7 each time. Right? So this guy should be 26 and 33, etc. Right? Now the question wants us to find the next two terms. That's it, right? Next one, a recursive definition, right? So we're going to use the formula right here, right? So we have a sub n plus 1 equals a sub n plus 7, right? Now, next one, number 3 right here, explicit formula. So we have a sub n equals a sub 1 equals negative 2 plus n minus 1 times common difference, which means times 7, right? So I put 7 in the front right here, right? Now if you want to simplify this one, it's going to be 7n minus 9. So this one is the explicit formula, right? This one is recursive formula. Now we're going to move on to the second sequence right here. To get 6 from 3, we're going to multiply by 2, right? This guy multiplied by 2, right? So we have a sub n equals 3, 6, 12, 24, 48. If you multiply by 2, it's going to be 96, right? And it's going to be 192, etc. Right? Now, for the recursive formula, we're going to use the formula right here, right? So we have b sub n plus 1 equals b sub n times common ratio is 2, right? So I put 2 in the front, right? Now for the explicit formula, it's going to be b sub n equals b1 times common ratio raised to the n minus 1. Substitute value b sub n equals b1 is going to be 3 right here, right? Times common ratio is going to be 2 right here. Raised to the n minus 1, right? And if you want to simplify this one, it's going to be 3 times 2 to the n over 2, right? And it's going to be 3.5 times 2 to the n, right? Now let's move on to the next one, limit of a sequence. Definition of the limit of a sequence. Let L be a real number. The limit of a sequence a sub n is L, written as limit of a sub n as n approaches infinity equals L. If the terms of the sequence approach a unit number, L as n increases without bound. If the limit L of a sequence exists, then the sequence converges to L. If the limit of the sequence does not exist, then the sequence diverges. Now let's move on to the next theorem. Limit of a sequence. Let L be the real number. Let f be a function of a real variable such that limit of Ls when s approaches infinity equals L. If a sub n is a sequence such that f of n equals a sub n for every positive integer n, then the limit of a sub n when n approaches infinity equals L. Now let's take a look at example number 3. Limit of a sequence. For each of the following sequences, write out the first 4 terms. If you believe the sequence converges, make a conjecture about its limit. If the sequence appears to diverge, explain why. Assume each sequence has beginning index of n equals 1 and is defined infinitely. Alright. Now, the first term a sub 1 equals, substitute 1 for n. So you have negative 1 to the first over 1 squared plus 1 equals negative 1/2, right? Now a sub 2 is going to be negative 1 squared over 2 squared plus 1, and it's going to be 1 over 5, right? Now a sub 3 is going to be negative 1 cubed over 3 squared plus 1. It's going to be negative 1 over 10, right? And a sub 4 is going to be negative 1 power 4 over 4 squared plus 1. It's going to be 1 over 17, right? Now observe that if n is odd, I have the negative side on the top. You see that? This is 3, you have negative side on the top. If n is even, I have positive side on the top, right? So you see that on the top, the number is still 1, but it's changing from negative 1 to 1. That's it, it's alternates, right? Now look at the bottom. a sub 1, you have 2 on the bottom, right? A sub 2, you have 5. A sub 3, you have 10. A sub 4, you have 17, right? So you see that the bottom getting larger and larger, right? So you have the limit of -1 to the n over n squared plus 1 when n approaches infinity. The top always alternates between positive and -1. The bottom getting larger as n increases without bounds, right? So it could be infinity right here. The answer must be 0, right? Now let's move on to question B. Now we have big 1 is going to be cosine of pi is going to be -1. B2 equals cosine of 2 pi is going to be 1. B3 cosine of 3 pi is going to be -1. And B4 cosine of 4 pi is going to be 1, right? And we see that the value on the right hand side alternates between 1 and -1, right? So it tells us that the sequence divergent. Now question A, we get 0 over here, so the sequence convergence, right? Now question C, we have sec1 equals 4 times 1 cubed over 1 cubed plus 1, so it's going to be 2. C2 is going to be 4 times 2 cubed over 2 cubed plus 1. So it's going to be, now we're going to print up the calculator and calculator. So we have 2 cubed, it could be 8 times 4, it could be 32, right? So we have 32 divided by 9, right? Press Ctrl, Enter. It's going to be 3.555, right? Now C3 is going to be 4 times 3 cubed over 3 cubed plus 1, right? So if you print up the calculator, you have 4 times 3 cubed over 3 cubed plus 1. And then press Ctrl, Enter. It's going to be 3.857, right? Now C4 is going to be 4 times 4 cubed over 4 cubed plus 1. So it's going to be approximately 3.938, right? And observe that the answer getting closer to 4. So it's going to be convergent, right? But anyway, we're going to check our work by taking the limit, right? So we're going to take limit of 4n cubed over n cubed plus 1, right? When n approaches infinity, we're going to use the relative growth rate, right? So when n approaches infinity, this guy right here grows faster than 1, right? So we can ignore 1. It turns out to be limit when n approaches infinity of 4n cubed over n cubed. This guy cancel out, so it could be 4. That is the answer. So we see that this guy getting closer to number 4, right? So this one is convergent. Now question D. N equals 1, we have D2 equals -2 times D1, right? N equals 2, you have D3 equals -2 times D2. But D2 equals -2 times D1, so it could be -2 times -2 D1, right? So it's going to be -2 altogether square D1, right? Now D4 equals -2 D3, right? But D3 equals this one right here, so it could be -2 times -2 square D1. So it could be -2 cube D1, right? Now first we can observe that If the index right here is odd, right? And this guy right here is the positive number, right? Power of 2, right? If the index right here is even, and then the value of this guy right here is the negative number, right? So it's going to be alternating between positive and negative powers of 2, right? So the sequence is divergent, right? Moreover, the limit of d sub n when n approaches infinity does not exist. Now let's move on to example number 4. A bouncing basketball. A basketball is tossed straight up in the air and reaches a high point before falling to the floor. Each time the ball pounds on the floor, it rebounds to 0.6 of its previous high. Let Hn be the high point after the n pounds, with the initial high being 20 feet. So we just get the diagram and we see that this is the first one, right? And then the second one is going to be 0.6 of its previous high, right? So 0.6, which means it's like more than half, right? So it could be something like this. And the third one is going to be something like this. And then next one is going to be something like this, right? Etc. Alright, find a recursive definition and an explicit formula for the sequence h sub n. Alright, so we know that the first term, which means the initial value, right, is going to be 20, right? So this one is h1, right? Now each time the ball bounces on the floor, it rebounds to 0.6 of its previous high. So this one is the common ratio, right? So we know that a sub n equals a sub n minus 1 times the common ratio. This one is the recursive formula of the geometric sequence, right? So we have h sub n equals h sub n minus 1 times 0.6, right? Or you can write 0.6 times h sub n minus 1. That's it, right? Now, explicit formula, remember you have a sub n equals a1 times the common ratio raised to the n minus 1, right? So we have h sub n equals 0.6 raised to the n minus 1 times the first term. The first term is 20. So you have 20 right here. And don't forget to put this one inside parentheses, right? Now question B. What is the high point after 10 bounce? Right? So we're going to use the recursive formula right here, right? So we have h10 equals 20 times 0.6 raised to the 10 minus 1 is to be 9, right? So you're going to print up the calculator. So you have 20 times 0.6 raised to the 9. Press Ctrl Enter. It's going to be 0.20554, right? Now question C. What conjecture can you make about the limit of the sequence h sub n, right? So we're going to use the recursive formula. Limit of this guy right here, 20 times 0.6 raised to the n minus 1 when n approaches infinity, 0, right? Because this decimal right here getting closer to 0 when n approaches infinity, right? Now let's move on to the next one, definition of infinite series. Given a sequence of numbers of this one, the sum of these guys should be sigma of a sub k when k goes from 1 to infinity. is called an infinite series. Its sequence of partial sum s sub n has the terms: if n equals 1, you get this guy. If n equals 2, you get two terms right here. N equals 3, we get this one, etc. until you reach s sub n, right? So this one can be written as this guy right here first. If the sequence of partial sums s sub n has a limit L, the infinite series converges to that limit. And we can write this guy. If the sequence of partial sums diverges, the infinite series also diverges. Now let's move on to example number 5. Sequence of partial sums. Consider the infinite series sigma of 1 over k times k plus 1 when k's go from 1 to infinity. Question A. Find the first 4 terms of the sequence of partial sums. Alright, so we have a sub 1. Substitute 1 for k. So we have sigma k goes from 1 to 1. 1 over k times k plus 1. Right? So it's going to be 1 over 1 times 1 plus 1. Right? Substitute 1 for k. So it could be 1 half. Now add sub 2 is going to be sigma k goes from 1 to 2. Right? Of 1 over k times k plus 1. Right? Now k equals 1. We get this guy right here, 1 half. K equals 2, we have 1 over 2 times 2 plus 1, right? Now if you simplify this one, it's going to be 2 thirds, right? Now add sub 3 is going to be sigma k goes from 1 to 3 of 1 over k times k plus 1, right? Now if k equals 1, we get 1 half right here, right? K equals 2, we get 1 over 6, right here. And k equals 3, we get 1 over 3 times 3 plus 1, right? So it's going to be 2 thirds plus 1/12, right? 2 thirds, what we got right here. So it could be 9 over 12. If you simplify, it could be 3 over 4. Now s sub 4 is going to be sigma k goes from 1 to 4 of 1 over k times k plus 1 equals k equals 1, we get 1 half right here, right? K equals 2, we get 1 over 6, right? Because 2 times 2 plus 1, it could be 6, right? K equals 3, we get 3 times 3 plus 1 is going to be 1 over 12, right? K equals 4, 4 times 4 plus 1 could be 20, right? Plus 1 over 20, right? Now if you simplify this one, it's going to be 4 over 5, right? Find an expression for s sub n, right? So we just rewrite s1 equals 1 over 2, s2 equals 2 thirds, s3 equals 3 4, s4 equals 4 5. Now we look at the problems and look at the top and bottom. The bottom always 1 unit greater than the top, right? So then you can conclude that n sub n equals n over n plus 1, right? Now if you take the limit of this one, when n approaches infinity, it's going to be the limit of n over n plus 1 when n approaches infinity, right? So it's going to be limit of n over n when n approaches infinity, right? Because this guy right here grows faster than this, right? So n divided by n is going to be 1, so the answer must be 1, right? Another way to do example number 5, faster without finding the partial sums. That is partial fraction decomposition you learn in unit 6. So this one right here can be written as the sum of 1 over k minus 1 over k plus 1, right? When k goes from 1 to infinity, right? Now, if k equals 1, you get 1 over 1 minus 1 over 2, right? If k equals 2, you're going to add 1 over 2 minus 1 over 3, right? If k equals 3, substitute over here, you have 1 over 3 minus 1 over 4, right? Etc. When k equals n, you have 1 over n minus 1 over n plus 1. Now observe that this guy and this guy cancel out. The next two terms cancel out. Next two terms cancel out. This guy and the previous term cancel out, right? So we're gonna have the first term and the last term left, right? So it's gonna be 1 minus 1 over n plus 1, right? Now we're gonna take the limit of this one. It's gonna be 1, right? Because this guy approaches 0, right? Now let's move on to the last example, example number 6. A sequence versus a series. Consider the following sequence divided by a sub n equals n over 2n plus 1. And its corresponding series divided by this guy right here. Graph each on your calculator, find each of the following limits. Alright, so we're going to print up the calculator. Click graph right here. Click menu, graph entry, edit. Number 7 sequence, number 1 sequence. Now you're going to input this sequence n over 2n plus 1. So you're going to press fraction right here. N over 2n plus 1, right? And you press enter. It's going to be right here, right? Now to graph the series right here, I'm going to press home screen right here. Then I'm going to pick new. I'm going to add number 4 right here. Go to the top of the A column. I'm going to type N. Now right here I just populate the rows from 1 to 20, right? Now we're going to go to the column B. You need to type S, E, Q, N, A. It's called sequence A. So you press enter. Now the next row right here of column B, you're going to enter the expression right here, right? So I'm going to press the button right here to put the fraction. And it's going to be n over 2n plus 1, right? And I'm going to press enter. Now you need to click on the arrow right here and choose all variable reference. Press OK. Now go to the column C, part sum. And then press enter. Now in the cell C1 right here, you need to copy the value of B1 right here. You put it over here, right? So it turns out to be 1/3, right? So I put 1 divided by 3, right? And then press enter. Now in cell C2, you're gonna type the formula equals C1 plus B2. Then you press enter. Now you're gonna drag this one downward to copy the formula for as many cells as you like. So I'm gonna copy this one until 20 cells, right? Now you want to grab this one on the X and Y coordinate plane. You're gonna press Ctrl dot and then number 2 graph. Select menu number 3 and number 6. Now for the x value, it's going to be the n value, right? For the y value, it's going to be the C column, which means possum. So you just type possum and then press enter. It's going to be right here. Alright. Now, in order to find the limit of this one, it's the same thing as limit of n over 2n plus 1 when n approaches infinity. It's going to be limit of n over 2n when n approaches infinity. N and n cancel out, so it could be 1/2, right? Now, limit of this one is going to be infinity, right? Look at the graph right here. When n approaches infinity, this guy approaches infinity, right? We're going to learn how to prove these two formulas. Alright. The sum of finite geometric series and convergence of the geometric series. Alright, now in order to prove this formula, first we need to populate this guy, right? So we have x sub n equals a1 plus a1 r plus a1 r squared plus a1 r cube plus etc plus the last term a1 r to the n minus 1, right? Now I'm going to multiply both sides by r, so it's going to be r s n equals a1 r plus a1 r squared plus a1 r cube plus etc plus a1 r to the n minus 1 plus a1 r to the n, right? Now we're going to subtract this one vertically. So we have s sub n subtract r times s sub n equals this guy cancel out, right? So we're going to end up with a sub 1 subtract a sub 1 r to the n, right? Now I'm going to factor Sn out, so I have 1 minus r times S sub n equals, I factor a sub 1 out, so I have 1 minus r to the n, right? Divide both sides by 1 minus r, so S sub n equals a1 times 1 minus r to the n over 1 minus r, right? And this one has been proved, right? Now look at the right hand side. We're going to do exactly the same thing, right? So we're going to populate this guy first. Now the right hand side, we have two different ways to write the infinite geometric series. If k goes from 1 to infinity, and this one must be k minus 1. If k goes from 0 to infinity, this guy only have k, right? So I have s equals a1 plus a1r plus a1r squared plus a1r cube plus etc, right? Now I'm going to multiply both sides by r, so I'm going to end up with r s equals a sub 1 r plus a sub 1 r squared plus a sub 1 r cube plus a sub 1 r to the 4, right? S subtract r, S equals this guy cancel out, right? So you're going to end up with a sub 1. That's it. Now you're going to factor S out, so you have 1 minus r times S equals a sub 1, right? So then you're going to divide both sides by 1 minus r, so it can be S equals a 1 over 1 minus r, right? So this one has been proved, right? Let's explore why absolute value of r less than 1, then the series converges to the sum of this one, right? So go back to this one right here. You know that absolute value of r less than 1 is the same thing as negative 1 less than or less than 1, right? So when n approaches infinity, you have r to the n approaches 0, right? So then this guy's gone, right? So you're gonna end up with s infinity equals a sub 1 over 1 minus r, right? Which is the one on the right hand side right here, right? When absolute value of r greater than or equal to 1, this series diverges, meaning it does not approach a finite limit. We're going to learn how to work with finite and infinite geometric series. Alright, so we have two theorems right here. The first one is going to be the sum of finite geometric series. It's going to be given by this formula. And the second one is going to be conversion of the geometric series. It's going to be given this formula. Alright, if absolute value of r less than 1, then the series converges to the sum of this guy. If absolute value of r greater than or equal to 1, then the series diverges. Alright. Now, in order to understand how we got these two formulas, please check out the video in the description below, or the video 10.2a. Question A. Sigma of 1 over 2 to the n when n goes from 1 to 10. Alright, so if n equals 1, we have 1 half, right? N equals 2, we have 1 half power of 2, right? N equals 3, we have 1 half power of 3, plus etc. until n equals 10, 1 half power of 10, right? Now, in order to get the second terms from the first term, we're going to multiply by 1 half, right? So this one is the geometric series with the common ratio equals 1 half, right? Now question B. If n equals 1, we have 1 divided by 1 is going to be 1. N equals 2, we have 1 half, right? N equals 3, we have 1/3, right? N equals 4, we have 1/4, plus etc. until n equals 20, it's going to be 1 over 20, right? And this guy not the geometric series, right? Now question C. N equals 0, we have 2 times 0 plus 1 is going to be 1. N equals 1, we have 2 times 1 plus 1 is going to be 3. N equals 2, we have 5. N equals 3, we have 7, right? And this one not a geometric series because we don't have the common ratio, right? Now, let's take a look at the example number 2. We need to find sum of finite geometric series. Alright, so we're going to go back over here. The formula right here is going to be the first term times 1 minus common ratio raised to the n over 1 minus r. We're going to populate this one, so it's going to be 4 times 0.3. When k equals 1, it's going to be power of 0, right? K equals 2, it's going to be 4 times 0.3 power of 1 plus 4 times 0.3 power of 2 plus etc. plus 4 times 0.3 power of 11, right? So it tells us that the first term is going to be A1 equals 4, right? The common ratio is going to be 0.3, right? And n equals 12, right? Now the sum of this one is going to be A1 times 1 minus r to the n over 1 minus r, right? So it's going to be 4 times 1 minus 0.3 raised to the 12, right? Over 1 minus 0.3, right? So we're going to print up the calculator. Press calculate. So we have 4 times, hit the fraction right here, 1 minus 0.3 raised to the 12 over 1 minus 0.3, and then press Ctrl Enter. It's going to give you the values of 5.714, right? Now question B looks similar to question A. But in order to apply this formula right here, you need to rewrite this one in the form of this guy right here, k minus 1, right? So this guy turns out to be sigma k goes from 1 to 12, 4 times 0.3. Now 0.3 raised to the k, I can write 0.3 raised to the k minus 1 times 0.3, right? So I can print 0.3 to the front right here, right? So now I have A1 equals 4 times 0.3, right? The common ratio R equals still 0.3, right? And n equals 12, right? So this sum equals A1 is going to be 4 times 0.3 times 1 minus common ratio 0.3 power of 12, right? Divided by 1 minus 0.3, right? So you just take the answer from the left hand side, you multiply by 0.3, right? So I'm going to print up the calculator, I'm going to multiply this number by 0.3, right? And then I'm going to press Ctrl Enter. It's going to be 1.714, right? Example number 3. Convergent and divergent geometric series. Evaluate each of the following geometric series or state the series diverges. Alright, so we're gonna go back over here, the formula right here. If absolute value of r less than 1, then the series converges, and the sum of the series should be this one, right? If absolute value of r greater than or equal to 1, then the series diverges, right? So we're gonna populate this one. If n equals 0, we have 1, right? N equals 1, we have 1.1. N equals 2, we have 1.1 square, right? Plus etc., right? So you see that the common ratio is 1.1, which is greater than or equal to 1, right? Then the series diverges, right? Now question B. We're gonna populate this one. So we have S equals n equals 0, we have 1, right? N equals 1, we have 1 over e. N equals 2, we have 1 over e squared. N equals 3, we have 1 over e cubed, right? So then the common ratio is 1 over e, right? And you know that e is going to be 2.718, right? So this guy less than 1, greater than 0, right? Then the series convergent, right? Then the sum should be s equals a over 1 minus r, right? Now a, which means the first term, right? So it could be 1 right here, over 1 minus 1 over e, right? So it could be e over e minus 1. Now let's take a look at the question C. We need to populate this one, right? So n equals 1, we have 3 times negative 0.75 to the first plus n equals 2, you have 3 times negative 0.75 square, right? Plus 3 times negative 0.75 cube, plus etc., right? And observe that the common ratio is negative 0.75, right? Which is greater than negative 1, less than 1, right? So I convert this one to improper fraction. It's going to be negative 3, 4, right? So then the sum is going to be, the first term is going to be right here, right? So I have 3 times negative 3 over 4 over 1 minus common ratio. Common ratio is negative 3 over 4. So it could be plus 3 over 4, right? So we're going to simplify this one. It's going to be negative 9 over 4, right? Divide by, simplify this one. It's going to be 7 over 4, right? Now let's multiply the top and bottom by 4. So the final answer must be negative 9 over 7, right? Now question D. Let's populate this one. So if n equals 0, we have 3, right? N equals 1, we have 3.5, right? N equals 2, you have 3 over 2 square. N equals 3, you have 3 over 2 cube, etc., right? Now you're going to factor 3 out, so it could be 3 times 1 plus 1 over 2 power of 1 plus 1 over 2 square plus 1 over 2 cube. And observe that the common ratio is 1/2, which is greater than 0, less than 1, right? And the first term is 3, right? So you have the sum is going to be a1, which means 3 over 1 minus 1/2, right? So it's going to be 6, right? Now question E. N equals 0, we have 3 over 2 power of 0 plus 3 over 2 power of 1 plus 3 over 2 square plus etc., right? So the common ratio is 3.5, which is greater than 1, right? Then the series diverges, right? Now question F, let's populate this one. N equals 0, you have e over pi power of 0 plus e over pi power of 1 plus e over pi square plus etc., right? So the common ratio is e over pi. You know that e is going to be about 2.718. Pi is going to be 3.14 something, right? So this guy less than 1 but greater than 0, right? Then the series convergent, right? So the sum is going to be the first term is right here. It's going to be 1, right? Over 1 minus e over pi, right? So if you simplify this one, it turns out to be pi over pi minus e, right? Now let's move on to question G. First, we need to split this sum into two sums, right? So it's gonna be sigma when n goes from 0 to infinity of 2 over 5 altogether to the n minus 1. Subtract. Now, this one right here, you have the power of n minus 1. This one is n plus 1, so which is 2 units greater than this one, right? I need to rewrite this one and this one in the same power, n minus 1, right? So, the top right here, I can rewrite this one as 3 squared times 3 to the n minus 1, right? So 3 squared is going to be 9, right? And then this guy and this guy can be combined as 3 over 5 to the n minus 1, right? Now I'm going to separate these two guys. So now I need to calculate each of this one, right? So I'm going to start with this guy first. Now I'm going to separate this guy as 2 over 5 to the n times 2 over 5 to the negative 1, right? So I put 2 over 5 to the negative 1 to the front, and I'm going to end up with this guy right here. Now look at this series right here. The common ratio is 2 over 5, which is greater than 0, less than 1. So then the series convergent, right? Now I have 2 over 5 raised to the negative 1. It's going to be 5 over 2 times. When n equals 0, you have the first term actually 1, right? 1 minus common ratio, which means 2 over 5, right? If you simplify this one, the answer should be 25 over 6, right? Now the second one, you do exactly the same thing, right? So basically, you have 9 times 3 over 5 to the negative 1 sigma when n goes from 0 to infinity of 3 over 5 to the n, right? So the sum is going to be 9 times 3 over 5 to the negative 1 is going to be 5 over 3, right? Times 1, right? The first term is 1, and 1 minus common ratio is going to be 3 over 5, because 3 over 5 less than 1 greater than 0. So then this series is convergent, right? Now if you simplify this one, it's actually 75 over 2, right? Now I'm going to combine these two guys, 25 over 6 and 75 over 2, right? So you have 25 over 6 subtract 75 over 2. The answer must be negative 100 over 3, right? Now let's take a look at this question. We need to populate this one, right? So it's going to be 4 plus 4 times 0.6 plus 4 times 0.6 square plus 4 times 0.6 cube plus etc. Right? Now the common ratio is 0.6, right? And the first term is 4, so it's going to be the sum equals 4 divided by 1 minus 0.6, right? So it's going to be 4 divided by 0.4, right? So it's going to be 10, right? Now the last one right here. The first term is 3, the common ratio is 0.1, right? So then you have the sum is going to be 3 divided by 1 minus 0.1, right? So 3 divided by 0.9, right? Multiply the top bottom by 10, so you have 30 divided by 9, right? And then divide the top and bottom by 3, so you have 10 over 3. This one is the final answer, right? Now let's take a look at the example number 4. Decimal expansion as a geometric series. Write 1.0.25 as a geometric series and express its values as a fraction. Alright, so you see that there is a part right here. It means 25 repeating, right? So 1.025 equals 1.025, 25, 25, 25, keep repeating, right? Etc. And then it's gonna be 1 plus, now I'm gonna cut this one off 3 decimal number, right? So I'm gonna end up with 0.025, right? Next it's gonna be plus 0.00025, right? Next plus 0.0000025, right? Plus etc. right? So it's gonna be 1 plus 25 over 10 cubed plus 25 over 10 power 5 plus 25 over 10 power 7, right? Plus etc. Now I'm going to divide the top and bottom by 10. So I'm going to end up with 1 plus 2.5 times 1 over 10 square plus 2.5 times 1 over 10 to the 4 plus 2.5 times 1 over 10 to the 6 plus etc. right? And then this one equals 1. Now look at this guy right here. Actually, it's going to be geometric series, right? So it's going to be plus sum when n goes from 1 to infinity of 2.5 times 1 over 100 to the n, right? Now we're gonna populate this one. So then you have 2.5 times n equals 1. You have 0.01, right? Plus 2.5 times 0.0001, right? Plus etc. right? So you see that the common ratio is 0.01, right? And the first terms a1 equals 0.025, right? If you multiply this one, it's actually 0.025, right? So then the sum equals, don't forget this one, 1 plus the first term 0.025 over the common ratio. It's going to be 0.01, right? So 1 subtract 0.01 because this one less than 1 greater than 0, right? So we have the sum. Now if we simplify this one, it's going to be 1 plus, I'm going to multiply the top and bottom by 1000, right? So I have 25 over 1000 minus 10, right? So then it's going to be 1 plus 25 over 990, right? So it's going to be 1015 over 990, right? Now divide the top and bottom by 5. You're going to end up with 203 over 198. Now let's move on to the next one, telescoping series. Telescoping series can have the form b1 minus b2 plus b2 minus b3, etc. So you see that all terms inside cancel out, right? You're gonna have the first and the last term only, right? Now a telescoping series converges if and only if b sub n approaches a finite number as n approaches infinity, right? So you're gonna take the limit of the final terms right here, right? Now, let's look at example number 5, telescoping series. Find the sum of the following series. Alright, so first we need to populate this one, right? If n equals 1, we have 1 over 2 minus 1 over 2 squared, right? Plus n equals 2, you have 1 over 2 squared minus 1 over 2 cube, right? Plus 1 over 2 cube minus 1 over 2 to the 4, right? Plus etc. Plus 1 over 2 to the n minus 1 over 2 to the n plus 1, right? And this guy cancel out, this guy cancel out, this guy cancel out, this guy and the terms before it cancel out, right? So you're gonna end up with the first term 1/2, and the last term right here you're gonna take limit of this one, right? When n approaches infinity, right? When n approaches infinity, this guy approaches 0, right? So the answer must be 1/2. Now let's take a look at question B. In order to do question B, we need to do partial fraction decomposition. We learned in unit 6, right? So I have 1 over n times n plus 1 equals a over n plus b over n plus 1, right? So then this guy becomes a times n plus 1 plus b times n over n times n plus 1, right? Now I'm going to equate this guy and this guy right here, right? Because denominator are the same, right? So I have a times n plus 1 plus b times n equals 1. I'm gonna let n equals -1, right? And then this guy gone, right? So you have b times -1 is gonna be negative, b equals 1, then b equals -1, right? I'm gonna let n equals 0, so this guy gone, right? So I have a equals 1, right? So then this guy becomes 1 over n minus 1 over n plus 1, right? So I put the sigma in the front when n goes from 1 to infinity of the whole thing right here, right? Now I'm going to populate this one. So if n equals 1, we have 1 over 1 minus 1 over 2. N equals 2, we have 1 over 2 minus 1 over 3, right? Plus etc. Plus until the last one, 1 over n minus 1 over n plus 1, right? This guy cancel out. This guy and this guy cancel out. This guy and the previous term cancel out. So we're going to end up with 1 minus 1 over n plus 1, right? So then the sum of this one equals 1 minus limit of this one when n approaches infinity, right? So then it's going to be 1 minus 0 is going to be 1. Now, example number 6 is slightly different from what we did before. Many telescoping series contain several terms B1, B2, B3 that do not cancel and become part of the sum. Now, we need to do partial fraction decomposition first, right? So, I'm going to have 2 over, I'm going to factor the bottom out first, so it could be n plus 3 times n plus 1, right? Equals a over n plus 3 plus b over n plus 1, right? And then this guy becomes a times n plus 1 plus b times n plus 3 over n plus 3 times n plus 1, right? Now I just equate this guy and this guy, right? So I'm going to end up with a times n plus 1 plus b times n plus 3 equals 2. I'm going to let n equals negative 1, right? And then substitute negative 1 for n over here. I have 2b equals 2, and then b equals 1. I'm going to let n equals negative 3, right? So this guy equals 0, right? So I have negative 2a equals 2, and then a equals negative 1, right? So this sum right here becomes the sum when n goes from 1 to infinity of negative 1 over n plus 3. So I put this one in the back, right? And 1 over n plus 1, I put this one in the front, right? Since this series is slightly different from what we did in the example number 5, I'm going to populate this one in different way to help you understand better. Alright, so I'm going to deal with the positive term first. N equals 1, you have 1 half. N equals 2, you have 1 third. N equals 3, you have 1 4. N equals 4, you have 1 fifth, right? Until the last term, it's going to be 1 over n plus 1, right? Now the negative terms, n equals 1, you have negative 1 4, right? So I put negative 1 4 here. N equals 2, I have negative 1 fifth, right? Etc. until the last term, 1 over n plus 3. So it could be right here. Right? Now, the one before 1 over n plus 3 is 1 over n plus 2. Right? And the one before this term is going to be 1 over n plus 1. Right? Now, we're going to add this guy up. Right? So does that mean this guy cancel out? You're going to end up with the first two terms and the last two terms right here, right? So the sum equals 1 half plus 1 third minus limit of 1 over n plus 2 plus 1 over n plus 3 when n approaches infinity, right? So when n approaches infinity, this guy approaches 0, this guy approaches 0, right? You're going to end up with 1 over 2 plus 1 over 3, and it's going to be 5 over 6. This one is the final answer. We're going to explore topic 10.3, the n term test for divergence. Alright, theorem 10.3a. Limit of the n term of a convergent series. If the sum of a sub n when n goes from 1 to infinity converges, then limit of a sub n when n approaches infinity equals 0. But the converse of this theorem is not true, which means if you have limit of a sub n when n approaches infinity equals to 0, then the sum of a sub n when n goes from 1 to infinity, this one is wrong. So be careful, okay? So keep this one in mind, which means unknown. Now, let's move on to the important theorem for this lesson, n-term test for divergence. If limit of a sub n when n approaches infinity not equal to 0, then the sum of a sub n when n goes from 1 to infinity diverges. Alright, so keep that one in mind. Now let's take a look at the first example. Using the n-term test for divergence, determine the convergence or divergence of each series. Question A. The sum of n over n plus 1 when n goes from 0 to infinity. Alright, so we're going to use n-term test for divergence, right? So we're going to take limit of n over n plus 1 when n approaches infinity, right? It's going to be right here. Alright, so when n approaches infinity, n grows faster than 1, right? So we can rewrite this one as limit of n over n. When n approaches infinity, we just ignore 1, right? So this one equals 1, not equal to 0, right? So by the n-term test for divergence, this series divergence, right? Now question B. We have limit of 1 plus 3 to the n over 2 to the n when n approaches infinity equals. This guy right here grows faster than this guy, right? So we just ignore 1, right? So we have limit of 3 to the n over 2 to the n when n approaches infinity. It's going to be limit of 3 over 2 to the n when n approaches infinity, right? And it's going to be infinity, right? So by the n-terms test for divergence, this guy's divergence, right? Now we have another way to do this one. We can use geometric series, right? So the common ratio is 3 over 2, which is greater than 1. Then by the geometric series, the series divergent, right? Now question C. We have limit of 1 over n when n approaches infinity equals 0, right? This one is inconclusive, right? Now question D. We have limit of n cubed over n factorial when n approaches infinity. Now remember, this one is exponential function. This one is factorial function. Factorial grows significantly faster than exponential function, right? So the bottom is much larger than the top, and then this one becomes 0, right? So you can say this one is inconclusive, right? Now let's take a look at the example number 2. For each series below, decide whether it converges or diverges and explain your reasoning. We have limit of 3 minus 2n over 5n plus 1 when n approaches infinity. This guy grows faster than this guy, right? This guy grows faster than this guy, right? So we can ignore 3 and 1 right here, right? So we have limit n approaches infinity of negative 2 and over 5n, right? N and n cancel out, so it's going to be negative 2 over 5, which is not equal to 0, right? So by the n-term test for divergence, this series diverges, right? Now question 2. We have limit of 3 to the n plus 1 over 5 to the n when n approaches infinity, right? So it's going to be limit of 3 times 3 to the n over 5 to the n when n approaches infinity. And it's going to be limit of 3 times 3 over 5 to the n when n approaches infinity, right? Now, when n approaches infinity and this fraction is greater than 0, less than 1, so it becomes 0, right? 0 times 3 is going to be 0, right? Now, by the n-term test, it is inconclusive, right? We can use geometric series to determine if the series convergent or divergent. Now, we look at this one right here. This guy actually geometric series, right? Where common ratio is 3 over 5, right? Which is less than 1, right? So then the series convergence, right? Now by the formula we have a over 1 minus r, right? A is the first term. The first term when n equals 1. You substitute over here, you have 9 over 5, right? Over 1 minus 3 over 5. Now, it's going to be 9 over 5 over 2 over 5. Multiply the top and bottom by 5. So the answer is 9 over 2. So the series convergent to this number. Now, question 3. We're going to take limit of 2n over square root of n squared plus 1. When n approaches infinity, it's going to be limit of 2n over n squared grows faster than 1. We can ignore this one, right? So we only have square root n squared when n approaches infinity. And it's going to be limit of 2n over absolute value of n when n approaches infinity. Now, when n approaches infinity, this guy always positive, right? So you can remove the absolute value side, right? So it could be limit of 2n over n when n approaches infinity. N and n cancel out, so it could be 2, right? So by the n-term test, this series diverges, right? Now, question 4. We have limit of e to the n plus 1 over pi to the n when n approaches infinity, right? So it's going to be limit of e times e over pi to the n when n approaches infinity, right? Now this guy actually equals 0, right? Because e equals 2.171828, etc. And pi is going to be 3.14 something, right? So the top is less than the bottom. When n approaches infinity, this guy approaches 0. 0 times e is going to be 0, right? Now, so then we can say that this guy is inconclusive, right? We can use the geometric series to determine if this one convergent or divergent, right? So we look at this one right here. The common ratio is e over pi, right? And the first term is e times e over pi, right? So we have the formula a over 1 minus r, right? This guy right here less than 1. So the series converges, right? So it could be e squared over pi over 1 minus e over pi. So it could be e squared over pi over pi minus e over pi. Multiply the top bottom by pi. So it could be e squared over pi minus e. Alright, so finally the series converges to this number, right? Now question 5. We have limit of 7 to the n plus 1 over 7 to the n plus 1 when n approaches infinity. Now when n approaches infinity, this guy grows faster than this guy, right? We can ignore 1, right? So we have limit of 7 to the n over. You cannot say you're gonna ignore 1 right here. Be careful, okay? You only ignore the 1 on the top. That's it, right? This one is addition. This one is the multiplication, right? So you have 7 to the n times 7 when n approaches infinity, right? So it's gonna be 1 over 7, right? Because this one cancel out, right? and this one not equal to 0, right? So we can say this series diverges by the n-term test. Now question 6, we have limit of phi times phi over 2 to the n when n approaches infinity. Now look at the fraction right here, the top greater than the bottom. So when n approaches infinity, this guy approaches infinity, so this guy equals infinity, right? So by the n-term test, the series diverges, right? Now we have a second way to do this one. Observe that this guy actually geometric series, right? With the common ratio equals phi over 2, right? But phi over 2 is greater than 1, right? So by the geometric series, this series diverges, right? Because the common ratio is greater than 1, right? Now let's take a look at example number 3. For each series below, decide whether it converges or diverges and explain your reasoning. The n-term test can be used to determine divergence for which of the following series. Alright, so we're going to take limit of psi to n when n approaches infinity. This guy does not exist. You know that the psi function is going to be oscillating between 1 and -1, right? So when n approaches infinity, this guy does not exist, right? So it tells us that this guy diverges, right? Now, question 2, we have limit of 2 plus 3 over n when n approaches infinity, right? This guy approaches 0, so it's going to be 2 not equal to 0, right? So this one diverges, right, by the n-term test, right? Number 3, we have limit of n cubed plus 1 over n squared when n approaches infinity. We can ignore 1, right, because this guy grows faster than this guy, right? So we have limit of n cubed over n squared when n approaches infinity, right? We're going to simplify this one, so it could be limit of n when n approaches infinity, and it's going to be infinity, right? So this series diverges, right, by the n-terms test. So the final answer must be D. Now question B, we still use the n-terms test, right? So we have limit of natural log of n minus 1 over n when n approaches infinity. It's going to be limit of L and up. When n approaches infinity, this guy grows faster than this guy, right? So we have n over n. We just ignore -1, right? When n approaches infinity, and it's going to be limit of ln up 1, right? When n approaches infinity. So it could be ln of 1 equals 0, right? So it could be 0. And this one is inconclusive, right? Now question B, we have limit of 3n minus 2n squared over 5n squared when n approaches infinity. Now when n approaches infinity, this guy right here grows faster than this guy, right? So we can ignore this guy, right? So we have limit of -2n squared over 5n squared when n approaches infinity, right? n squared cancel out, so this could be -2 over 5, not equal to 0, right? So by n-term test, this guy diverges, right? Now number 3, we have limit of 3 times 5 over 4 to the n when n approaches infinity. Alright, look at the fraction right here, 5 greater than 4. So when n approaches infinity, this guy approaches infinity, right? So by n-term test, this one diverges, right? Now we have the second way to do this one. We're going to use geometry series where the common ratio is 5 over 4 greater than 1. So then this one still diverges, right? Now go back to this question. We need to determine the divergence, right? So only B. Correct, right? Now example number 4. If a sub n equals cosine of pi over 2n for n equals 1, 2, 3, etc. Which of the following about the sum of a sub n when n goes from 1 to infinity must be true, right? Now we can take this limit, right? It's the same thing as limit of cosine of pi over 2n when n approaches infinity, right? So then this guy becomes 0, right? So it could be limit of cosine of 0, right? When n approaches infinity, cosine of 0 equals 1, right? This guy not equal to 0, right? So by the n term test, the series diverges, right? So the answer must be C. We're going to explore topic 10.4, the integral test for convergence. Alright, let's talk about the theorem. Suppose the function f(s) is positive, continuous, and decreasing. These three guys extremely important. Okay, you must have these three guys happen in order to apply this theorem, right? On the interval k to infinity, where k is a positive integer greater than or equal to 1, and ls equal a sub n, right? Number 1. If the interval from k to infinity of ls ds is convergent, so is the series. Number 2. If the interval from k to infinity of ls ds is divergent, so is the series, right? The integral test will always result in having to evaluate an improper integrals, which you learn in topic 6.13. The AP Calculus BC exam has required students to state the conditions for which the integral test can be applied. You typically will not have to prove they apply, rather just state that they apply. Alright? Now I'm going to rule the first one. If the integral from k to infinity of ls ds is convergent, so is this series, right? Now you look at this function right here, it's going to be decreasing, right? It's continuous, right? And it's positive because it's above the x-axis, right? Now I'm going to use the right endpoint Riemann sum. We have this point right here is the height of the rectangle. It's going to be f of 2. And this guy actually a sub 2, right? This guy is f of 3. And this guy actually a sub 3, right? This guy f of n. And this guy actually a sub n, right? So the error equals the error of each rectangle, and then you add them up, right? So you know that each rectangle has the width of 1, right? So you have 1 times f of 2, right? Plus 1 times f of 3, plus etc. Plus 1 times f of n, right? And then I just replace f of 2 with a sub 2, right? And then multiply by 1 is going to be itself, right? So it can be a sub 2 plus a sub 3 plus etc. plus a sub n, right? And this guy actually the series of a sub k when k goes from 2 to n, right? This guy actually less than the error under the curve. And the error under the curve is defined as the interval from 1, 2, and of f of s ds, right? Since this one is a decreasing function, the right endpoint remains sum always underestimates the error, right? Now suppose the integral from 1 to infinity of f of s ds converges. It means limit of the integral from 1 to b of f of s ds when b approaches infinity equals a constant. I call this m, right? Now since f of s is positive, right? We have the integral from 1 to n of f of s ds always less than the integral from 1 to infinity of f of s ds, right? Observe that this series right here is less than this one, right? But this one less than this one, right? So by transitive property, we have, now look at this series, it's gonna start from 2, right? But we need this series to start from 1, right? So we're gonna add a sub 1 both sides, right? So we have the series a sub k when k goes from 1 to n less than the integral from 1 to infinity of f of s ds plus a sub 1, right? Now look at this one right here. This guy converges to m, right? So if you add a constant, it still converges, right? So I call this one as capital N, right? Now I'm gonna name this one as S sub n, right? So I have S sub n always less than or equal to S sub n plus A sub n plus 1, right? Because I just add a constant to the series right here. And it's gonna be the series A sub k when k goes from 1 to n plus a sub n plus 1, right? And it's gonna be the series a sub k when k goes from 1 to n plus 1, right? And it's gonna be s sub n plus 1, right? So we just prove that s sub n less than or equal to s sub n plus 1, right? It tells us that S sub n converges. So the series A sub n when n goes from 1 to infinity is also convergence, right? And the first one has been proved, right? Now let's prove the second one. In order to prove the second one, we're gonna use left endpoint remains sum. Now similarly, we have the error equals the width times the height. The height in this situation is going to be f of 1, right? Plus 1 times f of 2 plus etc. plus 1 times f of n minus 1, right? And you know that this guy actually a sub 1. This is a sub 2. This is a sub 3. And this one a sub n minus 1, right? So it could be a sub 1 plus a sub 2 plus etc. plus a sub n minus 1, right? And this guy actually the series of a sub k when k goes from 1 to n minus 1, right? And this guy always greater than the integral from 1 to n minus 1 f of s ds, which is the error under the curve, right? Right? Because we're going to use the left endpoint remains sum on the decreasing function. It's going to be over estimating the error under the curve, right? Now suppose the integral from 1 to infinity of f of s ds is divergent. It tells us that the integral from 1 to n of f of s ds approaches infinity if n approaches infinity, right? And since f of s is positive, right, we can conclude that n minus 1 always approaches infinity, right? So the integral from 1 to n minus 1 of f of s ds approaches infinity, right? Now let's call this one as s sub n minus 1, right? So we have s sub n minus 1 equals series a sub k, k equals 1 to n minus 1, right? Now we're going to add both sides by an, right? So it turns out to be s sub n equals the series a sub k when k goes from 1 to n, right? This guy greater than the integral from 1 to n minus 1 of f of s ds plus a sub n, right? So we can conclude that the partial sum s sub n is divergent, right? Then the series a sub n when n equals 1 to infinity also divergent, right? And we're going to explore topic 10.4b, integral test for convergence. Alright, so we have the theorem, the integral test. Suppose the function f(s) is positive, continuous, and decreasing on the interval k to infinity, where k is a positive integer greater than or equal to 1, and f(s) equals a sub n. Then if the integral from k to infinity f(s) ds is convergent, so is the series. If the integral from k to infinity of f(s) ds is divergent, so is the series. Now, if you want to know why this theorem works, please check out the link in the description below, or check out the video 10.4a. Now, let's take a look at the first example. Using the integral test, confirm whether the integral test can be applied to the series. Then use the integral test to determine the convergence or divergence of the series. Alright. Now, in order to know if the integral test applied to the series, you need three things. First, the function f of s must be positive, right? Second, it must be continuous. And the third one, it must be decreasing. Alright, so let's take a look at the question A. The series of n over n squared plus 1 when n equals 1 to infinity. We're gonna let f of n equals n over n squared plus 1, right? Now we're gonna expand this one. So it turns out to be 1 over 1 squared plus 1 plus 2 over 2 squared plus 1 plus etc. Right? So if you simplify this one, it's going to be 1 over 2 plus 2 over 5 plus etc. Right? And you know that this guy always greater than 0, right? So the function is positive, right? Observe that the bottom one right here is always greater than 1, right? So it never be 0, right? So the function is continuous. Now, in order to know if the function decreasing, we're going to take derivative of this one, right? So we have f prime of n equals, we're going to use the quotient rule, right? So it's going to be n squared plus 1 times 1, right? Minus 2n times n, right? Over n squared plus 1 altogether squared, right? Now we're going to simplify this one. It turns out to be 1 minus n squared over n squared plus 1 altogether squared, right? We need this one to be less than 0 so that the function is decreasing, right? Now we look at the bottom right here. This guy always positive, right? So then the top must be less than or equal to 0, right? So this guy turns out to be 1 minus n squared less than or equal to 0, right? So then n squared greater than or equal to 1, right? And then n greater than or equal to 1, or n less than or equal to negative 1, right? Now we look at this one right here. We see that n always goes from 1 to infinity, right? So this one works, right? We can ignore this guy, right? So the function is decreasing for n greater than or equal to 1, right? It's right here. Now since 3 elements right here satisfies, right? So the integral test applies, right? Now we're going to apply the integral test. So we have the integral from 1 to infinity of n over n squared plus 1 dn. It's going to be limit of the integral from 1 to b of n over n squared plus 1 when b approaches infinity dn, right? Now observe that if you take the derivative of the bottom, it's going to be 2n, right? So we're going to apply the formula right here. N times derivative of u prime over u du is going to be ln absolute value of u plus c, right? So this one I can rewrite as 1/2 limit when b approaches infinity of the integral from 1 to b of 2n over n squared plus 1 dn, right? Now this guy turns out to be 1/2 limit when b approaches infinity of ln absolute value of n squared plus 1 evaluated from 1 to b, right? Now since n squared plus 1 always positive, right? So I can remove the absolute value sign, right? I just put the parentheses, right? So this guy turns out to be 1/2 limit when b approaches infinity of ln of b squared plus 1 subtract ln of 1 squared plus 1, right? And then it's going to be 1/2 when b approaches infinity. Substitute over here, you have ln of infinity subtract ln 2, right? And this guy actually diverges, right? It tells us that the series n over n squared plus 1 when n goes from 1 to infinity diverges, right? Now question B, we're gonna let f of n equals n over square root of 2n minus 5, right? Now first we need to check to see if the function is positive, right? So we need to populate this one, right? So this guy turns out to be 3 over 2 times 3 subtract 5 is going to be square root of 1, right? Plus 4 over 2 times 4 subtract 5 is going to be square root of 3, right? Plus n equals 5, you have 5 over square root of 5 plus 6 over square root of 7 plus etc. right? And you know that the answer of this one always positive, right? So the function f of s is positive, right? According to f of n greater than 0, right? Now we're going to check if the function is continuous, right? Now look at the bottom right here. The domain of this one is going to be 2n minus 5 greater than 0, right? And then n greater than 5 over 2, right? But look at this one right here. You have the interval 3 to infinity. Now every single n in this interval always greater than 5 over 2, right? So then the function is continuous, right? Next one, we need to check to see if the function is decreasing, right? So we're going to take the derivative of the function f of n, right? So we have f prime of n. It's going to be use the quotient rule, right? So it's going to be 1 times square root of 2n minus 5, right? Minus derivative of the bottom is going to be 2 over 2 square root of 2n minus 5, right? Times n over square root of 2n minus 5 all together square, right? Now we're going to simplify this one. 2 and 2 cancel out, and then we're going to multiply this guy. So this guy turns out to be 2n minus 5. And then you have n left right here, subtract n over square root of 2n minus 5 all together cube, right? Bring this one to bottom. Now simplify this one, it's going to be n minus 5 over square root of 2n minus 5 all together cube, right? Now look at the domain right here, it's going to be from 3 to infinity. So this one always positive, right? So in order for this one to be less than or equal to 0, we need n minus 5 less than or equal to 0, right? And then n must be less than or equal to 5, right? The interval 3, infinity can be written as the interval from 3, to 5, right? Union the interval from 5 to infinity, right? Now within this interval, the function is decreasing, right? But this interval is not decreasing, right? Then the integral test does not apply because the third condition does not satisfy, right? Now let's take a look at question C. We're gonna let f of n equals 1 over n squared plus 1, right? And the graph of this function is going to be right here, right? Now we're gonna populate this one. So we have n equals 1, we have 1 over 2. N equal 2, we have 1 over 5. N equals 3, we have 1 over 10, right? Plus etc. And the answer of this series always positive, right? So then we have f of n always positive, right? Now next we're gonna check to see if the function is continuous, right? Now look at this one is the rational function. So in order for this guy to be continuous, this guy must be not equal to 0, right? We look at the domain right here. N goes from 1 to infinity, right? For every single n in this interval, n squared plus 1 always greater than 1, right? And this guy actually not equal to 0, right? So then the function is continuous on this interval, right? Now first one, we're gonna check to see if the function is decreasing, right? So we're gonna take the derivative of f of n, right? Now we're going to use the quotient rule, right? So derivative of 1 equals 0, multiplied by this 1 equals 0, subtract 2n, right? Times 1 over n squared plus 1 all together square. Simplify, it's going to be negative 2n over n squared plus 1 all together square. Now we need this one to be less than or equal to 0, right? So then you have negative 2n less than or equal to 0, right? Because the bottom always positive, right? And then n greater than or equal to 0, right? But if you look at the domain right here, n always greater than or equal to 1, right? But 1 greater than or equal to 0, right? So we can say that the function always decreasing, right? So this guy satisfy, the function is continuous. So we need to say the function f of n is positive, continuous, and decreasing for n greater than or equal to 1. Then the integral test applies, right? We need to take the integral from 1 to infinity of 1 over n squared plus 1 dn. It's going to be limit when b approaches infinity of the integral from 1 to b of 1 over n squared plus 1 dn, right? And it's going to be limit when b approaches infinity of a tangent of n, right? Evaluated from 1 to b, and it's going to be limit when b approaches infinity of a tangent of b subtract a tangent of 1, right? Now when b approaches infinity, a tangent of b approaches pi over 2, and a tangent of 1 equals pi over 4, and it's going to be pi over 4, right? And this one is a constant. Then we can say that this integral right here convergent, right? If this one convergent, the series must be convergent, right? Let's move on to question D. We're gonna let f of n equals 1 over n ln of n, right? Now we're gonna check to see if the function is positive, continuous, and decreasing, right? So we're going to populate this one, right? So n equal 2, we have 1 over 2 ln 2 plus 1 over 3 ln 3 plus 1 over 4 ln 4 plus etc., right? So the answer of this one always positive, right? So the function is positive, right? So the first one works. Now check to see if the function is continuous, right? The domain of this function is n not equal to 0 for this guy, right? And right here, n must be greater than 0, right? So n must be greater than 0 is the domain, right? But we look at this one right here, n start from 2 all the way to infinity, right? So the function is continuous on the interval 2 to infinity, right? So the second one satisfied. Now the third one, we need to take derivative of this guy, right? So f of n equals, we're going to use the quotient rule, right? So derivative of 1 equals 0, multiplied by this 1 equals 0, minus n times l n of n prime, right, over n times ln of n all together squared, right? Now we're going to use the product rule, right? So it could be negative of of n 1 over n times n over n times ln of n altogether squared, right? So this one turns out to be negative ln of n minus 1 over n times ln of n altogether squared, right? We need this one to be less than or equal to 0, right? So does that mean you have negative ln of n minus 1 less than or equal to 0, right? Multiply both sides by negative 1, so we have ln of n plus 1 greater than or equal to 0, right? Now we look at the domain right here, n always between 2 and infinity. So this tells us that this one always greater than or equal to 0, right? So the function always decreasing, right? So then the third condition right here satisfied, right? Now we can take integral from 2 to infinity of 1 over n ln of n dn can be written as limit when b approaches infinity of the integral from 2 to infinity of d of ln of n over ln of n, right? Or you can use u substitution. If you let u be ln of n, you still get the same answer, right? So I can apply the formula directly. It's going to be antiderivative of du over u equals ln of absolute value of u plus c, right? Where u equals ln of n, right? So then this guy becomes limit when b approaches infinity of ln absolute value of ln of n, right? Evaluated from 2 to b, right? So this guy turns out to be limit when b approaches infinity of ln absolute value of ln of b subtract ln absolute value of ln of 2. Now when b approaches infinity, this guy right here approaches infinity, subtract ln absolute value of ln of 2, and it's going to be infinity, right? So this guy diverges, right? If this guy diverges, it tells us that the series diverges, right? Now let's move on to example number 2. I'm going to leave this one for you to practice. I just give you the answer key and a hint, right? Now for this one, you're going to let f of n equals n over e to the n, right? And this guy converges. Question 2. F of n equals, observe that this one right here. 1 right here can be written as 1 over 1, right? So if n equals 1, you have 1. N equals 2, you have 4. N equals 3, we have 9. So does that mean it's going to be 1 over n squared, right? And this series converges. Now, number 3, 1 can be written as 1 over 1, right? So if n equals 1, you have 1. N equals 2, you have 2. N equals 3, you have 3, right? So f of n equals 1 over n, right? And this one diverges. Now, number 4, f of n equals 1 over n squared sine of pi over n. And this one converges. Now, number 5, f of n equals n over n squared plus 1. And this one diverges. And the last one right here, f of n equals n to the k minus 1 over n to the k plus 2. You're gonna let u equals n to the k plus 2, right? And then this one diverges. Now question 8. Explain why the integral test does not apply for this series, right? So we're gonna let f of s equals e to the s times sine s, right? Now for s go from 1 to infinity, this function is continuous, right? We're gonna print up the calculator. We're gonna graph this one. We're gonna add graph right here. E to the s times sine s, and then press enter. Now for s greater than 1, the function sometimes positive, sometimes negative, right? It's up and down, right? So f of s is not positive on the interval 1 to infinity, right? If one of the condition is not met, then the integral test does not apply, right? Now question 9, I'm gonna leave this one for you to practice using the calculator, right? Now let's move on to question 10. Question 10 similar to question 7, right? The answer must be D. Now let's move on to question 11. Which of the following can be used to determine the convergence or divergence of this series, right? Number 1, properties of geometric series. Number 2, n-term test. Number 3, integral test, right? Now, we just review geometric series. A plus A times R plus A times R squared plus etc., right? And then the common ratio right here must be less than 1 in order for the series to be convergent, right? Now this guy not the geometric series, so number 1 does not apply, right? Now number 2, n-term test. In order to apply the n-term test, you need to take the limit of n plus 3 over n plus 4 when n approaches infinity, right? Now when n approaches infinity, this guy grows faster than 3. This guy grows faster than 4. So we can ignore 3 and 4, right? So it could be limit when n approaches infinity n over n, right? It could be 1 not equal to 0, right? This series diverges, right? Now number 3, in order to apply the integral test, we need the function to be positive, right? Continuous, right? And decreasing, right? If one of these criteria fails, then the integral test does not apply, right? Now we have the domain is going to be from 1 to infinity, right? So then the function right here always positive. This one applies, right? Continuous, right? Because the domain of this one n not equal to negative 4, right? But n from 1 to infinity right here is always different from negative 4, right? So this one continuous. Now to check if the function is decreasing on this interval, we're gonna take derivative of f of n, right? So it could be quotient rule, right? So it could be n plus 4 minus n plus 3 over n plus 4 all together square, right? N subtract n is going to be 0. 4 subtract 3 is going to be 1. 1 over n plus 4 all together square, right? This one always greater than 0, right? So the function f of n is increasing, right? So then this guy right here is not satisfied, right? So the integral test does not apply, right? Only number 2 right here works, right? So the answer must be B. Now question 12, similar to question 11, right? So we can rewrite this one as the series 1 over 2 altogether to the n when n goes from 1 to infinity, right? So we're gonna let f of n equals 1 over 2 altogether to the n, right? Now, this guy actually geometry series, right? Because if n equal 1, you have 1 over 2. N equal 2, you have 1 over 2 altogether square. And n equal 3, 1 over 2 altogether cube, right? And the common ratio is 1/2 less than 1, right? The series converges, right? So number 1 works. Now, n-term test, we need to take the limit of 1 over 2 to the n when n approaches infinity. It's going to be 0, right? We can say that this one is inconclusive. We don't know if the series convergence or divergence, right? So number 2 is wrong. Now number 3, integral test. We need to check to see if the function is positive, continuous, and decreasing, right? Now, we populate this series, we get this one right here. So it's always positive, right? So this one satisfies. Now, second condition right here, the function is continuous. Yes, the function always continuous, right? So this one satisfies. Now, to know if the function is increasing or decreasing, we're going to take derivative, right? So f prime of n equals. We're going to use the quotient rule, right? So the derivative of 1 equals 0, right? Times this one equals 0. Subtract 2 to the n prime, right? Times 1 over 2 to the n altogether square, right? Now, derivative of 2 to the n, we're going to use the formula derivative of a to the s is going to be ln of a times a to the s, right? So this guy becomes negative 2 to the n times ln of 2 over 2 to the n altogether square, right? And this guy always less than 0, right? Because this one right here always positive, this guy positive, and you multiply by negative 1, it's going to be less than 0. If it's less than 0, it tells us that the function is decreasing, right? So the third condition satisfied, right? So the answer must be E. Now let's move on to question 13. Consider the infinite series 1 over n cubed when n goes from 1 to infinity. The integral test can be used to determine the convergence or divergence of the series because f of s equals 1 over s cubed is positive, continuous, and decreasing on this interval. Which of the following is true? Alright. So since f of s is 1 over s cubed is positive, continuous, and decreasing on this interval, the integral test comparison bounds apply. So we have the integral form 1 to infinity of f of s dx less than or equal to the series f of n when n goes from 1 to infinity less than or equal to f of 1 plus the integral from 1 to infinity of f of s dx, right? Now we're going to substitute f of s equals 1 over s cubed and f of 1 actually 1, right? So we have this guy right here. We're going to explore topic 10.5 harmonic series and P series of AB calculus BC. Now let's talk about the definition of P series. A P series is an infinite series of the form sigma of 1 over n to the p when n goes from 1 to infinity. Now, if you populate this series, it's going to be 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, etc. until 1 over n to the p, where p is a positive number. Alright, so keep that in mind. Now, example number 1. Which of the following series are P series? We need to rewrite this one as sigma when k equals 1 to infinity of 1 over k to the 0.8, right? So P equals 0.8, and it's going to be positive, right? So you say yes. Now question B, we're going to rewrite this one as sigma when n goes from 1 to infinity of 1 over 2 to the n. Now look, P must be a positive number, not a variable, right? This one is the variable, so we say no, right? Now question C, it's going to be sigma of 1 over k to the 4 when k goes from 10 to infinity. Now, the starting index does not affect the convergence, so we don't have to worry about this one. What we need to worry is this guy right here, right? So P equals 4 greater than 0, right? So we're gonna say yes. Now question D, this one not a P series, right? Now question E, yes, because P equals 1, right? It's going to be right here. Now question E is the special case of the P series, that is called harmonic series. Now theorem 10.5, a convergence of a P series. Alright, the P series is convergence if P greater than 1 and divergence if P greater than 0, less than or equal to 1. Alright, example number 2, we're going to apply the P series theorem. Alright, determine whether the following series converges or diverges. Now we need to rewrite this one as sigma when k goes from 1 to infinity of 1 over k to the 3 over 4, right? So P equals 3 over 4 less than 1. Then this P series diverges, right? Now question B. Again, the starting index does not affect the convergence. Alright, so we don't have to worry about this guy. Now for this guy right here, we just left m equals n minus 1. So then this guy becomes sigma of 1 over m squared when n goes from 4 to infinity. So P equals 2 greater than 1. Then the P series converges, right? Now question C. This guy is not a P series because the base right here and this guy right here different, right? However, this one is a geometric series. Alright, so this one can be written as 1 over e squared plus 1 over e cubed plus 1 over e to the 4 plus etc, right? So the common ratio is 1 over e, which is less than 1. So this series converges, right? Now example number 3. Determine the convergence or divergence of the following P series. Alright, so we just rewrite this one as 1 plus 1 over 2 square altogether power of 1/3, right? Plus 1 over 3 square altogether power of 1/3, plus 1 over 4 square altogether power of 1/3, plus 1 over 5 square altogether power of 1/3, plus etc. Right? Now 1 right here, I can rewrite this one as 1 over 1 square power of 1/3, right? So I can rewrite this one as a series. So it could be sigma when n goes from 1 to infinity of 1 over n power of 2/3, right? Because if you multiply 2 by 1/3, 2 by 1/3, you get every single thing should be 2/3, right? So this guy actually the p series where p equals 2/3, which is less than 1, right? So the series diverges, right? Now we're gonna move on to the next one, the harmonic series. This is a special case of a p series. Why? Because the p right here equals 1. Right? So then we have this guy right here. So remember, if p greater than 1, the p series converges. Right? If p greater than 0 less than or equal to 1, the p series diverges. Right? So the harmonic series always diverges. Right? Because p equals 1. Right? So it falls into this case. Right? Now let's take a look at example number 4. Which of the following infinite series converges? Now number 1, we just rewrite this one as sigma of 1 over n power of 1/2 when n equals 1 to infinity, right? So p equals 1 over 2 less than 1. The series diverges, right? Now, question 2. This is power of negative n. We can rewrite this one as sigma when n goes from 1 to infinity of 2 over e power of n, right? And this one is not p series. This guy actually geometric series where the common ratio equals 2 over e less than 1, right? Because e equals 2.171828, right? So then the geometric series converges. Now question 3. This guy actually the p series where p equals e, which is greater than 1. So this one is convergent, right? Now the question asks us to find the series that converges, right? So 2 and 3 correct, so the answer must be E. Now question B. We're gonna rewrite this one as sigma when n goes from 1 to infinity of 1 over 3 raised to the n, right? This is not a p series. But this one is a geometric series where the common ratio equals 1 over 3 less than 1. So the series converges. Now, question 2. We can use the integral test or we can use the p-series test by letting m equals 3n plus 1, right? So this guy becomes sigma when n goes from 1 to infinity of 1 over m cubed, right? So p equals 3 greater than 1. So then the p series converges, right? Number 3 can be written as sigma when n goes from 1 to infinity of 1 over n power of 1 over 5, right? So p equals 1 over 5 less than 1. So the series diverges, right? Now we need the series to be convergent. So only 1 and 2 correct, right? So the answer must be D. Now question C. Which of the following infinite series is a divergent P series, right? So in order for the P series to be divergent, P must be less than or equal to 1, greater than 0, right? Now question A, this guy not a P series, this guy actually geometric series, right? Where the common ratio equals 1 over 4 less than 1. So the series converges, right? Now B can be written as sigma of 1 over n power 1 half, right? When n goes from 1 to infinity. Now this guy actually the P series, right? Where P equals 1 half less than 1. So this one is divergent, right? Now C can be written as sigma of 1 over n raised to the 3½ when n goes from 1 to infinity, right? And this is actually the P series where P equals 3½, right? Greater than 1. So this one convergent, right? Now D, this is not a P series, right? However, you can use the integral test or n-term test to determine the convergence of the series. Now the question asks us to determine the divergent P series, right? So the answer must be B. Now question D. Which of the following is not a P series? A can be written as sigma of 1 over n to the third when n goes from 1 to infinity, right? This guy actually the P series, right? Now question B. This guy actually harmonic series, right? C. This guy actually the P series, right? Where P equals pi. Now D. This guy not a P series, right? Because this guy right here must be a variable, not a constant, right? So the answer must be D. Now question E. Which of the following is a harmonic series? You know that harmonic series P equals 1, right? So we look at this one right here. Answer A is wrong, right? Because this is multiplication. Answer B, yes. P equals 1, right? So yes. Answer C, no, right? Because this guy is not infinity, right? Answer D is no, right? So the answer must be B. Now let's move on to question F. Find the positive values of K for which the series converges. Alright, so in order to do this one, we need to rewrite this one as an integral, right? So it could be integral from 3 to infinity of 1 over s ln s times ln of ln s to the k, right? Now we're gonna do u substitution. So we're gonna let u be ln of s, right? It's gonna be this guy right here. So then du equals 1 over ln of s times 1 over s ds, right? And it's gonna be 1 over s ln s ds, right? So this guy becomes, when s equals 3, we have the integral form ln of 3 to infinity of 1 over u, right? This one equals u. And this one right here, actually du, right? So I put du right here. And this one power of k, right? Now we're gonna apply the P series rule for the integrals. This integral is now in the form of a standard P integral. An integral of the form antiderivative of 1 over u to the k du converges if and only if k greater than 1, right? We're going to learn how to prove the direct comparison test for convergence. Now, theorem 10.6a, the direct comparison test. Let the series an greater than 0 less than equal to series bn for all n. Number 1. If the series bn converges, then the series an converges. Number 2. If the series an diverges, then the series bn diverges. Alright. Now we're gonna prove number 1 first, right? So let's start off with the partial sums of each series. Now since a sub n and b sub n greater than or equal to 0, right? So we have s sub n always less than s sub n plus a sub n plus 1, right? Now s sub n equal this guy right here, right? So I just replace s sub n with this guy, right? So it's gonna be the series ai when I goes from 1 to n plus a sub n plus 1, right? And this guy actually the series ai when I goes from 1 to n plus 1, right? I combine this guy and this guy, right? And this guy actually s sub n plus 1, right? Now similarly we have now on the top right here we can conclude that s sub n less than equal to s sub n plus 1. The bottom y sub n less than equal to y sub n plus 1, right? From these two guys we can conclude that Sn and Yn are increasing sequences, right? Now, since a sub n less than or equal to b sub n for all n's, right? Then we can conclude that s sub n less than or equal to y sub n, right? Now, number 1. Suppose the series b sub n when n goes from 1 to infinity converges. And we know that b sub n always positive, right? So we have y sub n equals the partial sum bi when I goes from 1 to n always less than or equal to the series bi when I goes from 1 to infinity, right? But s sub n less than or equal to y sub n, right? So from these two guys right here, we can conclude that s sub n less than or equal to the series b sub I when I goes from 1 to infinity by transitive property, right? But this guy right here converges, right? Then s sub n converges, right? But s sub n is the partial sum, right? So when the partial sum converges, the series must be convergent, right? Now let's prove number 2. If series a sub n diverges, then the series b sub n diverges. Now suppose the series a sub n diverges. Since a sub n positive, right? The limit of s sub n when n approaches infinity is infinity, right? Also, we know that s sub n always less than or equal to y sub n we proved above, right? So we can conclude that limit of y sub n when n approaches infinity is infinity, right? So it tells us that the series b sub n when n goes from 1 to infinity diverges, right? We're going to learn how to prove the limit comparison test. Suppose a sub n greater than 0, b sub n greater than 0, and limit of a sub n over b sub n when n approaches infinity equals L, or limit of b sub n over a sub n when n approaches infinity equals L, where L is a finite and positive number, right? It means L between 0 and infinity. Then the two series a sub n and b sub n either both converge or both diverge. Alright, now since 0 less than L less than infinity, we can find two positive and finite numbers s less than L less than y. Since limit of a sub n over b sub n when n approaches infinity equals L. So there must be a positive integer n such that if little n greater than capital N, we have s less than a sub n over b sub n less than y, right? Now we're going to multiply 3 sides by b sub n, so we have s times b sub n less than a sub n less than y times b sub n, right? Now if the series b sub n converges, we can conclude that the series y times b sub n converges, right? But a sub n less than y times b sub n, right? So we can conclude that the series a sub n converges, right? By direct comparison test, right? Now the second case, if the series b sub n diverges, the series s times b sub n diverges, right? But s times b sub n less than a sub n, right? So we can conclude that the series a sub n diverges, right? By the direct comparison test, I call this DCT, right? We're going to explore topic 10.6 comparison test for convergence. Alright, in this topic, we're going to explore two theorems. The first one is going to be direct comparison test. This theorem has been proved in the video 10.6a. And the second one is going to be limit comparison test. And this theorem has been proved in the video 10.6b. Now let's take a look at the direct comparison test theorem. Let a sub n less than or equal to b sub n and both positive for all n. If the series b sub n converges, then the series a sub n converges. If the series a sub n diverges, then the series b sub n diverges. Now I have tips for you to memorize this theorem. If the larger series converges, the smaller series must also converge, right? We look at this one right here, b sub n larger than a sub n, right? So if the series b sub n converges, then the smaller series a sub n converges, right? Now the second one, the smaller series diverges, then the larger series must also diverge. Now we look at this one right here, the smaller one diverges, then the larger one diverges, right? Now let's take a look at the first example using the direct comparison test. Determine the convergence or divergence of the following series, right? So we're going to start with this guy right here. So we have 2 plus 3 to the n always greater than 3 to the n, right? Now, I'm going to take reciprocal both sides. So it could be 1 over 2 plus 3 to the n. It's going to be less than 1 over 3 to the n, right? So then I have the series 1 over 2 plus 3 to the n when n goes from 1 to infinity less than the series of 1 over 3 to the n when n goes from 1 to infinity, right? Now look at the one on the right hand side right here. This guy can be written as sigma when n goes from 1 to infinity of 1 over 3 altogether to the n, right? And this guy actually geometric series, right? Where the common ratio equals 1 over 3 less than 1. So this geometric series converges, right? Now if the larger converges, the smaller must converge, right? Now question B. Question B is slightly different from question A. Alright, so we have 2 plus square root of n always less than or equal to 2 plus n, right? I take reciprocal both sides, so it could be 1 over 2 plus square root of n greater than or equal to 1 over 2 plus n, right? So I'm gonna put the summation in the front. N goes from 1 to infinity. Alright, now I'm gonna use U substitution for this one. So that I'm gonna use P series, right? This is 2 plus n. I'm gonna let U be 2 plus n, right? N equals 1, we have U equals 3, right? N equals infinity, you have U equals infinity, right? So then I have sigma of 1 over U when U goes from 3 to infinity, right? So then I'm gonna shift this one back over here by changing the index, right? So this guy is the same thing as sigma when n goes from 3 to infinity of 1 over n, right? And this guy actually the harmonic series or the P series, right? Where P equals 1 less than or equal to 1. So then this series diverges, right? By the P series, right? The smaller diverges, the larger one must diverge, right? By the direct comparison test. Now example number 2, we're going to use direct comparison test. So we have n squared minus cosine square of n always less than or equal to n squared, right? I'm going to take reciprocal both sides. So I have 1 over n squared minus cosine square of n greater than or equal to 1 over n squared, right? I'm going to multiply both sides by n. So I have, now I'm going to put the summation in the front. So I have, I'm going to simplify this one. It's going to be sigma when n goes from 1 to infinity of 1 over n. This guy actually the P series, right? Or you can say harmonic series, right? And P equals 1 less than or equal to 1. So this series diverges, right? So the smaller diverges, the larger one must diverge, right? By the direct comparison test, I call this DCT. But on the AP exam, you need to write this one out, right? You need to write this one out. Now, question B. We have n plus cosine square of n always greater than or equal to n, right? Now, I'm going to take reciprocal both sides. So I have 1 over n plus cosine square of n less than or equal to 1 over n, right? Now I'm going to multiply both sides by e to the negative n. So I have, but this guy always less than or equal to e to the negative n, right? So I have sigma when n goes from 1 to infinity of e to the negative n over n plus cosine square of n less than or equal to sigma of e to the negative n when n goes from 1 to infinity, right? Now I can convert this one to the integral. So integral from 1 to infinity of e to the negative s ds, right? Now I'm going to use the integral test. So I'm going to let f of s equals e to the negative s. Now it's easy for you to verify that this function always positive, right? Continuous and decreasing, right? So I'm going to calculate the integral from 1 to infinity of e to the negative s ds equals limit when b approaches infinity of the integral from 1 to b of e to the negative s ds, right? So it's going to be limit when b approaches infinity of negative e to the negative s evaluated from 1 to b. So it's going to be negative e to the negative b, right? Subtract, and it's turned out to be at e to the negative 1, right? So it's going to be limit when b approaches infinity of negative 1 over e to the b, right? Plus 1 over e, right? Now when b approaches infinity, this guy approaches 0, right? So you're going to end up with 1 over e, right? And this one actually a constant. So this guy right here converges, right? Now since this guy converges, this series right here must converge, right? By the integral test, right? Now let's move on to question C. So we have n squared plus 2 over n to the 4 plus 5 is going to be less than n squared plus 2 over n to the 4, right? You can drop 5, right? So this guy can be written as n squared over n to the 4 plus 2. So I have, now I can simplify this one. So this guy turns out to be sigma when n goes from 1 to infinity of 1 over n squared, right? Plus I can bring 2 to the front, right? So I have 2 sigma of 1 over n to the 4. N goes from 1 to infinity. Observe that these two guys right here are p series, right? Where p equals 2 greater than 1, and this one p equals 4 greater than 1, right? So then these two series are convergent, right? Now each of this one convergent, the sum must be convergent, right? Now since the larger convergent, the smaller one must be convergent, right? So this one converges. Suppose a sub n greater than 0, b sub n greater than 0. If you have the limit of a sub n over b sub n equals L, where L is a finite and positive number, then both a sub n and b sub n either converge or diverge, right? Example number 2 show that the following general harmonic series diverges. So let a sub n equals 1 over a n plus b. Now we're going to compare this one with the p series, right? So the p series is going to be b sub n is going to be 1 over n. Now we're going to take limit of a sub n over b sub n when n approaches infinity, right? So it could be limit of 1 over a n plus b over 1 over n when n approaches infinity, right? Now I'm going to multiply the top and bottom by n, right? So it's going to be limit of n over a n plus b when n approaches infinity, right? Now when n approaches infinity, this guy doesn't really mean anything, right? We can ignore this one. So it's going to be limit of n over a times n when n approaches infinity. This guy cancel out, right? So it could be 1 over a, right? This guy is a constant, right? Now we go back to the limit comparison test, the constant L right here, right? Now, since this one right here is the harmonic series, right? And harmonic series always diverges, right? So, is this one, right? Now you have helpful examples in choosing an appropriate p-series when using the limit comparison test. Alright, when it comes to this one, you need to use this guy right here. Alright, and this guy actually the p-series where p equals to greater than 1, and this guy converges by the p-series test, right? So if this one converges, this one converges, right? Now for this one right here, we need to use this guy right here, right? And this guy turns out to be 1 over n power of 1/2, right? And this guy p equals 1/2 less than or equal to 1, and this series diverges. So this guy diverges, right? Now for this guy right here, we can drop this guy and this guy, right? We're gonna use this guy right here, right? And we simplify n squared, it's gonna be this one. So this one actually the p series where p equals 3 greater than 1, and it's gonna be converges, right? And if this one converges, this one converges, so they both converges, right? Now example number 3, using the limit comparison test to determine the convergence or divergence of the following series. Alright, so we're gonna pick the series square root of n over n squared, right? When n goes from 1 to infinity, right? I call this one a sub n. I call this one b sub n, right? When n approaches infinity of a sub n over b sub n equals limit when n approaches infinity of square root of n over n squared plus 1 divided by square root of n over n squared, right? So it's going to be limit when n approaches infinity. When this guy divided by this guy, you're going to multiply by its reciprocal, right? So it could be square root of n over n squared plus 1 times n squared over square root of n, right? Now this guy cancel out, right? So you have limit when n approaches infinity of n squared over n squared plus 1. So we're going to use relative growth rate, right? So number 1 right here doesn't really matter, right? So we have limit of n squared over n squared when n approaches infinity, right? This guy cancel out, the answer is 1, right? So this guy actually a constant, right? Now we're gonna go back over here. We check to see if this guy converges or diverges, right? So we're gonna rewrite this one as sigma when n goes from 1 to infinity. This is n power of 1/2. This guy n square, right? So we're going to simplify this one. It turns out to be sigma when n goes from 1 to infinity of 1 over n power of 3.5, right? Now this guy actually the p series, right? P equals 3.5 greater than 1. So this series converges, right? By the p series, right? This guy converges and the limit is a constant. This guy must be convergent, right? Now question B. We need to use the limit comparison test, right? So we have n times 2 to the n over 4n cubed plus 1, right? This guy is similar to n times 2 to the n over 4n cubed, right? Because when n approaches infinity, number 1 doesn't matter at all, right? And then this guy is the same thing as 2 to the n over n square, right? N and n right here cancel out, right? Number 4, you just ignore it, right? So then we're gonna compare this guy with this guy, right? So we're gonna take the limit of, I call this a sub n. I call this one as b sub n, right? So a sub n is gonna be n 2 to the n over 4n cubed plus 1 divided by 2 to the n over n square, right? When n approaches infinity, is the same thing as limit when n approaches infinity of n times 2 to the n over 4n cubed plus 1 times n square over 2 to the n, right? So then this guy cancel out, right? And then you have limit when n approaches infinity of n cubed, right? Because n times n squared is going to be n cubed over 4n cubed plus 1, right? We're going to use the relative growth rate, right? So number 1 right here doesn't matter at all, right? So it could be limit of n cubed over 4n cubed when n approaches infinity. This guy equals 1 over 4 because this guy cancel out, right? And this guy is a positive and finite numbers, right? So by the limit comparison test, this guy and this guy both either converge or diverge, right? Now we're gonna check this guy to see if this guy is convergent or divergent, right? So we're gonna take limit of this guy 2 to the n over n squared when n approaches infinity. It's gonna be indeterminate form, right? So I'm gonna use L'Hospital rule, right? So it could be limit when n approaches infinity. The derivative of this one is gonna be ln of 2 times 2 to the n, right? Over 2n. And it's still indeterminate form, right? So we're gonna L'Hospital rule one more times, right? So it could be ln of 2 altogether square times 2 to the n over 2. Alright, so this guy actually infinity, right? Not equal to 0, right? So by the n term test, this limit right here diverges, right? So if this guy diverges, the original one right here diverges, right? Now let's move on to question C. So we have 1 over 3 to the n minus n. It's going to be the same thing as 1 over 3 to the n, right? Because they behave the same thing when n approaches infinity, right? So we can call this one as b sub n, right? So we have limit of a sub n is going to be 1 over 3 to the n minus n divided by 1 over 3 to the n when n approaches infinity. Remember this one is a sub n, right? So then it's going to be limit of, I'm going to multiply the top and bottom by 3 to the n, right? So it could be 3 to the n over 3 to the n minus n, right? When n approaches infinity, right? So this one right here grows faster than this guy, right? So we can ignore this guy. So it could be limit of 3 to the n over 3 to the n when n approaches infinity. This guy cancel out, the answer is 1. And this guy is finite and positive, right? So then, by the limit comparison test, either a sub n and b sub n converge or diverge, right? Now we're going to check this guy. So it's going to be sigma when n goes from 0 to infinity of 1 over 3 to the n. It's going to be sigma when n goes from 0 to infinity of 1 over 3 altogether to the n. And this guy actually geometric series, right? Where the ratio equals 1 over 3 less than 1, right? And then this geometric series converges, right? Then the original one right here must converge, right? Now let's move on to question D. So we have a sub n equals 4n squared plus n over cube root of n to the 7 plus n cube, right? Now observe that the top is the polynomial function. The bottom still the polynomial function under the radical sign. So they both behave in the same way as the largest power, right? So the largest power right here is 7. The largest power right here is 2, right? So this guy is the same thing as n squared over cube root of n to the 7, right? So I'm gonna rewrite this one as n squared over n to the 7 over 3, right? So I'm gonna simplify this one. It's gonna be 1 over n 1 over 3, right? And I call this one as b sub n, right? So I'm gonna check limit when n approaches infinity of a sub n over b sub n, right? So it's going to be limit of 4n squared plus n over cube root of n to the 7 plus n cube over 1 over n to the 1/3 when n approaches infinity, right? Now I'm going to multiply the top bottom by n to the 1/3. So it could be, now I'm going to multiply this guy by n to the 1/3. So I'm going to end up with, now I'm going to factor n to the 7 out. So it's going to be, now I'm going to factor n to the 7 over 3 out. So I have limit when n approaches infinity, n to the 7/3. It's going to be 4 plus 1 over n, right? I'm going to bring n to the 7 out, so it's going to be n to the 7 over 3, right? Don't forget the cube root right here. Times cube root of 1 plus 1 over n to the 4, right? Now this guy right here and this guy right here cancel out, right? So when n approaches infinity, this guy approaches 0, this guy approaches 0, it's going to be 4. This guy actually a positive and finite number L, right? So by the limit comparison test, either both of them converge or diverge, right? Now, I'm going to check to see if this guy converges or diverges, right? So this guy actually the P series, right? Where P equals 1 over 3 less than 1. So this series diverges, right? By the P series test. If this guy diverges, the original one right here must diverge. We're gonna learn how to prove the alternating series test theorem. Let the series b sub n greater than or equal to 0 for all n. The alternating series a sub n where a sub n equals negative 1 to the n times b sub n, or a sub n equals negative 1 to the n plus 1 times b sub n converge if limit of b sub n when n approaches infinity equals 0. The sequence b sub n is a decreasing sequence. What does it mean? It means b sub n always greater than or equal to b sub n plus 1 for all n greater than k, where k is an integer. Alright, so this one is given, right? And we need to prove that this guy right here converges, right? So we're gonna start off with this one right here, right? So we have b sub n greater than or equal to b sub n plus 1. It tells us that b sub n minus b sub n plus 1 greater than or equal to 0, right? So now I'm gonna let s sub 2 equals b sub 1 minus b sub 2, right? N equals 1, you have b sub 1 minus b sub 2, right? And this guy actually greater than or equal to 0, right? Now s sub 4 equals b sub 1 minus b sub 2 plus b sub 3 minus b sub 4, right? And I can replace this guy right here with this guy, right? So it's going to be s sub 2 plus b sub 3 minus b sub 4, right? And this guy actually greater than or equal to s sub 2, right? Now next one, s sub 6 equals s sub 4 plus b sub 5 minus b sub 6, right? And this guy actually greater than or equal to s sub 4, right? Now I'm going to generalize this one, so I have s sub 2 and it's going to be equal to s sub 2 n minus 2 plus b sub 2 n minus 1 minus b sub 2 n, right? This guy actually greater than or equal to s sub 2 n minus 2, right? So we just prove that s sub 2 n greater than or equal to s sub 2 n minus 2. This guy tells us that s sub 2 n is an increasing sequence. Now I'm gonna rewrite s sub 2 n equals, right? I'm gonna combine all of these guys right here, right? So it's gonna be b sub 1 minus b sub 2 plus b sub 3 minus b sub 4 plus b sub 5 minus etc. minus b sub 2 n minus 2 plus b sub 2 n minus 1 minus b sub 2 n, right? Now this guy turns out to be b sub 1. Now I'm gonna group this guy and this guy, this guy and this guy, right? This guy and this guy. So it turns out to be minus b sub 2 minus b sub 3, right? Minus b sub 4 minus b sub 5, etc. Minus b sub 2 n minus 2 subtract b sub 2 n minus 1, right? And minus b sub 2 n, right? You know that this guy always greater than or equal to 0, right? Look, right? This guy and this guy right here, right? So then S sub 2 and big one subtract a positive number. It tells us that S sub 2n is always less than or equal to B sub 1, right? For all n. And we're gonna combine this guy together. It tells us that S sub 2n must converge, right? In other words, limit of S sub 2n when n approaches infinity equals L, right? Now, if you do exactly the same thing for the odd partial sums, S sub 2n plus 1, right? You're gonna end up with limit of S sub 2n plus 1 when n approaches infinity equals limit of S sub 2n plus B sub 2n plus 1 when n approaches infinity equals limit of S sub 2n when n approaches infinity plus limit of B sub 2n plus 1 when n approaches infinity, right? Now, this guy right here equals 0, right? If you look at this one right here, right? So then you're gonna end up with limit of S sub 2n when n approaches infinity equals L is to be right here, right? So we just prove that S sub 2n and S sub 2n plus 1 converge. And limit of S sub 2n when n approaches infinity equals limit of S sub 2n plus 1 when n approaches infinity equals L, right? These two guys tells us that the series A sub n is convergent. By the definition of infinite series you learn in topic 10.1, right? We're going to explore the alternating series test for convergence. Alright, previously we only deal with most series that have positive terms. In this session, we're going to deal with the series that has both positive and negative terms. That's called alternating series. Alright, so we look at the definition right here. An alternating series is a series either of the form this guy or this guy. For the first one, if n equals 1, we substitute over here, we have the power of 2, right? So negative 1 power of 2 is going to be 1. 1 times a sub n is going to be a sub n. So the first term is going to be positive, right? The second term, this one becomes odd number, right? So the negative 1 raised to the odd number is going to be negative, right? So the second term is going to be negative, etc. Alright, third term is positive, the fourth term is negative. Or you're going to see this guy right here, only power of n, right? The first terms become negative, right? The second terms becomes positive, right? Where a sub n positive for all integers n greater than or equal to 1, right? We're gonna look at the theorem alternating series test. Let b sub n greater than or equal to 0 for all n. The alternate series a sub n where a sub n equals negative 1 to the n times b sub n, or a sub n equals negative 1 raised to the n plus 1 times b sub n. Converge if the limit of b sub n approaches 0 when n approaches infinity. Number 2, the sequence b sub n is a decreasing sequence. What does that mean? It means b sub n greater than or equal to b sub n plus 1 for all n greater than k, where k is an integer, right? Now, for the proof of this theorem, you're going to check it out in the videos 10.7a. Now, example number 1. Determine if the following series converge by the alternating series test. Alright, so we look at the theorem right here. We need to verify number 1 and number 2 right here, right? So we're gonna let this one right here be b sub n, right? And the whole thing right here, I call this a sub n equals the whole thing, right? Now, number 1, we need to verify limit of b sub n when n approaches infinity equals 0, right? So we have limit of 1 over n when n approaches infinity equals 0. So this one satisfies, right? Now number 2, we're gonna verify this guy right here, right? So I have n plus 1 greater than n, right? Now I'm gonna take reciprocal both sides, so I have 1 over n plus 1 less than 1 over n, right? So it's the same thing as b sub n greater than or equal to b sub n plus 1, right? Number 2 right here satisfies, right? So from these two guys right here, we can conclude that the series a sub n converges, right? By the alternating series test. Now on the AP exam, you must write this one out. Alright, so keep that in mind. Now question B. I'm gonna let the whole thing right here be a sub n, right? And then this guy right here, I'm gonna let this one be b sub n equals n over n plus 1, right? Now I need to verify number 1 right here, right? So I'm gonna take limit of n over n plus 1 when n approaches infinity. It's gonna be limit of n over n when n approaches infinity, right? Because number 1 right here doesn't really matter, right? So I'm gonna simplify this one. It's gonna be 1. This one not equal to 0, right? So you're gonna say that the alternating series test is inconclusive, right? To verify non-increasing behavior for a sequence. Number 1, you can use algebraic difference test to show that a sub n plus 1 minus a sub n less than or equal to 0, right? This guy tells us that a sub n always greater than or equal to a sub n plus 1, right? Now, number 2, you can use algebraic ratio test to show that a sub n plus 1 over a sub n less than or equal to 1. This one also tells us that a sub n always greater than or equal to a sub n plus 1, right? Now, number 2, you can use the derivative of the related function f of s, for which a sub n equals f of n for all n defined for s greater than 0, shows that the first derivative less than or equal to 0 for all n greater than k for some k in the integer set, right? Now, example number 2, determine if the following alternating series converge or diverge, right? So I'm gonna let the whole thing right here be a sub n, right? And I'm gonna let b sub n equals 1 over 2 and altogether factorial, right? First, I need to verify if limit of b sub n when n approaches infinity equals 0, right? But b sub n equals 1 over 2 and altogether factorial, right? This one equals 0, right? Now, number 2, we're gonna use the second one right here to do it, right? We're gonna have b sub n plus 1 over b sub n. It's gonna be 1 over 2 times n plus 1 factorial over 1 over 2 times n factorial. Now I'm going to multiply the top bottom by 2n factorial. So I'm going to end up with 2n factorial over 2 times n plus 1 factorial, right? Now I'm going to distribute the bottom, so it's going to be 2n factorial over 2n plus 2 factorial, right? So look at the bottom. It's going to be 2 units greater than the top, right? So I just write 2n factorial over 2n factorial times 2n plus 1 times 2n plus 2, right? And then this guy cancel out. It's going to be 1 over 2n plus 1 times 2n plus 2, right? And look at the bottom right here. It's going to be always greater than 1, right? So then this guy always less than 1, right? So this one tells us that b sub n is decreasing, right? So by the alternating series test, this series converges, right? Now, question B. I'm going to let this one be a sub n, right? And then b sub n equals n squared over n squared plus 25, right? Now, I'm going to go back to the alternating series test, right? I need to verify two things, right? It's going to be right here, right? So, I'm going to check to see if limit of b sub n when n approaches infinity equals 0 or not, right? So I'm going to have limit of n squared over n squared plus 25 when n approaches infinity. It's going to be limit of n squared over n squared when n approaches infinity, right? By relative growth rate, when n approaches infinity, 25 doesn't really matter, right? So I can drop 25, right? So if I simplify this, could be 1, different from 0, right? Now, the first condition is not met. There's no reason for me to check the second one, right? So I can conclude that a sub n is not convergent by the alternating series test, right? Now, you need to read the question carefully. The question says, determine if the following alternating series converge or diverge, right? It doesn't say that you need to use the alternating series test, right? This question different from example number 1 right here. It says, determine if the following series converge by the alternating series test. So they make you use this theorem, right? But example number 2 right here, you can use whatever theorem to verify if this alternating series converge or diverge, right? So you're not gonna stop right here. You need to do more, right? So I look at this one. I can use the n-term test. That's called divergent test. We're gonna take the limit of a sub n right here, right? So we have limit of a sub n when n approaches infinity equals limit of -1 to the n times n squared over n squared plus 25 when n approaches infinity. Now observe that this limit always equals 1, right? And then this limit right here is going to be alternating between 1 and -1, right? So obviously this limit does not exist, right? It's the same thing as limit of a sub n when n approaches infinity diverges, right? By the n-terms test. Now, let's move on to question C. I'm gonna let the whole thing right here be a sub n. And then b sub n equals square root of n over n plus 4, right? Now I'm gonna check the first one to see if limit of b sub n when n approaches infinity equals 0 or not, right? So I'm gonna take limit of square root of n over n plus 4 when n approaches infinity equals limit of n power of 1/2 over n when n approaches infinity, right? I can drop for by relative growth rate, right? So this one is the same thing as limit of 1 over n power of 1/2 when n approaches infinity. So it could be 0, right? So the first one is met. Now the second one, I'm gonna let f of s equals square root of s over s plus 4, right? I'm gonna use the third one right here to verify if the function is decreasing, right? Now I'm gonna check the derivative of this one using the quotient rule, right? So I have u over v prime is to be u prime v minus v prime u over v squared, right? So it's gonna be 1 over 2 square root of s, right? Times s plus 4 minus 1 times square root of s over s plus 4 altogether square, right? So it's gonna be 1 over 2 square root of s times s plus 4 altogether square. Now I can put 4 minus s on the top. So in order to use the alternating series test, I need this guy to be less than or equal to 0, right? Now I need to find the critical numbers. So the critical numbers are s equals 0, so s equals 4, right? The bottom right here, square root of s equals 0, s equals 0, right? S plus 4 equals 0, s equals negative 4, right? But you need to be careful. You need to eliminate this one. Why? Because s for negative 4 makes the original one right here undefined, right? So we only have two critical numbers, right? We're going to draw the number line, right? So we're going to put 0 here, 4 here, right? Now we're going to pick a value within this interval. So suppose I pick 1, right? I substitute 1 for s back over here, right? So 4 minus 1 is going to be 3. The bottom is positive. So this one positive, right? So I have the plus side right here. If this guy plus side, this guy must be negative. This guy must be negative, right? Now I need this guy to be less than or equal to 0, right? So I'm going to conclude that f prime of s less than or equal to 0 when s less than or equal to 0, right? This guy right here. Or s greater than or equal to 4, right? Now we're going to go back to original series. We're going to replace s with n, right? So we have f prime n less than or equal to 0. If n less than or equal to 0 or n greater than or equal to 4, right? S must be greater than 0, right? For some n greater than k, right? So we can eliminate this guy right here. We only take this guy, right? So b sub n is decreasing on 4 to infinity, right? This guy right here. So the second one is met, right? The first one is met. So by the alternating series test, a sub n converges, right? Now let's move on to question D. Question D is interesting. Why? Because you don't have -1 to the n or -1 to the n plus 1, right? So in order to use the alternating series test, you need these two guys, right? But this guy right here is hidden. Why? Look at this one right here. We know that cosine of pi equals -1, right? Cosine of 2 pi equals 1. Cosine of 3 pi equals -1. Cosine of 4 pi equals 1. Cosine of 0 equals 1. Alright, so technically cosine of n pi actually -1 power n, right? If n is even, it's gonna be positive. If n is odd, it's gonna be negative, right? So this series can be written as sigma when n equals to infinity of -1 to the n over square root of n, right? I'm gonna let this one be a sub n, right? And I'm gonna let b sub n be 1 over square root of n, right? Now I'm gonna check two conditions, right? The first condition, I'm gonna take the limit of b sub n when n approaches infinity. It's gonna be limit of 1 over square root of n when n approaches infinity, and this guy actually 0, right? So the first one met. Now the second condition, I have square root of n less than square root of n plus 1, right? I take reciprocal both sides, so I have 1 over square root of n greater than 1 over square root of n plus 1, right? And this guy actually b sub n, right? And this guy actually b sub n plus 1, right? So you just prove that b sub n greater than b sub n plus 1, right? So the second condition is met. So by the alternating series test, the series converges, right? We're going to explore topic 10.8, ratio test and root test for convergence. Alright, now we're going to talk about the ratio test theorem. Let a sub n be a series with non-zero terms such that limit of absolute value of a sub n plus 1 over a sub n when n approaches infinity equals a constant L. Now, if L less than 1, then the series converges absolutely. Hence, it converges. Number 2, if L greater than 1 or L equals infinity, then the series diverges. Now, number 3, if L equals 1, then the ratio test is inconclusive. The series may be divergent, conditionally convergent, or absolutely convergent. Now, let's take a look at the first example using the ratio test only. Determine the convergence or divergence of the following series. Question A. I'm gonna let a sub n equals 2 to the n over n factorial, right? And then a sub n plus 1 equals 2 to the n plus 1 over n plus 1 factorial, right? Now I'm gonna set up this guy, right? So I have limit of absolute value of a sub n plus 1, which means 2 to the n plus 1 over n plus 1 factorial divided by 2 to the n over n factorial, right? When n approaches infinity, right? Now this guy is the same thing as limit when n approaches infinity. I just take reciprocal of this one, right? So it can be absolute value of 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n, right? Now I'm going to simplify this guy. So this guy turns out to be 2 to the n plus 1 and 2 to the n right here is going to be 2 on the top, right? N plus 1 factorial and n factorial right here. You have n plus 1 on the bottom, right? Now when n approaches infinity, this guy approaches 0, right? 0 is less than 1, right? Now we look at the theorem right here. L less than 1. The series converges, right? So we're going to say that the series A sub n converges by the ratio test. Now question B, I do exactly the same thing, right? So I'm going to let A sub n be n squared times 2 to the n plus 1 over 3 to the n, and A sub n plus 1 equals n plus 1 squared times 2 to the n plus 2 over 3 to the n plus 1, right? Now I'm going to set up the limit, right? A sub n plus 1 over A sub n, right? Alright, now I'm going to check reciprocal of this one, so it turns out to be n plus 1 square, I rewrite it. 2 to the n plus 2 and 2 to the n plus 1, I have 2 on the top, right? 3 to the n and 3 to the n plus 1 here cancel out, right? So the bottom should be n squared times 3, right? Now by relative growth rate, we have limit when n approaches infinity of 2 times n squared over 3 times n squared, right? Because n right here grows faster than 1, right? So I can cancel out this guy, so the answer must be 2 over 3, right? This guy less than 1, right? So by the ratio test, the series converges, right? Now question C, I do exactly the same thing, right? So I'm going to let A sub n equals n to the n over n factorial. A sub n plus 1 equals n plus 1 to the n plus 1 over n plus 1 factorial, right? Now I'm going to set up the limit, right? So I have limit of A sub n plus 1 over A sub n is going to be, so this guy turns out to be A sub n plus 1 times the reciprocal of A sub n, right? Alright, so this guy turns out to be limit when n approaches infinity of, I just rewrite this guy and this guy, so it could be n plus 1 to the n plus 1 over n to the n, right? Now this guy cancel out, I have n plus 1 on the bottom, right? So this guy turns out to be limit when n approaches infinity of n plus 1 to the n, right? Because n plus 1 to the n plus 1 is going to be n plus 1 to the n times n plus 1, and n plus 1 cancel out with this one, so you only have n plus 1 to the n left, right? Over n to the n, right? So this guy turns out to be limit of n plus 1 over n all together to the n, right? When n approaches infinity, right? So it's going to be limit when n approaches infinity of n divided by n is going to be 1 plus 1 over n all together power of n. And then this guy actually equals e, greater than 1, right? Now, if you want to know why this one equals e, please check out the proof in the description below. Now, by the ratio theorem, it's gonna be diverges, right? Now let's move on to question D. I'm gonna let a sub n be negative 1 altogether raised to the n square root of n over n plus 1, and a sub n plus 1 equals negative 1 altogether raised to the n plus 1 square root of n plus 1 over n plus 1 is going to be n plus 2, right? Now I'm going to check the limit when n approaches infinity of absolute value of a sub n plus 1 over a sub n, right? So it could be negative 1 raised to the n plus 1 square root of n plus 1 over n plus 2 times reciprocal of this one is going to be n plus 1 over negative 1 to the n square root of n, right? And then it's going to be negative 1 to the n plus 1 is going to be negative 1 to the n times negative 1, right? So this guy cancel out, right? Now you have negative 1 left right here. So when you check absolute value, it's going to be positive, right? So I don't really worry about this guy, right? So I'm going to end up with limit when n approaches infinity of square root of n plus 1 times n plus 1 over n plus 2 times square root of n, put the absolute value side, right? This guy is the same thing as limit when n approaches infinity of absolute value of n plus 1 times square root of n plus 1 is going to be n plus 1 power of 3.5, right? Over this guy right here, when n approaches infinity, number 2 doesn't really matter, right? So I only have n square root of n. It's going to be n power of 3.5, right? And when n approaches infinity, number 1 right here doesn't really matter, right? So I have limit of absolute value of n power of 3.5 over n power of 3.5 when n approaches infinity, and it's going to be 1, right? So by the ratio test, this series is inconclusive, right? Now let's move on to question E. So I'm going to let a sub n equals n factorial over 5 to the n, and a sub n plus 1 equals n plus 1 factorial over 5 to the n plus 1, right? So I'm going to set up the limit when n approaches infinity of absolute value of a sub n plus 1 over a sub n, right? So it's going to be limit when n approaches infinity of absolute value of this guy cancel out, so you have n plus 1 on the top, right? This guy cancel out, so you have 5 on the bottom, right? So when n approaches infinity, this guy approaches infinity, right? So by the ratio test, this guy divergent, right? Now question F, I'm gonna let a sub n equals n squared over 2n minus 1 factorial, right? And I have a sub n plus 1 equals n plus 1 squared over 2 parentheses n plus 1 minus 1 altogether factorial, right? You need to be careful with the bottom right here. Alright, so I'm going to simplify this one, so it's going to be n plus 1 altogether square, right? Over 2n plus 1 altogether factorial, right? So I'm going to set up the limit, right? Now observe that 2n plus 1 factorial equals 2n plus 1 times 2n times 2n minus 1 factorial, right? So keep this one in mind. Now, so I can simplify this guy and this guy. So it's going to be limit when n approaches infinity of absolute value of n plus 1 altogether square, right? over, I have this guy left right here, right? So 2n plus 1 times 2n times n squared, right? Now observe that the highest exponent on the top is 2, right? And the highest exponent on the bottom is 4, right? This is 1, this is 1, and this is 2. When you multiply, it's going to be 4, right? So then, when n approaches infinity, this guy approaches 0 less than 1, right? So by the ratio test, this series converges, right? Now let's move on to question G. I'm going to let a sub n be 9 to the n over negative 2 to the n plus 1 times n, right? And a sub n plus 1 equals 9 to the n plus 1 over negative 2 to the n plus 2 times n plus 1, right? So I'm going to set up the limits, right? So I have limit when n approaches infinity of absolute value of. So if you simplify, it's going to be limit when n approaches infinity, right? 9 to the n plus 1, and this one cancel out, you have 9 on the top, right? This guy cancel out, you have negative 2 to the first on the bottom, right? The top you have n left, so I write n right here. The bottom you have n plus 1 left, right? Absolute value. And then this guy turns out to be limit when n approaches infinity. Absolute value of negative 2 equals 2. So it's going to be absolute value of 9 over 2. The top is n, the bottom is n, right? And then you can cancel out n, so it could be 9 over 2 greater than 1, right? So by the ratio test, this series diverges, right? Now let's move on to question H. I'm going to let a sub n be negative 1 to the n over n squared plus 1, and a sub n plus 1 equals negative 1 altogether to the n plus 1 over n plus 1 altogether square plus 1, right? So I'm going to set up the limit. Now I'm going to simplify this one, so it's going to be limit when n approaches infinity of absolute value of. This guy cancel out, so you have negative 1 raised to the first on the top, right? Times n squared plus 1 over n plus 1 altogether square plus 1, right? Now, absolute value of negative 1 equals 1, so it could be limit of absolute value of n squared plus 1 over n plus 1 altogether square plus 1 when n approaches infinity. Now, when n approaches infinity, number one right here and number 1 right here doesn't really matter, right? So I can drop all number 1s there, so it could be limit when n approaches infinity of absolute value of n squared over n squared, right? So it could be 1, right? So by the ratio test, the series is inconclusive, right? Now, if the question wants to use only the ratio test to determine the convergence or divergence of this series, you stop right here. But if the question doesn't say anything, so you're not going to stop right here. You need to use different tests to determine the convergence or divergence of this series, right? So we can use alternating series tests, and then this series converges. I'm going to leave this one for you to practice. Now, question G. I'm going to let a sub n equals n plus 2 over 2n plus 7, and a sub n plus 1 equals n plus 1 plus 2 over 2 times n plus 1 plus 7, right? Now I need to simplify this one, so it could be a sub n plus 1 equals n plus 3 over 2n plus 9, right? Now I'm going to set up the limit when n approaches infinity of absolute value of n plus 3 over 2n plus 9 times reciprocal of this one 2n plus 7 over n plus 2, right? So when n approaches infinity, the constant right here don't really matter, right? So I'm gonna drop all constant right here. So this guy turns out to be limit when n approaches infinity of absolute value of n times 2n, right? This guy right here times this guy over 2n right here times n right here, right? So it's gonna be 1, right? By the ratio test, this series is inconclusive, right? Alright, question G similar to question F. If the question just wants you to use the ratio test, you stop right here. But if the question doesn't say anything, you need to use different tests to determine if this series converges or diverges, right? So in this situation, by using the n-term test or divergent test, this series divergence. I'm going to leave this one for you to practice. Now let's move on to question H. I'm going to let a sub n be negative 10 to the n over 4 to the 2n plus 1 times n plus 1, right? Now a sub n plus 1 equals negative 10 to the n plus 1 over 4 to the 2 times n plus 1 times n plus 1 is going to be n plus 2, right? Now I'm going to simplify this one, so this guy turns out to be a sub n plus 1 equals negative 10 to the n plus 1 over 4 to the 2n plus 3, right? Times n plus 2. Now I'm going to set up the limit, right? So I'm going to simplify this one, so it could be limit when n approaches infinity of absolute value of this guy cancel out, so you have negative 10 to the first on the top, right? The top still have n plus 1, right? The bottom still have n plus 2, right? Now 4 to the 2n plus 3 and 4 to the 2n plus 1 is going to be 4 squared left, right? Absolute value of negative 10 equals 10, right? So 10 over 16, right? Because when n approaches infinity, number 1, number 2 doesn't really matter, so I can cancel out this guy, right? So n and n left right here, I can cancel out, so the answer should be 10 over 16, right? This guy less than 1, right? So by the ratio test, the series converges, right? Now let's move on to the next one, strategies for testing series. A recap of unit 10.1 to 10.8. Alright, so here's the guideline. First, you're gonna check to see if the n-term test works, right? Next, you're gonna check to see if you have the geometric series, P series, telescoping series, alternating series. Those are the special types, right? Third, you're going to check the integral test, ratio test, and root test. And next, you're going to check to see if the series compare favorably to one of the special types. Alright, let's take a look at example number 2. You can apply any series test, right? Determine the convergence or divergence of the following series using the strategies you learned so far. Based on instruction right here, I need to use the n-term test first, right? N-term test, in other words, that is the divergence test, right? So I'm going to let a sub n be n plus 1 over 3n plus 1, right? So I'm going to check the limit of a sub n when n approaches infinity. It's going to be limit of n plus 1 over 3n plus 1 when n approaches infinity. It's going to be limit of n over 3n when n approaches infinity, right? Because when n approaches infinity, 1 and 1 right here doesn't really matter, right? So I can cancel out n, so it could be 1 over 3, right? This guy not equal to 0, right? So by the n-term test, this series diverges, right? Question B. Observe that this one is the geometric series where the common ratio equals pi over 6 less than 1. So the series converges, right? Now question C. You can use the ratio test or integral test. Let a sub n be n times e to the negative n squared. So it's going to be n over e to the n squared, right? Then a sub n plus 1 equals n plus 1 altogether over e to the n plus 1 altogether squared, right? So I'm going to set up the limit when n approaches infinity of a sub n plus 1 over a sub n, right? Alright, so this guy turns out to be limit of absolute value of n plus 1 over n times absolute value of e to the n squared over e to the, I'm going to distribute this one using the complete square formulas, right? So it could be n squared plus 2n plus 1, right? When n approaches infinity, right? Now, when n approaches infinity, this guy doesn't really matter, right? So I can ignore this using the relative growth rate, right? So n divided by n is going to be 1, so this one equals 1, right? So I'm going to end up with limit when n approaches infinity of absolute value of the second one right here, e to the n squared over e to the n squared times e to the 2n plus 1, right? And then this guy cancel out, so it could be limit when n approaches infinity of 1 over e to the 2n plus 1, right? When n approaches infinity, the bottom approaches infinity, this y equals 0, right? Less than 1. So by the ratio test, this series convergence, right? Now question D. I'm going to let a sub n be 1 over 3n plus 1, right? B sub n equals 1 over n. I'm going to use the limit comparison test. So I'm going to take the limit of a sub n over b sub n, right? When n approaches infinity. So it's going to be limit of absolute value of 1 over 3n plus 1 times reciprocal of this one is going to be n over 1, right? When n approaches infinity, so it could be limit absolute value of n over 3n plus 1 when n approaches infinity. Now when n approaches infinity, number 1 right here doesn't really matter, right? So it could be limit of n over 3n when n approaches infinity. N and n cancel out, so it could be 1/3, right? 1/3 right here is positive and finite, right? So by the limit comparison test, both of this one either converge or diverge, right? So I'm gonna check this guy right here, right? So b sub n equals 1 over n is divergent by the harmonic series test, right? Or you can use the p series where p equals 1 less than or equal to 1. So by the p series, this one divergence, right? Finally, you have the series a sub n diverges. Now let's move on to question E. We see that we have the negative 1 to the n, so think about the alternating series test, right? So I'm going to let a sub n be negative 1 to the n times 3 over 4n plus 1, right? And b sub n equals 3 over 4n plus 1, right? Now, I'm going to check the limit of b sub n when n approaches infinity, right? So it's going to be limit of 3 over 4n plus 1 when n approaches infinity, right? This guy actually 0, right? So the first condition is met. Now the second one, you need to prove that this guy decreasing, right? So I'm going to let b sub n plus 1 equals 3 over 4 times n plus 1 plus 1, right? So I need to prove that b sub n plus 1 over b sub n less than 1, right? So I have 3 over 4 n plus 1 plus 1, right? Divide by b sub n, I'm going to multiply by its reciprocal. So it can be 4n plus 1 over 3, right? So then 3 and 3 right here cancel out, right? Now the bottom right here I simplify, so I have 4n plus 1 over 4n plus 5, right? And of course, the top is less than the bottom. This guy less than 1, right? So then it tells us that b sub n decreasing, right? So the second condition is met, right? So by alternating series tests, a sub n converges, right? We're gonna let a sub n be n factorial over 10 to the n, right? Now we're gonna check the limit of this one. So we have limit of a sub n, which means n factorial over 10 to the n when n approaches infinity, right? Now observe that the factorial function always grows faster than the exponential function, right? So then this guy equals infinity, right? So by the n-term test, this series divergent, right? Now question G, we're going to use the limit comparison test. So we're going to let a sub n be n plus 1 over 2n plus 1 all together to the n, right? And b sub n equals 1 over 2 all together to the n, right? Now we're going to check the limit of a sub n over b sub n when n approaches infinity. It's going to be limit of n plus 1 over 2n plus 1 all together to the n when n approaches infinity times reciprocal of this one is going to be 2 to the n over 1, right? Alright, so this guy turns out to be limit of absolute value of 2 times n plus 1 over 2n plus 1 all together to the n when n approaches infinity, right? Now I'm going to simplify this one, so it's going to be limit when n approaches infinity of, I'm going to distribute this one, so then it's going to be 2n plus 1 plus 1 over 2n plus 1, right? All together to the n absolute value. So it could be limit when n approaches infinity, absolute value of 2n plus 1 divided by 2n plus 1 is going to be 1 plus 1 over 2n plus 1 raised to the n, right? Now we have the formula definition of Euler number. It's going to be limit of 1 plus 1 over n all together raised to the n equals e when n approaches infinity. Alright, I will prove this one in another video. Please check out the link in the description below. Or you can go to my website. The video is right here. Right? Now, to apply this formula, you need to rewrite that this guy and this guy must be the same, right? So in order to do that, I'm going to rewrite this one as limit when n approaches infinity of 1 plus 1 over 2n plus 1, right? Right to the 2n plus 1, right? Look, formula right here. Absolute value of n over 2n plus 1, right? So then this guy cancel out. Let's go back to original one right here, right? So this guy right here turns out to be e, right? And then limit of n over 2n plus 1 when n approaches infinity. Number 1 doesn't really matter, so it could be n over 2n, right? And you cancel out n and n, so it could be 1/2. So the final answer is e to the 1/2, right? And this number is positive and finite, right? So by the limit comparison test, both of this one converge or diverge, right? Now I'm going to check b sub n right here. So I have b sub n equals 1 over 2 to the n, right? And this could be 1 over 2 altogether to the n. And this guy actually the geometric series where the common ratio equals 1/2 less than 1. And then by the geometric series, b sub n converges, right? A sub n must converge. The second way that is easier to do this problem is to use the root test. Alright, so you're gonna let a sub n equals n plus 1 over 2n plus 1 all together to the n. Now you're gonna take n root both sides, so you have n root of a sub n equals n plus 1 over 2n plus 1, right? Now you're going to take the limit of this one. So I have limit of n root of absolute value of a sub n equals limit of absolute value of n plus 1 over 2n plus 1 when n approaches infinity, right? So then you can drop 1, right? So it could be limit of absolute value of n over 2n when n approaches infinity, and it could be 1/2, right? Less than 1, right? So by the root test, the series converges, right? Now let's move on to the last question. This guy actually is example number 1D, right? So we just prove above by using the ratio test. This series is inconclusive, right? Now we're going to use different tests to determine if this one convergent or divergence, right? So I'm going to use the alternating series test. So I'm going to let a sub n equals -1 raised to the n square root of n over n plus 1, right? And b sub n is going to be square root of n over n plus 1, right? Now I'm going to check the limit of b sub n when n approaches infinity. It's going to be the limit when n approaches infinity of square root of n over n plus 1, right? So then you have limit of square root of n over n when n approaches infinity, right? Because number 1 doesn't really matter. So this guy turns out to be limit of 1 over n to the 1/2 when n approaches infinity, and this guy equals 0, right? So the first condition is met. Now I'm going to check the second condition. I need to prove that this guy right here decreasing, right? So I'm going to use the function f of s equals square root of s over s plus 1, right? The condition is s must be greater than 0, right? So I'm going to check the derivative of this one. I'm going to use the quotient rule, right? Square root of s is going to be 1 over 2 square root of s times s plus 1, right? So 1 times s plus 1 is going to be right here. Subtract. Derivative of the bottom is going to be 1 times square root of s over s plus 1 all together square, right? And then I multiply this one by this guy, and then I bring this one down, right? So it's going to be s plus 1 minus 2s over 2 square root of s times s plus 1 all together square, right? So it's going to be negative s over 2 square root of s times s plus 1 all together square, right? The bottom always greater than 0. The top always less than 0 because s greater than 0, right? So you can say that f prime of s less than 0, and then f of s is decreasing, right? If this guy decreasing, and then the series right here, b sub n is decreasing. So the second condition is met, right? So by the alternating series test, a sub n converges. We're going to explore the topic 10.8b, the root test for convergence or divergence of the series. Alright, let's take a look at the theorem right here. Let a sub n be a series such that limit of n root of absolute value of a sub n when n approaches infinity equals limit of absolute value of a sub n raised to the 1 over n when n approaches infinity equals L. Now, we know the fact that limit of n raised to the 1 over n when n approaches infinity equals 1, right? Now, number 1, if L less than 1, then the series converges. Number 2, if L greater than 1 or L equals infinity, the series diverges. Number 3, if L equals 1, the root test is inconclusive. Right? You may use other tests to test for the convergence or divergence of the series. Right? Now, keep in mind, the root test is not tested on the AP Calculus BC exam. However, knowing this test is extremely helpful, especially for the series involving the n powers. Right? So if you look at the problem right here, now, if you don't know the root test, you would have to use the limit comparison test, and it's extremely cumbersome and time consuming. Alright, now in the last video, I'm going to use the limit comparison test for this series, right? Now I'm going to use the root test for this series, so it's extremely easy, right? So I'm going to let a sub n be n plus 1 over 2n plus 1 all together raised to the n, right? So I'm going to take n root both sides, right? So it's going to be n plus 1 over 2n plus 1, right? Now I'm going to take the limit of n root of absolute value of a sub n when n approaches infinity equals limit of n plus 1 over 2n plus 1 when n approaches infinity, right? And when n approaches infinity, this guy and this guy doesn't really matter, right? So I can ignore them, right? So limit of n over 2 and when n approaches infinity, and it's going to be 1/2, right? Now 1/2 is less than 1, right? So by the root test, the series converges, right? Now let's take a look at example number 3. Using the root test, question A. We're gonna let a sub n be e to the 2n over n to the n, right? And then I'm gonna take n root both sides, right? So it's gonna be n root of e squared over n all together to the n, right? So this guy turns out to be e squared over n, right? Now I'm going to take the limit of n root of absolute value of a sub n. When n approaches infinity, it's going to be limit of e squared over n when n approaches infinity, right? So this guy equals 0, right? Less than 1. By the root test, the series converges, right? Now question B. I'm going to let a sub n be n to the n over 3 to the 2n plus 1. I'm going to take n root both sides, so it's going to be n root of a sub n equals n to the n over 3 to the 2n plus 1 altogether power of 1 over n, right? Now this guy turns out to be, this guy and this guy cancel out, so it's going to be n over, I'm going to distribute the power of 1 over n, right? So 2n times 1 over n is going to be 3 power of 2, right? Plus 1 over n, right? Now I'm going to take the limit of n root of absolute value of a sub n when n approaches infinity equals limit of absolute value of n over 3 raised to the 2 plus 1 over n when n approaches infinity, right? So the top approaches infinity, the bottom approaches 3 squared, right? So it could be infinity, right? Now we look at this one right here. The series diverges by the root test, right? Now question C. I'm going to let a sub n be 5n minus 3n cubed over 7n cubed plus 2 altogether raised to the n, right? Now I'm going to take n root both sides, right? So I have n root of a sub n equals 5n minus 3n cubed over 7n cubed plus 2, right? So I'm going to take the limit of n root of absolute value of a sub n when n approaches infinity equals limit of absolute value of 5n minus 3n cubed over 7n cubed plus 2 when n approaches infinity, right? Now when n approaches infinity, this guy doesn't really matter, right? This guy doesn't really matter, right? So it's going to be limit of absolute value of negative 3n cubed over 7n cubed when n approaches infinity, right? So it's going to be this guy and this guy cancel out. It's going to be 3 over 7 less than 1, right? So we look at this one right here. By the root test, the series converges, right? Now let's move on to the last one. Let a sub n be negative 12 to the n over n, right? Now we're gonna take n root both sides. So we have n root of a sub n equals negative 12 altogether raised to the n over n raised to the 1 over n, right? So I'm going to take the limit of n root of absolute value of a sub n when n approaches infinity equals limit of negative 12 to the n over n raised to the 1 over n when n approaches infinity, right? So I'm going to distribute power of 1 over n, right? So I have limit of negative 12 over n raised to the 1 over n when n approaches infinity, right? And then it's going to be limit of absolute value of negative 12 is going to be 12, right? Over n raised to the 1 over n when n approaches infinity, right? Now we look at the formula right here. Limit of n raised to the 1 over n when n approaches infinity equals 1, right? So the bottom 1 right here equals 1. The top equals 12, so 12 over 1. And it's going to be 12 greater than 1. By the root test, the series diverges, right? We're going to explore topic 10.9, determining absolute or conditional convergence. Alright, when analyzing the convergence or divergence of a series A sub n, there are three possible cases. Case number 1, the series converges absolutely. How do we do it? We're going to check the series absolute value of A sub n to see if it converges. If it converges, then the original series also converges. Case number 2, converges conditionally. If the series of absolute value of A sub n diverges, but the original series A sub n converges, then the original series A sub n is said to converge conditionally. Number 3, diverges. If both series absolute value of A sub n and original A sub n diverge, then original A sub n diverges. Now note that the converse of the first case right here is not true. That said, the statement say if the series A sub n converges, then the series absolute value of A sub n also converges is not true. So keep that in mind. Alright? You don't have the converse for this one. Right? Now, example number 1. Determine whether each of the series is absolutely convergent, conditionally convergent, or divergent. Alright? Question A. Now, step number 1, we're going to check the series of absolute value of A sub n. Right? So it's going to be, check the absolute value of this one. It's actually the series of 1 over n, right? Now, this guy is the harmonic series, so it's going to be diverges. Now, we're going to check the second one, original series, right? We look at this one. If this one diverges, case number 2, right? We're going to check original one to see if it converges or diverges, right? If it converges, and then this is going to be convergent conditionally, right? So original one is going to be A sub n equals -1 raised to the n plus 1 over n. We look at this one, we see that -1 raised to the n plus 1, actually we're going to use the alternating series test, right? So we're going to let b sub n be 1 over n, right? So here's the alternating series test, right? We need to check to see if limit of b sub n equals 0. Second one, the sequence b sub n is a decreasing sequence, right? So we're going to use this one right here. And we have the tips to verify non-increasing behavior for a sequence using one of this one right here, right? So I'm going to find the limit of 1 over n when n approaches infinity. This guy actually 0, right? So the first condition is met, right? Now second condition, I have b sub n plus 1 over b sub n equals 1 over n plus 1 over 1 over n, right? So it's going to be 1 over n plus 1 times n over 1, right? So it's going to be n over n plus 1, right? Less than 1, right? So the sequence b sub n decreasing, right? So then by alternating series test, this guy right here converges, right? So by number 2 right here, this series converges conditionally, right? Now question B, we're going to check to see if the series of absolute value of A sub n converges or diverges, right? So it's going to be 1 over square root of n, right? So it's going to be 1 over n power of 1/2, right? And this series diverges by the p series, right? Because p equals 1/2 less than or equal to 1, right? Now we're gonna check the original one, right? So we have the series of a sub n equals the series of -1 raised to the n over square root of n, right? Now we're gonna use the alternating series test to do this one. So we're gonna let b sub n equals 1 over square root of n, right? Now we're gonna take the limit of b sub n, right? When n approaches infinity equals limit of 1 over square root of n is going to be n power of 1/2, right? When n approaches infinity, it's going to be 0. So the first condition is met, right? Now we're going to move on to second condition, right? So we're going to take the b sub n plus 1 over b sub n. It's going to be 1 over square root of n plus 1 times square root of n over 1, right? So it's going to be square root of n over n plus 1. And it's going to be less than 1 for sure, right? Then by the alternating series test, the original one right here convergent. So you can conclude that the original one right here converges conditionally, right? Now question C. You need to check the series of absolute value of a sub n, right? So it's going to be the series of n factorial over 2 to the n, right? The factorial function always grows faster than the exponential function, right? So this series approaches infinity, which diverges, right? By the n-term test. Now we're going to check the original one. Now we're going to use the ratio test to check this one, right? The ratio test right here. So we're going to have the series of a sub n plus 1 equals. So you're going to take the limit of absolute value of a sub n plus 1 over a sub n when n approaches infinity equals limit when n approaches infinity of absolute value of times the reciprocal of this one, so it could be 2 to the n over -1 raised to the n times n factorial, right? Now we're going to simplify this one. -1 raised to the n plus 1 is going to be -1 raised to the n times -1, right? And then this guy and this guy cancel out, right? 2 to the n plus 1 is going to be 2 to the n times 2. This guy cancel out, right? N plus 1 factorial is going to be n plus 1 times n factorial, right? This guy cancel out, right? Now absolute value of -1 is going to be 1, right? So we don't really care about this one anymore, right? So the top equals, so we have limit when n approaches infinity, absolute value of n plus 1, right? Over 2, right? Now when n approaches infinity, this guy approaches infinity, right? So by the ratio test, the series diverges, right? And finally, the original one right here diverges, right? Now let's take a look at question D. We need to check the series of absolute value of a sub n, right? So it's going to be the series of 1 over n factorial, right? Now we're going to use the ratio test, right? So we have a sub n plus 1 equals 1 over n plus 1 factorial, right? So we have limit of absolute value of a sub n plus 1 over a sub n when n approaches infinity equals limit of absolute value of 1 over n plus 1 factorial multiplied by this reciprocal, right? So it could be n factorial over 1, right? When n approaches infinity, so it's going to be limit of n factorial over n plus 1 altogether factorial when n approaches infinity, right? So it's going to be limit of absolute value of 1 over n plus 1, right? When n approaches infinity. So this one equals 0, right? So by the ratio test, if the limit less than 1, the series converges absolutely, right? And we look at the number 1 right here. If this guy converges, and then original one must be convergent, right? Now, you have two different ways to deal with this topic. You either start with the original one, or you're going to start with the absolute value 1, right? Now, for the first one, the series a sub n either converges or diverges. If it diverges, you stop, right? If it converges, you're going to check to see if it is absolutely converges or conditionally converges, right? Number 2, you can start with the absolute value of the series, right? If it diverges, and then you're going to check to see if the original one is conditionally convergent or divergent, right? If it converges, and then you stop, because if this guy converges, and then original one must be convergent, right? Let's move on to example number 2. Determine whether each of the series is absolutely convergent, conditionally convergent, or divergent, right? Now question A, we're going to check the series of absolute value of a sub n, right? So it's going to be the series of square root of n over n squared plus 1, right? Now I'm going to use the direct comparison test. So I'm going to compare this guy with the series of square root of n over n squared, right? So I'm going to start with n squared always less than or equal to n squared plus 1, right? And then I'm going to take reciprocal both sides, so it could be 1 over n squared greater than or equal to 1 over n squared plus 1, right? So I'm going to multiply both sides by square root of n, right? So square root of n over n squared greater than or equal to square root of n over n squared plus 1, right? Now, this guy right here is larger, right? This guy right here is smaller, right? Now, we need to check this guy. So we have the series right here, right? It's going to be the series of 1 over n power of 3.5, right? And this guy actually converges by p series because p equals 3.5 greater than 1, right? So the larger converges, then the smaller must converge. And the original one right here converges, right? Because I just used the direct comparison test, right? And the first one right here, the series of absolute value of a sub n converges, then original one converges. We don't need to check the original one anymore, right? Now question B. I'm going to check the series of absolute value of a sub n, right? So when you take absolute value of this one, it turns out to be the series of 2 to the k over k squared, right? Now I'm going to use the n-term test to check to see if this one is converges or diverges, right? Look at the n-term test right here. If the limit not equal to 0, the series diverges, right? So I'm gonna take the limit of this one. When k approaches infinity, the top is the exponential function. The bottom is the polynomial function. The exponential function grows faster than the polynomial function, right? So this one approaches infinity, right? So by the n-term test, this guy diverges, right? Now I look at this one right here. Since it diverges, I need to check the original one right here to see if it converges conditionally, right? So I'm going to use the ratio test, right? So I have limit of absolute value of a sub n plus 1 over a sub n when n approaches infinity, right? It's going to be limit of a sub n plus 1, so it can be absolute value of -1 raised to the k plus 2, right? Times 2 to the k plus 1, right? Over k plus 1 square, right? Times this one reciprocal, so it can be k square over -1 raised to the k plus 1 times 2 to the k, right? When k approaches infinity, right? Now, since I use the variable k, so every single thing right here must be k, right? And -1 raised to the k plus 1 cancel out. So you have -1 power of 1. So if you take absolute value, it's going to be positive, so it's gone, right? Now, 2 to the k plus 1 and 2 to the k cancel out. So you have 2 on the top left, right? So you have limit when k approaches infinity of absolute value of 2 k squared over k plus 1 altogether square. Now when k approaches infinity, number 1 right here doesn't really matter, right? So it turns out to be limit of 2k squared over k squared. When k approaches infinity, it's going to be 2, right? So we look at the ratio test. If it's greater than 1, the series diverges, right? So you can say that this guy right here diverges, right? By the ratio test. Let's move on to question C. We're gonna check the series of absolute value of a sub n, right? So if you check absolute value of this one, it's gonna be 1, right? So it's gonna be the series of 1 over n, right? Now this guy actually harmonic series or the p series where p equals 1, right? So this one diverges by the harmonic series. Now we need to check the series a sub n. Now I'm going to use the alternating series test, right? So I'm going to let b sub n equals 1 over n, right? Now I'm going to check limit of 1 over n when n approaches infinity. This one equals 0. So the first condition is met, right? Second one, I'm going to check b sub n plus 1 over b sub n. It's going to be 1 over n plus 1 times this one reciprocal. It's going to be n over 1, right? So it can be n over n plus 1. This guy less than 1. It tells us that b sub n is decreasing, right? So the second condition is met, right? So we look at the alternating series test right here. Two conditions are met, the series converges, right? So then you can say that a sub n converges by the alternating series test. Alright, so you can conclude that the original one right here converges conditionally, right? Now let's move on to question D. We need to check the series of absolute value of a sub n, right? So if you take absolute value of this one, it's going to be the series of 1 over n squared, right? So this series converges by p series, right? So you can conclude that the original one, series a sub n, converges absolutely, right? Now let's move on to question E. We need to check the series of absolute value of a sub n, right? So it could be, now when n approaches infinity, n cubed should be positive, right? So I have the series of n cubed on the bottom. This guy is still inside the absolute value sign, right? Now observe that sine n always greater than or equal to -1 less than 1. So then the absolute value of sine n always less than or equal to 1, right? So then I'm going to divide both sides by n cubed. So I have absolute value of sine n over n cubed less than or equal to 1 over n cubed, right? So this guy is the same thing as, observe that this series converges by the p series, right? So this one converges by the direct comparison test, right? Now since the series of absolute value of a sub n converges, the original one right here converges absolutely, right? Now let's move on to question F. First, note that the terms are non-negative, since 1 plus cosine n greater than or equal to 0, right? Now observe that this series right here converges by p series because p equals 2 greater than 1. Now for the second one right here, I'm going to check the series of absolute value of cosine n over n squared when n goes from 1 to infinity, right? It's going to be absolute value of cosine n over n squared when n goes from 1 to infinity, right? Now you know that absolute value of cosine n always less than or equal to 1, right? So this guy less than or equal to the series of 1 over n squared, right? But this one converges by p series since p equals 2 greater than 1, right? So by direct comparison test, this guy converges, right? Since this guy converges, then the series n goes from 1 to infinity of cosine of n over n squared converges, right? Now this guy converges. This guy also converges. Then the original one right here must converge, right? Now let's move on to the next one. Rearrangement of series. A finite sum such that 1 plus 3 minus 2 plus 5 minus 4 can be rearranged without changing the value of the sum. However, it's not necessarily true of an infinite series. It depends on whether the series is absolutely convergent or conditionally convergent. Alright, so let's take a look at example number 3. It has been proved that the alternating harmonic series converges to Ln2. Now, rearrange the series to produce a different sum. We're gonna rewrite this one as 1 divided by 1 is gonna be 1 minus 1 half, right? And then subtract 1 over 4 plus 1 over 3. Subtract 1 over 6 minus 1 over 8 plus 1 over 5 minus 1 over 10 minus 1 over 12 plus 1 over 7 minus 1 over 14, right? Plus etc., right? Now I'm going to group the first two terms, right? The next two terms right here. This guy and this guy, this guy and this guy, right? So 1 minus 1/2 is going to be 1/2 minus 1 over 4 plus 1 over 6 minus 1 over 8 plus 1 over 10 minus 1 over 12 plus 1 over 14 plus etc. Right? Now I'm going to factor 1/2 out, so it will be 1/2 times 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5 minus 1 over 6 plus 1 over 7 minus etc. Right? This guy actually ln2, right? So it will be 1 over 2 times ln2, right? Now let's move on to example number 4. For what value of S is the series absolutely convergent? So if this one is absolutely convergent, we have this series must be convergent, right? So we're going to use the ratio test. So we have limit of absolute value of a sub n plus 1 over a sub n when n approaches infinity, right? This one right here is a sub n now. Limit when n approaches infinity of absolute value of a sub n plus 1 is going to be n plus 1 times s plus 5 raised to the n plus 1 over 7 raised to the n plus 1, right? Multiplied by this one reciprocal. So it could be 7 raised to the n over n times s plus 5 raised to the n, right? Now we're going to simplify, so it could be limit when n approaches infinity absolute value of. Now on the top n plus 1, the bottom is n, we just rewrite, right? Now this one s plus 5 raised to the n plus 1 can be written as s plus 5 raised to the n times s plus 5, right? So this guy and this guy cancel out, so we have s plus 5 left on the top, right? Now 7 to the n and 7 to the n plus 1 is going to be 7 left on the bottom, right? When n approaches infinity, this guy right here approaches 1, right? So we only have s plus 5 over 7 left, right? And we need this guy s plus 5 over 7 less than 1, right? By ratio test right here. Be the same thing as s plus 5 over 7 less than 1 greater than -1, right? So it's going to be s plus 5 less than 7 greater than -7, right? Subtract 5 both sides, so it's going to be -12 less than s less than 2, right? So the answer must be D. Now if the question asks you to find the value of s, show that the series is conditionally convergent, and then you need to check the endpoint. We need to check s equals -12, s equals 2, right? And then we're going to do this in this problem B right here, right? Problem B, we do exactly the same thing, right? We're going to use the ratio test, right? So we have limit of a sub n plus 1 is going to be n plus 1 times s to the n plus 1 over 4 to the n plus 1 times n plus 1 altogether square plus 1, right? Times this reciprocal. So it could be 4 to the n times n square plus 1 over n times s to the n when n approaches infinity, right? Now we're going to simplify this one, so it could be limit of absolute value of n plus 1 rewrite, right? And right here we just rewrite, right? S to the n plus 1 and s to the n is going to be s on the top left, right? Now 4 to the n plus 1 and 4 to the n right here, we have 4 left on the bottom, right? Now on the top we have n squared plus 1. The bottom we have n squared plus 2 and plus 2, right? When I expand this one and simplify. Now when n approaches infinity, this guy approaches 1. This guy approaches 1, right? We have s over 4 left, right? So we need this one less than 1, right? By ratio test. So we have absolute value of s over 4 less than 1, right? So it's going to be s over 4 less than 1 greater than negative 1, right? So it's going to be s less than 4 greater than negative 4, right? This guy is the absolutely convergent, right? But the question asks us to find the conditionally convergent, right? So we need to check the endpoints, right? So we need to check s equals negative 4 first, right? Today over here, we have the series n goes from 1 to infinity of n times negative 4 to the n over 4 to the n times n squared plus 1, right? So it's going to be the series when n goes from 1 to infinity of n times 4 to the n times negative 1 to the n, right? Over 4 to the n times n squared plus 1, right? So then you can cancel out this guy and this guy, right? So then it's gonna be the series when n goes from 1 to infinity of negative 1 raised to the n times n over n squared plus 1, right? Now I'm gonna let b sub n be n over n squared plus 1, right? So I'm going to use the alternating series test, right? So I'm going to take limit of b sub n when n approaches infinity. It's going to be this guy actually 0, right? So we'll look at the alternating series test right here. The first condition is matched, right? Now we're going to check the second condition to see if the sequence is decreasing, right? I'm going to let f of s equals s over s squared plus 1, right? This guy right here. The domain s greater than or equal to 1, right? Look at this one right here. So I'm going to check the derivative of this one. I'm going to use quotient rule, right? So it could be negative 2 s squared plus s squared plus 1 over s squared plus 1 all together squared, right? So it could be negative s squared plus 1 over s squared plus 1 all together squared. The bottom always positive, right? The top is less than or equal to 0 because s greater than or equal to 1, right? So then you have f prime of s less than or equal to 0. Then f of s is decreasing, right? Alright, so using the alternating series test, the first and the second condition satisfies. So then the series converges, right? So s equals negative 4 works, right? And the answer is B. Now we're going to check to see if s equals 4 works, right? Now if s equals 4, we have s equals 4 right here, right? So I just change the sign right here, right? So then I don't have this guy, right? So I only end up with the series of n over n squared plus 1, right? I don't need this guy, right? When n goes from 1 to infinity, right? Now we need to compare this guy n over n squared plus 1 with harmonic series, right? Why? Because this guy is the same thing as n over n squared. When n approaches infinity, you can drop 1, right? And you can simplify it's going to be 1 over n, right? This one is harmonic series. Harmonic series always diverges, right? So now we're going to use the limit comparison test, right? So we have limit when n approaches infinity of a sub n over b sub n. Now this one right here is a sub n. This one right here is b sub n, right? So we have limit of absolute value of n over n squared plus 1 divided by b sub n, which means multiplied by its reciprocal, right? So it could be n over 1 when n approaches infinity, right? So then it's gonna be limit when n approaches infinity. This guy always positive, right? So I can remove the absolute value side, right? So it could be n squared over n squared plus 1, right? When n approaches infinity, you can drop 1 by relative growth rate, right? So we have limit when n approaches infinity of n squared over n squared, right? So it could be 1. This one is the positive number and finite. Limit comparison test right here. If we get the limit equals L, that is positive and finite, right? Now you're gonna check if one series converges, then both series converge, right? If one series diverges, then both series diverge, right? Now since this one diverges, right? Original one right here must be divergent, right? So you can conclude that a sub n diverges by limit comparison test, right? So as equal 4 is to be diverges, so this one is wrong, right? So the final answer must be s equal negative 4 only, right? Question C. Which of the following statements true about the series? Alright, so first we need to check the absolute value, right? So we have series of absolute value of this one, right? So it could be negative 1 to the n plus 1 over n power 1 third, right? When n goes from 1 to infinity, right? So this guy actually, the series when n goes from 1 to infinity of 1 over n power 1 third, right? And this one diverges by p series because p equals 1 third less than or equal to 1, right? So the absolute value of the series is divergent. We need to check to see original one is conditionally convergent, right? So we're going to use the alternating series test right here, right? So we're going to let b sub n be this guy right here, right? So we let b sub n equals 1 over n power 1 third, right? So we're going to take limit of b sub n is going to be 1 over n power 1 third. When n approaches infinity, it's going to be 0. So the first condition is matched, right? Now the second condition, we're going to check to see if this one increasing or decreasing, right? So we're going to use f of s equals 1 over s power 1 third, right? S greater than or equal to 1, right? Right here. So then f prime of s equals, we're going to use the quotient rule, right? So the derivative of this one equals 0 times this one is going to be 0 minus 1 over 3 s 1 third subtract 1 is going to be negative 2 third, right? Over s power 2 third. So it's going to be negative 1 over 3 s power of 4 third, right? And this one always less than 0, right? So f of s is decreasing, right? And then the series b sub n decreasing. The second condition is matched, right? So you can conclude that this guy right here converges conditionally, right? So the answer must be A. Now let's move on to question D. We do exactly the same things, right? Now we need to check the absolute value, right? So we have series of absolute value of A sub n, right? Is going to be absolute value of negative 1 raised to the n over 1 plus n power of 3 and a half, right? So it's going to be the series of 1 over 1 plus n power of 3 and a half, right? We have 1 plus n power of 3 and a half always greater than or equal to n power of 3 and a half, right? And we take reciprocal of this one, it's going to be 1 over 1 plus n raised to the 3 and a half less than or equal to 1 over n power of 3 and a half, right? Now, this one is the larger, right? This one is the smaller, right? Now, the larger converges by P series, right? Since P equals 3 over 2 greater than 1, right? So since the larger converges, the smaller converges, right? By comparison test. Alright, so since the absolute value of this series converges, the series converges, right? So the answer must be B. Now let's move on to the last question, question E. Which of the following statement true about this series? Alright, so first we need to check this series of absolute value of A sub n, right? To see if it converges or diverges, right? So this guy is the same thing as series of L n of n over n, right? Because when you check absolute value of this guy, it's going to be positive, right? Now we're going to check this one, right? So observe that if n greater than e, right? And then ln of n greater than ln of e, right? So ln of n greater than 1, right? Divide both sides by n. So you have ln of n over n greater than 1 over n, right? We're going to use direct comparison test. So we know that the series 1 over n diverges by harmonic series test, right? So then by direct comparison test, the smaller diverges, the larger diverges, right? So then we look at this one, the smaller diverges, then you can conclude that the series of ln of n when n goes from 1 to infinity diverges by direct comparison test. So we need to check the series negative 1 to the n ln of n over n when n goes from 1 to infinity, right? So we're gonna let b sub n equals ln of n over n, right? Now we need to use the alternating series test, which is right here, right? So we need to find the limit of b sub n, and then we need to prove that b sub n is decreasing, right? So I have limit of b sub n when n approaches infinity equals limit of ln of n over n, right? When n approaches infinity, indeterminate form, right? So we need to use last video rule, right? So we have limit when n approaches infinity, derivative of ln is going to be 1 over n. derivative of n is going to be 1, right? So when n approaches infinity, this one approaches 0, right? So the first condition is met, right? Now the second one, we need to prove that b sub n decreasing, right? So we're gonna let f of s equals ln of s over s, right? Now we're gonna take the derivative of this one, so it could be f prime of s equals, we're gonna use the quotient rule, right? So the derivative of ln s it could be 1 over s times s minus derivative of s it could be 1 times ln s over s squared, right? So we simplify, it's gonna be 1 minus ln s over s squared, right? The bottom is positive, right? So we need this one to be less than or equal to 0, right? In order for this one to be decreasing, right? So then we have 1 minus ln s less than or equal to 0, right? So then ln s greater than or equal to 1, right? So s greater than or equal to e power of 1, which means e, right? So we can conclude that f of s is decreasing for s greater than or equal to e. Is the same thing as the series b sub n is decreasing. So the second condition is met, right? It tells us that the series a sub n converges by alternating series tests, right? But you know that the absolute value 1 diverges, right? So the answer must be 3. We're going to explore topic 10.10, alternating series error bound. Alright, we look at the theorem right here. It's called alternating series remainder. If a convergence alternating series satisfies the condition a sub n plus 1 less than or equal to a sub n, then the absolute value of the remainder r sub n involved in approximating the sum s by s sub n is less than or equal to the first neglected term. That is, error equals absolute value of actual subtract estimate. So the best way for you to memorize the formula is EAE, right? Equals absolute value of the sum of the infinite series subtract the partial sum of the series equals absolute value of the remainder less than or equal to a sub n plus 1 inside the absolute value, right? Where s sub infinitive equals the sum of the series, s sub n is called the partial sum of the series, r sub n is called remainder, also known as error, and a sub n plus 1 called the next term, also known as error bound, right? Now let's take a look at the first example. Approximate an interval of the sum of the alternating series, right? Which means they ask you to find the interval of s, right? Using the alternating series error bound for the first 6 terms correct to the 3 decimal places. Alright, so we're going to use the formula right here, right? So you have the formula absolute value of s subtract s sub 5, right? We look at this one, n goes from 0, right? So s sub 5, which means 6 terms, right? Less than or equal to a sub n plus 1, which means absolute value of a sub 6, right? Now we need to calculate s sub 5. So we have s sub 5 equals the sum when n goes from 0 to 5 of negative 1 raised to the n over n factorial equals how much, right? And then we need to calculate a sub 6, right? This guy is the same thing as negative 1 raised to the 6 over 6 factorial, right? So we're gonna print up the calculator. Now we're gonna press the button right here. Pick the summation notation right here, right? Now n goes from 0 to 5. Now you're gonna hit this button right here. Pick the fraction. Negative 1 raised to the n, right? Over n factorial. So we're gonna pick n right here, and you're gonna hit the button right here and pick the factorial right here, right? And then press Ctrl Enter. It's gonna be 0.36667, right? We're gonna calculate a sub 6, right? So we have the fraction right here, parentheses negative 1 altogether raised to the 6 over 6 factorial. And then press Ctrl Enter. It's gonna be 0.01389. Alright, so we sub these two values right here into the formula right here. So we have the formula absolute value of s less than or equal to a, and then s less than or equal to a greater than or equal to negative a, right? And by the way, if we have the formula absolute value of s greater than or equal to a, it's gonna be s greater than or equal to a, or s less than or equal to negative a. So keep that in mind. Alright, so we're gonna apply the first formula right here, right? So we have s minus 0.36667 less than or equal to 0.001389 greater than or equal to 0.001389. Don't forget the negative side, right? Now you just add 0.36667 three sides, so you're gonna end up with. Now question B similar, right? So I'm gonna leave this one for you to practice. The answer is negative 0.680 less than or equal to s less than or equal to 2.961, right? Now let's move on to example number 2. Show that the series converges. Alright, so this is alternating series, right? So we let this guy right here be b sub n, right? We need to prove that b sub n positive, right? B sub n decreasing, right? And limit of b sub n when n approaches infinity equals 0, right? Three conditions right here must be matched, right? By the alternating series test right here, right? Now, the first one, b sub n equals 3 over 2 to the n times n plus 1. This one always positive for all n greater than or equal to 1, right? Now, the second condition, b sub n equals 3 over 2 to the n times n plus 1. Now, as n increasing, this one decreasing, right? So you just say b sub n is always decreasing when n increasing, right? Now, number 3, limit of b sub n when n approaches infinity equals limit of 3 over 2 to the n times n plus 1 when n approaches infinity, and this guy actually 3 over infinity is going to be 0, right? So the third condition is met, right? So we can conclude that the series converges by alternating series test, right? Now let's move on to question B. Find S sub 6 and use the alternating series error bound to show that S sub 6 differs from S by less than 3 over 1000. Alright, so we have S sub 6 equals the sum n goes from 1 to 6 of negative 1 raised to the n minus 1 times 3 over 2 to the n times n plus 1, right? And then you just put this one on the calculator. The answer is 0.267225, right? Now we need to use alternating series error bound to show that S sub 6 differs from S by less than 3/1000, right? So we have the formula absolute value of S subtract S sub 6 always less than or equal to absolute value of B sub 7, right? So we have absolute value of S subtract S sub 6 less than or equal to. Now substitute 7 for n, so we have 3/2 power of 7 times 8, right? Now we're going to simplify this one. It's actually 3/1000 to 4, right? And this guy always less than 3/1000, right? Right here. So by transitive property, you can conclude that S subtract S sub 6 less than 3/1000, right? Now let's move on to example number 3. Determine the number of terms required to approximate the sum of the given convergence series with an error of less than 0.01, right? So we have the formula absolute value of S subtract S sub n less than or equal to absolute value of A sub n plus 1, right? And we need this one to be less than 0.001, and this guy actually 1/1000, right? Now absolute value of A sub n plus 1, so this guy gone, because when you take absolute values, every single thing should be positive, right? So I have 1/, instead of n square, I write n plus 1 altogether square, right? A sub n plus 1. Now we need this one to be less than 1000, right? We're going to take reciprocal both sides, so it's going to be n plus 1 altogether square greater than 1000, right? Now you're going to take square root both sides, so you have n plus 1 greater than square root of 1000, right? Or n plus 1 less than negative square root of 1000, right? But number of terms are always positive, right? So we just ignore this one, right? So we have n plus 1 greater than 31.6228. Subtract 1 both sides, so n greater than 30.6228. The question asks you to find the least number of terms, right? So then you can conclude that n equals 31, right? Now question B, we do exactly the same thing, right? So we need to take absolute value of A sub n plus 1, right? It's going to be 1/2 to the n plus 1 times n plus 1 factorial, right? We need this one to be less than 1/1000, right? Now take reciprocal both sides, so we have 2 to the n plus 1 times n plus 1 factorial greater than 1000, right? Now to solve this one, we just check n equals 3, so it's going to be 2 power 4 times 4 factorial, right? So you're going to bring up the calculator. 2 power 4 is going to be 16, right? Times 4 factorial. Press enter. It's going to be 384. 384 is less than 1000, so it doesn't work, right? Now check the next one, n equals 4, so it could be 2 power of 5 times 5 factorial, right? So it's going to be 32 times 120, right? Press enter. It's going to be 3840. Greater than 1000. So this one works, right? So n equals 4. Determine the least number of terms of the series required to guarantee a partial sum that is within 0.05 of S using the alternating series error bound. Alright, So we have absolute value of a sub n plus 1 less than 0.05, right? So it's going to be 1 over square root of n plus 1 less than 0.05, right? And 0.05 actually 5 over 100, right? And it's going to be 1 over 20, right? Now you just take reciprocal both sides, so it turns out to be square root of n plus 1 greater than 20, right? Square both sides, so it could be n plus 1 greater than 400, right? So n greater than 339, right? The question asks us to find the least number of terms, right? So the least integer that's greater than 399 is 400, right? So the answer must be D. Now let's move on to example number 5. If the infinite series S is approximated by p sub k, what is the least value of k for which alternating series about guarantees this? So this guy actually the same thing as absolute value of a sub k plus 1 less than 7 over 100, right? So we just ignore this one, right? So this one turns out to be 4 over k plus 1 less than 7 over 100, right? So you just take reciprocal both sides, so it can be k plus 1 over 4 greater than 100 divided by 7, right? Multiply both sides by 4, so k plus 1 greater than 400 divided by 7, right? Now 400 divided by 7 is going to be 56 something, right? So it's going to be k greater than, subtract 1 both sides, so it can be 400 over 7 subtract 1, right? So it's going to be k greater than 56 point something, right? Now the least integer k such that k greater than 56 is 57, right? Now let's move on to example number 6. Let FLS be this series. Show that 1 minus 1 over 3 factorial approximates f of 1 with an error less than 0.01. Alright, so we have the formula absolute value of s subtract s sub n always less than or equal to absolute value of a sub n plus 1, right? Now we look at this one. This one is the first term. We call this a1, a sub 2, a sub 3, a sub 4, etc. Right? Now show that this guy actually a sub 1. This is a sub 2, right? So this guy, the partial sum is 2, right? So we have absolute value of s subtract s sub 2, right? Less than, this guy must be absolute value of a sub 3, right? Because it's a sub n plus 1. So we see that f of 1, we substitute 1 for s over here. So we have this one turn out to be 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial, right? Now a sub 3 is going to be right here, right? So we have absolute value of s minus s sub 2 less than or equal to 1 over 5 factorial is going to be 1 over 120, right? And this number always less than 0.01, right? Which is 1 over 100, right? So this one has been proved, right? Now let's move on to example number 7. The series converges by the alternating series test if the partial sum is the n partial sum of the series. Which of the following statement must be true? Alright, we don't know this guy, right? We don't know this. This guy right here 26, this guy 25, yeah, 1 unit less than this one, so the answer must be D. This is 20, this is 26, so this is wrong, right? Remember, we have the formula absolute value of s subtract s sub n always less than or equal to a sub n plus 1, right? Now let's move on to example number 8. If the series is approximated by the partial sum with 15 terms, what is the alternating series at about, right? So we have the formula absolute value of s subtract s sub n less than or equal to absolute value of a sub n plus 1, right? So we have absolute value of s subtract s sub n less than or equal to a sub n plus 1, which means 1 over 5 times n plus 1, right? Now n equals 15, right? So we have absolute value of s subtract s sub 15 less than or equal to 1 over 5 times 15 plus 1 plus 1, right? So it's going to be 1 over 15 plus 1, it could be 16 times 5, it could be 81, right? So the answer must be D. Now, example number 9, similar to example number 6, so I'm going to leave this one for you to practice, right? Now, let's move on to example number 10. Let f of s be this series for all s which the series converges. Question A. Use the first 3 terms of the series to approximate f of -1/3, right? So you have f of -1/3 equals the sum n goes from 1 to 3 of -1/3 to the n times n to the n over n factorial, right? So you're gonna print up the calculator. You're gonna press this button right here, and you're gonna pick the summation notation right here, right? N goes from 1 to 3. Now you're gonna put the fraction right here. It's gonna be -1/3 to the n times n to the n divided by n factorial. So you press n and you press the button right here, pick the factorial, and then you press Control Enter. It's gonna be -27778. Now question B. How far off is this estimate from the value of f of -1/3? Justify the answer. Alright, so actually we need to use the error bar, right? So we have absolute value of s subtract s sub n less than or equal to absolute value of a sub n plus 1, right? So we have 3 terms, right? So we have absolute value of s subtract s sub 3 less than or equal to absolute value of a sub 4, right? So a sub 4, which means n equals 4, right? So we have absolute value of s equal -1/3. So you have -1/3 raised to the 4 times 4 raised to the 4 over 4 factorial, right? So you're going to print up the calculator. It's going to be 0.131687, right? We're going to explore topic 10.11, finding Taylor polynomial approximations of functions. Alright, we're going to talk about the linear and quadratic approximation. Alright, so in topic 4.7, we know that the linear approximation is given by this formula. This guy actually the point slope formula, which you learned from Algebro 1, right? Y minus y1 equals m times s minus s1. So it's going to be y equals m times s minus s1 plus y1, right? So this one is y1, this one is m, this is s1, right? Now, this linear approximation is the first degree polynomial of s, so we can name this one as p sub 1 of s, right? So we replace L of s with p sub 1 of s, right? Now the problem is that linear approximations don't always work so well when the graph of f has a great deal of curvature near C. So then, in order to fix this problem, we're gonna create a quadratic approximation. Alright, so we just add a times s minus c squared, right? This one is the first degree, this one the second degree, right? Now we need to solve for a, right? So here's the p2 of c where s equals c, right? So we substitute over here, we get f of c, right? Now we take the derivative of this one. So derivative of f of c, this is a constant, it's going to be 0, right? This is a constant, we just rewrite it, right? Derivative of s equals 1, right? A is a constant, we just rewrite it. Bring 2 to the front, we're going to use the power rule, so we get this one right here, right? Now we substitute c for s, right? So we're going to end up with this guy right here, right? Now we're going to take the second derivative, so it turns out to be 2a only, right? This one is 0, right? So p2 the program of c, where s equals c equals 2a, right? And you know that p2 the program of c is the same thing as f the program of c equals 2a. Divide both sides by 2. We get this one right here. So we substitute this guy back to the formula right here, and we get this one right here, right? Now example number 1, find the linear approximation to fs equals lns at s equals 1, right? So we have p1 of s equals f of c plus f prime of c times s minus c, right? F of s equals ln of s, and it's going to be p1 of s, right? Equals f of c, so it's going to be ln of c plus derivative of this one is going to be 1 over s, right? So it's going to be 1 over c, right? Because s equals c times s minus c, right? This one is c equals 1. So we have ln of s is ln of 1, right? Plus 1 over 1, right? Times s minus 1, right? Ln of 1 is equal 0, right? So this one equals s minus 1, ln of s, right? Now question B, find the quadratic approximation to this one, right? So we need to find p sub 2 of s is going to be f of c plus f prime of c times s minus c plus 1/2 f double prime of c times s minus c square, right? We have ln of s is the same thing as p2 of s, and it's going to be f of c, which means ln of c, right? Plus 1 over c, right? S minus c plus 1/2 f double prime. So we have f prime of s equals 1 over s. F double prime of s equals negative 1 over s squared, right? So you have times negative 1 over c squared, right? Times s minus c altogether squared, right? Now you have s equals 1, which means c equals 1, right? So substitute 1 for c. So you have ln of s equals ln of c, which means ln of 1, right? Plus 1 over 1 times s minus 1. Subtract 1 over 2, right? Times s minus 1 altogether squared, right? Now we're going to simplify, so it's going to be ln of s equal, this one equals 0, right? It's going to be s minus 1 minus 1 over 2 s minus 1 altogether squared, right? Now question C, use these approximations to estimate the value of ln of 1.05, right? Now we have p1 of 1.05 is going to be this guy right here, right? 1.05 subtract 1, right? So it could be 0.05. Now we're going to use p2 of 1.05. It's going to be right here, right? So it could be 1.05 minus 1 subtract 1/2 times 1.05 minus 1 altogether square, right? So it's going to be 0.05 minus 1/2 of 0.05 square, right? So we're going to print up the calculator, right? So it's going to be 0.4875, right? Now the next question, how do these approximations compare to the actual value of this one? Alright, so we're going to print up the calculator to find the actual value, right? So we're going to press Control E to the S right here, right? Put 1.05, press Control Enter. It's going to be 0.04879, right? And you see that P2 gives you the answer that's closer to the actual value, right? So P2 approximates the function better than P1, right? So the higher degree polynomials, the better, right? We're going to move on to the Taylor polynomials. So if you proceed the same process, you're going to end up with this formula right here. We have definition of n Taylor polynomial and n Maclaurin polynomial. Alright, if the function f has n derivatives as c, then the polynomial is given by this formula. Is called the n Taylor polynomial of the function f centered at c, and this guy right here is called the coefficient of the n degree term in a Taylor polynomial. Similarly, now if c equals 0, substitute 0 for c, you're going to end up with f of 0, f prime of 0 times s minus 0, which means s, right? F double prime of 0 over 2 factorial, s minus 0 square is going to be s squared, right? And then the n terms right here is called the n Maclaurin polynomial for the function f, and this one right here is called the coefficient of the n degree term in a Maclaurin polynomial, right? Note that Maclaurin polynomial is a special case of the n Taylor polynomial, right? Now let's move on to example number 2. Maclaurin polynomial for the sine s. Now find the 7th degree Maclaurin polynomial P7 of s for the function f of s equals sine s, right? Now we have f of s equals sine s, right? And then we can calculate f prime of s equals cosine s, right? And then f double prime of s equals negative sine s. Then f triple prime of s equals negative cosine s. And then the fourth derivative sine s, right? And the fifth derivative is going to be cosine s. The sixth derivative is going to be negative sine s, right? And the last one, the 7th derivative, is going to be negative cosine s, right? Now, since this one is Maclaurin series, right? So we're going to substitute 0 for c, right? So we have f of 0 equals sine of 0 is going to be 0, right? F prime of 0 is going to be cosine 0 equals 1, right? F double prime of 0 is going to be negative sine of 0 equals 0. F triple prime of 0 is going to be negative 1, right? Now this one equals 0, right? The fifth derivative of this one, s0 is going to be 1. The sixth derivative is going to be 0. And the 7th derivative is going to be negative 1, right? So we have the formula P7 of s equals f of 0 plus f prime of 0 times s, right? Plus f double prime of 0 over 2 factorial s squared, right? Plus f triple prime of 0 over 3 factorial s cubed plus the 4 derivative of 0 over 4 factorial s to the 4 plus. Now we just substitute values, right? F of 0 equals 0 right here, right? F prime of 0 equals 1, so we have P7 of s equals s, right? F double prime of 0 equals 0, so this guy gone, right? This guy gone. F triple prime of 0 equals negative 1, right? So we have negative 1 over 3 factorial s cubed, right? This guy right here equals 0, right? So it's gone. The fifth derivative is going to be 1 right here, right? So you have plus 1 over 5 factorial s to the fifth, right? The sixth derivative equals 0 right here, gone. The seventh derivative is going to be negative 1, right? So minus 1 over 7 factorial s to the 7, right? Now, if this one is the FRQ, you just leave it like this, right? But you need to simplify if this one is the MCQ, right? So you have s minus 3 factorial is going to be 3 times 2 times 1, right? So it will be 1 over 6 s cubed, right? 5 factorial is going to be 5 times 4 times 3 times 2 times 1, right? So it could be plus 1 over 120 s to the fifth, right? Minus 7 factorial is going to be 1 over 5040 s to the 7, right? Now question B, use P7 of s to approximate this one, right? So we have P7 of 0.2 is going to be 0.2 minus 1 over 6 times 0.2 cubed plus 1 over 120 times 0.2 to the fifth minus 1 over 5040 times 0.2 to the 7, right? So we're going to print up the calculator, press Ctrl Enter. It's going to be 1.9869, right? Now question C. What do you notice about the degree of each term of P7s? So we see that the degree of each term is 3, 5, 7, which is odd, right? Since the sine function is odd, right? Now, can you make an assumption about the degree of any Maclaurin polynomial for the cosine s, right? So similarly, the degree of each term is even for cosine s, since the cosine function is even, right? Now let's move on to example number 3. A function f of s is differentiable for all orders and has the following derivative values when s equals 1. Right? Use the third degree Taylor polynomial for f of s center s equals 1 to approximate this one, right? So we have p3 of s equals f of c plus f prime of c s minus c plus f double prime of c over 2 factorial s minus c square plus f triple prime of c over 3 factorial times s minus c cubed. We stop right here, right? Because it's a third degree, right? Now we substitute 1 for c, right? So we have p3 of s equals f of 1. F of 1 is 2 right here, right? Plus f prime of 1. F prime of 1 equals negative 3 times s minus 1, right? F double prime of c is going to be right here. So it's going to be 1 over 2 factorial. It's going to be 2, right? Times s minus 1 square plus f triple prime of c is going to be right here. Negative 6, right? negative 6 over 3 factorial is going to be 6, right? Times s minus 1 cubed, right? Now we're going to simplify this one, so it could be, now we need to approximate this one, right? So f of 1.1 is the same thing as p of 1.1, right? So it's going to be 2 minus 3 times 1.1 subtract 1 plus 1.1 subtract 1 square over 2 minus 1.1 subtract 1 cube, right? So we're gonna print up the calculator. Control Enter. The answer is. Now let's move on to assignment number 4. We need to find the coefficients of the Taylor and Maclaurin polynomials. Alright, question A. Let f be a function with third derivative f triple prime of s equals 7s plus 2 to the 3.5. What is the coefficient of s minus 2 to the 4 in the 4th degree Taylor polynomial for the function f about s equals 2? We're given f triple prime of s equals 7s plus 2 to the 3.5, right? So we need to find the 4th derivative of s, right? So it could be 3.5 times 7s plus 2, 3.5 subtract 1, it could be 1/2, right? And then times derivative of 7s plus 2, it could be 7, right? So it's going to be 21 over 2 times square root of 7s plus 2, right? We have f4 of 2, right? Center at 2 equals 21 over 2 square root of 7 times 2 plus 2, right? So 7 times 2 could be 14 plus 2, 16 square root, 16 equals 4, 4 divided by 2, it could be 2, 2 times 21, it could be 42, right? So remember the general terms of the Taylor polynomial is given by the formula f n of c times s minus c to the n over n factorial, right? Now this coefficient is this guy right here, right? So we have f4 of c equals 2, right? Over 4 factorial, right? So f4 of 2 is going to be 42 right here, right? So 42 divided by 4 factorial, it could be 24, right? So we're going to divide the top bottom by 6, so it could be 7 over 4. Now question B. A function f has a Maclaurin series given by this guy, and the series converges to FOS for all real numbers s. If g is the function defined by g of s equals this guy, what is the coefficient of s in the Maclaurin series for g? Alright, so remember Maclaurin series center s equals 0, right? Now we have the Taylor polynomial for this guy. It's going to be p n of s equals, so we have the Maclaurin series, which means c equals 0, right? So we have p n of s equals. Now we need to take the derivative of this one. So we have g prime of s equals, we're going to use the power rule, right? And then we're going to use the chain rule, right? So it's going to be f prime of s times e to the f of s, right? So we have g prime of 0 is going to be f prime of 0 times e to the f of 0, right? Now f prime of 0 is the function f of s right here, right? F prime of 0 is the coefficient in front of s, so it can be right here, equal 4, right? Now times e to the f of 0, this one is the constant in the function f of s, it could be right here, right? So it could be 3, right? Now the question wants us to find the coefficient of s in the Maclaurin series. coefficient of s in the Maclaurin series is right here. Right? Look, s right here. So g prime of 0 equals 4 times e to the third. So this one is the final answer, right? Now example number 5, a function g of s has derivatives of all orders at s equals 0. It's known that g of 0 equals 2, g prime of 0 equals -1, and the general term is right here for n greater than or equal to 2. Find a third degree Maclaurin polynomial for the function g of s, right? This is very simple. So we have p3, right? Third degree of s equals g of 0 plus g prime of 0, right? Times s plus g double prime of 0 over 2 factorial times s square plus g triple prime of 0 over 3 factorial times s cubed, right? Now we just substitute value. So g of 0 equals 2 plus g prime of 0 equals -1, right? So I have negative s right here, right? G double prime of 0 equals this formula right here, right? So it could be plus 2 square, right? Over 2 factorial, right? And then you have 2 factorial, so you just rewrite this one, right? And then times s square plus this guy is going to be 3 square over 3 factorial times 3 factorial s cubed, right? So we're going to simplify this one, so it's going to be 2 minus s plus 2 factorial is going to be 2, this is going to be 2, and then cancel out this one, so it could be s squared, right? 3 factorial is going to be 6, 3 factorial is going to be 6, this is going to be 9, right? So 9 over 36 is going to be 1 over 4 s cubed, right? Now let's move on to example number 6. It's going to be similar to example number 5, right? The only thing different right here is the function g of s given by the integral of this guy, right? So you just check derivative of g prime of s equals bring s over here, right? F of s. G double prime of s equals f prime of s, right? And g triple prime of s equals f double prime of s, right? We can stop right here, right? Because this is third degree Taylor polynomial, right? Now we need to calculate g prime of 0 equals f of 0, right? F of 0 equals 4. G double prime of 0 equals f prime of 0 is going to be -3. And g triple prime of 0 equals f double prime of 0 is going to be 3, right? So we have the third degree Taylor polynomial for g about s equals 0, so it could be Maclaurin series, right? So p3 of s equals, now we plug in values, g of 0 is going to be this guy right here, g of 0 equals the integral from 0 to 0 f of t dt. This guy and this guy the same, the answer must be 0, right? So this one equals 0. G prime of 0 equals 4 right here, right? So you have 4s. G double prime of 0 equals -3, right? So minus 3 over 2 factorial equals 2s squared, right? G triple prime of 0 equals 3 right here, right? So plus 3 over 3 factorial equals 6, right? So 3 over 6 could be 1/2, right? S cubed. Now let's move on to example number 7. Consider the logistic differential equation dy over dt equals y over 6 times 4 minus y. Let y equals f of t be the particular solution to the differential equation with f of 0 equals 6, which means t equals 0, y equals 6, right? Question A. Write the second degree Taylor polynomial for f about t equals 0, right? So this guy actually Maclaurin polynomial, right? So we have the formula b2 of t equals f of 0 plus f prime of 0 times t plus f double prime of 0 over 2 factorial times t squared, right? Now, f of 0 is set given right here, right? Now, f prime of 0 is this guy right here, right? dy over dt when t equals 0, right? And y equals 6, right? So substitute over here, you have 6 divided by 6, it could be 1, right? 4 minus 6, it could be negative 2, right? Now f double prime of 0 equals d squared y over dt squared at t equals 0, y equals 6, right? So we're going to take derivative of this one. So could be, we need to expand this one first, right? So we have 4 divided by 6 could be 2 over 3y, right? Minus 1 over 6 y squared, right? So it could be 2 thirds y prime, which means dy over dt, right? Minus, bring 2 to the front, it's going to be 1 third, right? Y, and then dy over dt, right? So then we substitute 0 for t, 6 for y, and negative 2 for dy over dt, right? So we have 2 over 3 times negative 2 minus 1 over 3 times 6 times negative 2, right? We're going to simplify, it's going to be negative 4 over 3 plus 4, right? So it's going to be 8 over 3. Alright, so we substitute into this formula. So we have P2 of t equals f of 0 equals 6 right here. F prime of 0 equals negative 2, so subtract 2t, right? And f double prime of 0 equals a over 3, right? And then divide by 2, it could be 8 over 6, which is 4 over 3, right? So plus 4 over 3t squared, right? Now question B, use the results from part A to approximate f of 1, right? So f of 1 equals P2 of 1, right? So it could be 6 minus 2 times 1 plus 4 over 3 times 1 square, right? This could be 16 over 3, right? Now let's move on to the last example, example number 8. The position of a particle moving along a straight line is modeled by s of t. Selected values s prime of t is shown in the table above, and the position of the particle at time t equals 10 is s of 10 equals 8. Question A. Approximate s double prime of 8 using the average rate of change of s prime of t over the interval for 10. Now you know that 8 is between 4 and 10, right? So s double prime of 8 equals s of 10 subtract s of 4 over 10 minus 4, right? So it could be 4 minus 5.8 over 6, right? So it could be negative 1.8 over 6. It could be negative 0.3, right? Now, question B. Use the correct units. Explain the meaning of s double prime of 8 in the context of the problem. So we need to say that the rate of change of the position of the particle is decreasing by 0.3 meters per second at time t equal 8 seconds. Now question C. Use a right Riemann sum with two subintervals to approximate the interval from 0 to 10 absolute value of s prime of t dt, right? So basically we just calculate the error, right? Now we need to find the width, right? From 0 to 4, the width is 4. From 4 to 10, the width is 6, right? Now the height. Since this one is the right Riemann sum, right? So the height is right here, 5.8 and 4, right? So you have the width times the height. So 4 times 5.8 plus 6 times 4, right? So it could be 47.2. Now question D. Let S be a function such that the third derivative of S with respect to t is this one, right? So we have S triple prime of t equals t minus 3 to the 7. Write the 4th-degree term of the 4th-degree Taylor polynomial for S about t equals 1, right? So we need the 4th-degree terms, right? So we have the general term is going to be, now we need to find S4 of t, right? So it's going to be 7 times t minus 3 power of 6, right? We need to take derivative of this one, right? So S4 of 1, right? Because t equals 1 right here. It's going to be 7 times 1 minus 3 power of 6, right? So it could be 7 times negative 2 power of 6, right? So we're going to print up the calculator. 7 times 2 power of 6. The answer is 448, right? So we're going to substitute into this formula right here, right? So we have the 4th-degree term is f4 of c times s minus c to the 4 over 4 factorial, right? Now c in this situation is 1 right here, right? So we have f4 of 1 is going to be 448, right? So we have 448 times t minus 1 to the 4 over 4 factorial. Now we need to simplify, so it could be 448 times t minus 1 to the 4 over 24. So it could be divide the top bottom by 8. So it could be 56 over 3 times t minus 1 to the 4, right? Now, one of the primary goals of studying Taylor polynomials, and later in topic 10.14, Taylor series is to find a way to represent an ugly function as a prettier function that we can manipulate much easier. Alright, so we look at this one right here. This one is ugly function and it's going to be prettier function right here, right? We're going to explore topic 10.12, Lagrange error bound. Alright, we're going to talk about the remainder of a Taylor polynomial. Alright, so in the topic 10.11, we learned that the exact value of the function f(s) equals the polynomial approximation plus the error, right? Now the error, sometimes we call this one as the remainder. So then I'm going to subtract Pn of s both sides. I'm going to get this one right here. So the absolute value of the error equals the difference between the exact value and the approximation, right? And then we're going to use this inequality right here to find the range of f(s). Now we're going to talk about the Taylor formula and Lagrange error bound. Alright, if a function f is differentiable through order n plus 1 in an interval I containing value of c, then for each s in the interval I, there exists a number z between s and c such that f(s) equals the polynomial approximation plus the remainder, right? So remainder right here is the term after this guy, right? So which means it's going to be the n plus 1 derivative of s, right? Now, in this situation, it should be the value of z, where z between x and c. So how do you understand z? We're going to take a look at the example later, right? Over, this is n, the next term should be n plus 1 factorial, right? This is power of n, this one should be n plus 1, right? Now, the Taylor's inequality. We're gonna represent the error as a bound using the inequality, right? So it's gonna be exactly same thing as this guy right here. We just replace the equal sign with the less than inequality right here. The notation mass of n plus 1 derivative of f of c represent the largest value of n derivative of f of c will take on for a value of c that will typically lie between c and s. Now, example number 1, the third Markov polynomial for sine s is given by p sub 3 of s equal s minus s cubed over 3 factorial. Use Taylor's theorem to approximate sine of 0.1 by p sub 3 of 0.1 and determine the accuracy of the approximation. Alright, so this is Markov polynomial, which means the center equals 0, right? Alright, so we have sine of 0.1 is the same thing as p sub 3 of 0.1, right? Because we're going to use this one to approximate this guy, right? So it's going to be substitute 0.1 for s, right? So I have 0.1 minus 0.1 power of 3 divided by 3 factorial, right? So we're going to print up the calculator. 0.1 minus 0.1 to the third divide by 3 factorial, right? So you divide by 3 and you hit the button right here and hit the factorial and press Control Enter. It's going to be 0.099833, right? We're going to use the formula absolute value of the r sub 3 of s, right? Formula right here. Alright, so this is n, this guy must be n plus 1, this guy must be n plus 1, and this guy must be n plus 1, right? So keep that in mind. So this is r sub 3 of s. It's going to be less than or equal to absolute value of maximum, which means the largest value of f, the fourth derivative of z, right? This guy is 3, this guy must be 4, right? Over 4 factorial, right? Times s minus c to the 4, right? Now c equals 0 and s equals 0.1, right? So I'm going to replace this one with 0.1 minus 0, right? Alright. And then I'm going to simplify this guy, so it can be absolute value of. Now you know that the function f of s equals sine s, right? Now f to the 4, if you take the derivative, it's going to be around sine and cosine, that's it, right? F prime of s is going to be cosine s. And then f double prime of s is going to be negative sine s, right? And f triple prime of s is going to be negative cosine s. And the fourth derivative of s is going to be sine s again, right? And you know that absolute value of sine s always less than or equal to 1. Absolute value of cosine s always less than or equal to 1. So keep that in mind, right? So the maximum value of this one, it doesn't matter what the value of c is, right? Remember z between c and s, right? C right here equals 0 and s right here equals 0.1, right? So this guy doesn't matter at all. The sine cosine function maximum values always 1, right? So I have 1 over 4 factorial, which means 24, right? Times 0.1 power 4, right? It's going to be 0.00004, right? Determine the accuracies of the approximation. So the error is absolute value of the actual value, which means sine of 0.1. Subtract the approximation, it's going to be P3 of 0.1, right? So it's going to be absolute value of sine of 0.1 subtract this guy right here, right? So it could be 0.1 minus 0.1 cubed over 3 factorial, right? I'm going to print up the calculator. It's going to give me this value, right? And the error right here is going to be 4.16 times 10 to the negative 6, right? And this guy always less than or 3 of s, right? Which is the value right here. Now let's move on to question B. The 4-degree Markov polynomial for cosine s is given by this guy. If this polynomial is used to approximate cosine of 0.2, what is Lagrange error bound? Alright, so the key information right here, Markov polynomial, right? Which means the center c equals 0. Alright, keep that in mind. Now the s value right here is 0.2, right? This one is p sub 4, right? So we have r sub 4 of s always less than or equal to absolute value of maximum of the fifth derivative of z times s minus c power of 5 over 5 factorial, right? Now we're going to substitute values. It could be absolute value of maximum of the fifth derivative of z times s right here equals 0.2. Subtract c is going to be 0 power 5 over 5 factorial, right? Now the maximum right here equals 1, right? So we have absolute value of 0.2 to the fifth over 120, right? We're going to print up the calculator. 0.2 to the fifth divided by 120. And then press Ctrl Enter. It's going to give you 2.666 repeating, right? Times 10 to the negative 6, right? Now let's move on to question C. If the Taylor polynomial about s equals 0, so this is the center, right? Whenever we see about, this is the center, so c equals 0, right? Which means this guy becomes the Markov series, right? Markov polynomial, right? For the approximation of e to the s is given by this guy. What is the upper bound for the error in the approximation of e, right? So we need to find it's going to be less than or equal to absolute value of maximum. Now the function f of s is e to the s right here, right? So if you take the sixth derivative, it's still e to the s, right? And you know that the value of z is between c and s, right? C equals 0 less than z and s equals right here e only, which means e power 1, right? So when you match this guy and this guy, s equals 1, right? So if you exponentiate 3 sides, it's going to be e power 0, e power c, and e power 1, right? And the maximum right here, e power 1, right? So you have absolute value of e times s minus c, which means 1 minus 0 is going to be 1 power 6, right? Over 6 factorial, right? And then you're going to print up the calculator. 1 power of 6 is going to be 1, right? So you have e only raised to the first. Then you divide by 6 and you press the button right here. Pick the factorial, press Ctrl, Enter. The answer is 0.003775, right? Now, let's move on to question D. The function f has derivatives for all orders for all real numbers. The fourth derivative of s equals this guy. If the third degree Taylor polynomial for f above s equals 0 is used to approximate f on the interval 0, 1, what is the Lagrange error bound? Alright, so again, above s equals 0, which means c equals 0, and this guy becomes Lagrange polynomial, right? Look, the third degree Taylor polynomial, so you have R3 of s less than or equal to absolute value of maximum of, so it's going to be maximum of this one, again c less than z less than s, right? So c equals 0, s equals 1, right? If you need maximum of this guy, and then this guy maximum when cosine equals 1, right? So then you have e to the first times s subtract c is going to be 1 subtract 0 is going to be 1, 1 power 4 over 4 factorial, right? So you're going to print up the calculator. So you have e to the first divide by 24 and then press Ctrl Enter. It's going to be 0.11326, right? Now let's move on to example number 2. Find the third degree polynomial approximation for e to the s equals 1, center s 0, right? So this one s equals 1. This is c equals 0. Use the Taylor's inequality to find the range of possible values for e to the s equals 1, center s 0, right? So you need to find the polynomial approximation for this one first, right? This is third degree polynomial, right? So we have p sub 3 of s, right? So if you look at this one, this guy actually the second degree polynomial for e to the s, right? And then third degree polynomial, you just write s cubed over 3 factorial, right? So you have, now you need to approximate this one, so you have e to the first, right, s equals 1 right here, approximately p sub 3 of 1, right? So it's going to be 1 plus 1 plus 1 over 2 plus 1 over 6, right? And if you simplify this one, it's going to be 8 over 3, right? Now, since this one is the third degree polynomial, so we're going to use r sub 3 of s always less than or equal to absolute value of maximum, right? So we're going to simplify this one. It's going to be absolute value of, now we're going to exponentiate 3 sides, right? So we have e to the 0, e to the z, e to the first, right? This is the maximum, right? So it could be e times s minus c, which means 1 minus 0 is going to be 1 power 4 over 4 factorial should be 24, right? So it turned out to be e over 24, right? Now we're going to use the formula right here, right? So we have, now f of s equals e to the s and s equals 1. So it can be e to the first, right? So it can be absolute value of e minus, this is p sub 3, right? This is r sub 3, right? P sub 3 is going to be 8 over 3 less than or equal to e over 24, right? Now remember we have absolute value of s less than or equal to a, so negative a less than or equal to s less than or equal to a, so keep this one in mind, right? So we have negative e to the 24, right, less than or equal to e minus 8 over 3 less than or equal to e over 24, right? Now you're gonna add 8 over 3 sides, right? So you have, so if you hit the calculator, it's gonna be, and actually e is the Euler number, it's gonna be 2.71828 repeating, right? So the range right here makes sense, right? Now let's move on to example number 3. Determine the degree of the Taylor polynomial piece of n of s expanded about c equals 1. That should be used to approximate ln of 1.2 so that the error is less than 0.001, right? So we have the function f of s equals ln s, right? Now we're going to take the derivative of f of s, right? So f prime of s equals 1 over s, which means s power of negative 1, right? F double prime of s equals negative s power of negative 2, right? I just use the power rule. F triple prime of s equals 2 s power of negative 3, right? F for derivative of s is going to be negative 6 s power of negative 4, right? Etc. Now we need to generalize this one, so we have f n plus 1 derivative of s equals, alright? Now observe that you have, if this one, the first derivative, you have the plus sign. The second derivative, you have the negative sign. The third derivative, you have the plus sign. The fourth derivative, you have the negative sign, right? So if you see even right here, it should be negative. If you see odd derivative, it should be positive, right? So you have the negative 1 right here, right? And then we need to relate this guy with the negative side right here, right? So if you raise to the even power, it should be positive, right? If you raise to the odd power, it should be negative, right? But it's 4. And then this guy must be 3, right? This is 3, this guy must be 2. This is 2, this guy must be 1. So that you have the negative, positive, negative, right? So this is n plus 1, this guy must be n, right? That's the first thing. Now the second thing, look at this one, 4. This is it, right? So if you reduce this one by 1 unit, you get 3. And does that mean you have 3 factorial equals 6, right? This is third derivative, right? So I have reduce 1, it could be 2. So I have 2 factorial, it could be 2 right here, right? This is 2, it could be 1. So 1 factorial, it could be 1 right here, right? So this is n plus 1. So you have n factorial right here to get the coefficient, right? Now, we're going to deal with this guy right here. So this is 4 derivative, right? This is, does that mean it's going to be negative 6 over s power 4, right? So then this guy must be the same, right? So this guy right here and the bottom right here, s to the n plus 1 must be the same, right? Now we need to set up the error. So we have the error absolute value of r sub n of 1.2, right? Less than or equal to absolute value of maximum f n plus 1 derivative, right? Times s minus c raised to the n plus 1, right? Over n plus 1 factorial, right? Now c equals 1, s equals 1.2, right? So we have absolute value of maximum of this one. This could be right here, right? So we have negative 1 to the n times n factorial, right? Times s minus c, which means 1.2 minus 1 is going to be 0.2 raised to the n plus 1, right? Over s to the n plus 1. In this situation, it's going to be z, right? To the n plus 1. I forgot z right here, right? Where z between c and s, right? C equals 1, less than z, less than 1.2, right? Times n plus 1 factorial, right? Now we need this guy right here to be maximum. If this guy maximum, this guy right here must be minimum, right? So this guy minimum, look at this one, it should be 1, right? So we have absolute value of -1 to the n. When you take absolute value, it doesn't matter positive or negative right here, it should be positive, right? So you're going to end up with 0.2 to the n plus 1, right? Now the top right here and the bottom right here, this is n factorial, this is n plus 1 factorial. N plus 1 factorial can be written as n plus 1 times n factorial, right? So this guy cancel out, right? So the bottom should be n plus 1 only, right? Now at this time I can remove the absolute value side, right? Now the error must be less than this one, right? So I need this guy to be less than 0.001, right? Now n equals 1, substitute 1 for n over here. You get 0.02, right? N equals 2. You get 0.00267, right? This guy is still greater than 0.001. This guy is still greater than 0.001, right? Now n equals 3. You get 0.0004, which is less than 0.001, right? So n equals 3 is the final answer, right? Now let's move on to question B. What is the smallest order Taylor polynomial center f s equal 1, so which means c equal 1, right? Which will approximate e to the s minus 1, so we have f of s equals e to the s minus 1, right? On the interval 0, 3 with a Lagrange error about less than 1, right? So first you need to have the Taylor polynomial for this one, right? So you already learned in topic 10.11. If you don't know how to do it, just visit that videos, right? And we're gonna revisit this concept in topic 10.14, right? So now I'm gonna leave this one for you to practice. I'm gonna give you the answer for the Taylor polynomial, right? You have the error bound is gonna be given by the formula, and you know that z is between 1 and 3, right? And in order for this guy to be maximum, z must be equals 3, right? So substitute 3 for s into this one, right? So you have e to the 3 minus 1 is going to be e squared, right? So substitute over here. So the maximum should be e squared, right? Now s right here equals 3 and c equals 1, right? Raised to the n plus 1 over n plus 1 factorial, right? And then you're going to simplify this one. It's going to be e squared times 2 raised to the n plus 1 over n plus 1 factorial, right? We need this one to be less than 1, right? So we just get the table, right? So you have n right here, and this is r sub n of s, right? Now if n equals 1, you just use the calculator. You get e squared times 2 power of 2, right? Over 2 factorial. So it's going to be 14.778, right? Now n equals 2. You do exactly the same thing. You get 9.852. N equals 3. You get 4.926, right? N equals 4. You get 1.970, right? And n equals 5. You get 0.6568, right? Now finally, this number right here less than 1, so you stop, right? So n equals 5. Now let's move on to example number 4. The function g has derivatives of all orders for all real numbers s. Let t sub n of s be the third degree Taylor polynomial for g about s equals 1, so you have to center 1. The maximum values of the n derivative of g for s between 1 and 1.7 for selected values of n are shown in the table right here. What is the maximum error guaranteed by the Lagrange error bound when t sub n of s is used to approximate g of 1.7? So this one is s, right? So you have absolute value of r, this is third degree, right? So the error r sub 3 of 1.7 less than or equal to absolute value of maximum of f. This is 3, this guy must be 4 derivative, right? In this situation, the function is g, right? So I change this one to g of z, right, times s minus c to the 4 over 4 factorial, right? Now I just substitute value, so I have absolute value of maximum of g, the 4 derivative, right, of g times s equals 1.7, c equals 1 to the 4 over 4 factorial, this could be 24, right? Now the maximum right here, g4 derivative, is could be 3.7, right? So it could be 3.7 times 0.7 to the 4 over 24, right? So we're gonna print up the calculator. It's gonna be 0.037, right? Now let's move on to example number 5. It's gonna be exactly the same thing as example number 4, right? This one is third degree Taylor polynomial about s equals 2, so this is c equals 2, right? And then g of 1.5, so s equals 1.5, right? So we have r sub 3 of 1.5 less than or equal to absolute value of maximum of g for derivative of c times s minus c, right? S equals 1.5, c equals 2 raised to the 4, right? Over 4 factorial. So now the maximum right here. Now remember that z is between c and s, right? So between 1.5 and 2, right? So the maximum should be z equals 2, right? So g for derivative of 2 is right here, it could be 3, right? So you have 3 over 24, right? Times 0.5 raised to the 4, right? So we're gonna print up the calculator. So you have 3 times 0.5 to the 4. Then press Ctrl Enter. Divide by 24. Press Ctrl Enter. It's going to be 0.078, right? Now question 6 similar to question 5, right? So we look at this one right here, we see that the 4th degree Taylor polynomial, right? Center 1, so we have c equals 1, right? S equals 0.5, right? So you have absolute value of the remainder r sub 4 of 0.5 less than or equal to maximum of h, the fifth derivative, right, of z times s minus c raised to the fifth over 5 factorial, right? So it's going to be maximum of this one. Get the interval right here, alright? So maximum of this guy when z equals 1, right? So z equals 1, so h, the fifth derivative of s should be 2, right? So you have 2 times subtract c, which means 1 to the fifth over 5 factorial. Alright, so we're going to simplify this one. So it's going to be 1 over 2 and 2 right here cancel out. You have 2 to the 4 on the bottom, right? 2 to the 4 is going to be 16, right? And 5 factorial is going to be 120, right? So it's going to be 1920. And this guy actually less than 1200, right? So this one has been proved. Now let's move on to example number 7. The Taylor series for a function f about s equals 3. So this is the center, right? Is given by this series and converges to f for 0 less than equal to s less than equal to 5. If the third degree Taylor polynomial for f about s equals 3 is used to approximate f of 13 over 4. What is the alternating series error bound? Alright, so we look at this one actually the n terms, right? So we have a sub n equals, since this one, the third degree Taylor polynomial is used, right? So then you have the 4 terms, right? The 4 terms becomes n equals 4, right? So 3 times 4 equals 12 plus 1 is going to be 13 over 2 to the 4 is going to be 16 times s right here equals 13 over 4 subtract c, right? So it's going to be 13 over 4 subtract 3 raised to the 4, right? Now the alternating series error bound, so it could be absolute value of R3 of S, right? S equal 13 over 4 less than or equal to the next term, right? So which means less than or equal to 13 over 16 times 13 over 4 minus 3 raised to the 4, and that's the answer, right? Now let's move on to example number 8. Let f be a polynomial function with non-zero coefficients such that f of s equals this guy. T sub 4 of s is the 4th degree Taylor polynomial for f about s equals c such that t sub 4 equals this guy. Based on the Lagrange error bound, f of s subtract t sub 4 of s must be equals which of the following? Alright, absolute value of r sub 4, right? This is 4 degree of s equals absolute value of f of s right here. Subtract t sub 4 of s, right? And remember r sub 4, which means the next term, right? So the next term should be this guy right here, right? Let's move on to question B. Let f be a function that has derivatives of all orders for all real numbers, and let p sub 3 of s be the third degree Taylor polynomial for f about s equals 0, right? So you have the center c equals 0, right? Now you given this formula for n between 1 and 5 for all values of s. Of the following, which is the smallest value of k for which the Lagrange error bound guarantees that absolute value of f of 1 subtract p sub 3 of 1 less than or equal to k. P sub 3 of s be the third degree Taylor polynomial approximation, right? So we have r sub 3 of s right here is the Lagrange error bound, right? And this guy must be less than or equal to k right here, right? And this guy equals f for derivative, right? Of c s minus c raised to the 4 over 4 factorial, right? Less than or equal to k. Now we just substitute values. We need to find maximum of this guy, right? Now, since this guy less than or equal to n over n plus 1, right? So if it's equal, you just substitute the value of this one for n, right? So 4 for n, so it's going to be 4 over 4 plus 1 is going to be 5 times s equals 1, and then c equals 0 raised to the 4 over 4 factorial less than or equal to k, right? So it's going to be 4 over 5 times 4 factorial, right? 1 minus 0 raised to the 4 is going to be 1, right? Less than or equal to k, or k greater than or equal to 4 over 5 times 1 over 4 factorial, right? Now let's say smallest value, which means the minimum of this one, minimum when the equality occurs, right? So minimum is k equals 4 over 5 times 1 over 4 factorial. The answer is D. Now let's move on to example number 9. Alright, let P of S be the 6-degree Taylor polynomial, right? So we're going to use 6 of S, right? For a function f about s equals 0, so c equals 0, right? Information about the maximum of the absolute value of selected derivative of f over the interval 0 to 1.5 is given below, right? So this is 5th derivative, 6th derivative, and 7th derivative, right? Now, since you use the 6th degree Taylor polynomial to approximate, right? We need to use this guy, right? So we have set of s equals, now remember z between, now maximum is 4h1.3, right? So you have 4h1.3 times s equals 1.5, c equals 0, so it can be 1.5 raised to the 7 over 7 factorial, right? So you're going to print up the calculator. You have 481.3 times 1.5 raised to the 7, right? Then you need to divide by 7 factorial, right? So press the button right here, hit the factorial and press Control Enter. The answer is 1.631, right? Now let's move on to example number 10. Question 8. Write the 3rd degree Taylor polynomial for f about s equals 2, so you have c equals 2, and use it to approximate f of 1.5, right? So we have p sub 3 of s equals, now we substitute values, right? Now f of 2 equals 6, right? So it could be 6. F prime of 2 equals negative 12, so minus 12 times s minus 2, right? Because c equals 2. F double prime of 2 equals 18, right? So plus 18. 18 divided by 2, it could be 9, right? So 9 times s minus 2 squared, right? Plus f triple prime of c, it could be negative 24, right? Divided by 6 right here, because 3 factorial equals 6, right? So it could be negative 4 times s minus 2 power 3, right? So we have f of 1.5 is approximately p sub 3 of 1.5, right? Because the question wants you to use p sub 3 to approximate this one, right? So you substitute 1.5 for s over here and you print up the calculator, right? So if you use the calculator, the answer must be around 14.751, right? Question B. The fourth derivative of f satisfies the inequality for s greater than 1. Use the Lagrange error bound to show that the approximation found in part A differs from f of 1.5 by no more than 1/8, right? Now, in question A, we're going to use third degree Taylor polynomial, right? So the error should be absolute value of r sub 3 of 1.5, right? This guy less than or equal to. Now the maximum of for derivative of f is going to be right here, 48, right? So this guy equals 48 times negative 0.5 raised to the 4 over 4 factorial, right? We're going to simplify, right? So it could be 48 times negative side raised to the 4 is going to be positive, right? So I have 1 over 2 power 4 over 24, right? 48 divided by 24 is going to be 2, right? So you have 2 over 2 to the 4, right? So it could be 1 over 2 third, right? And this guy equals 1/8, right? So finally, we just prove that this guy less than or equal to 1/8, which is right here, right? Now let's move on to the last question, question 11. The function f has derivative of all orders for all real numbers. Value of f and its first four derivative at s equals 3 given in the table. Write an equation for the line tangent to the graph of f as equals 3 and use it to approximate this one. Okay, very simple, right? So we know that the slope intercept from y minus y1 equals m times s minus s1, right? So we have y minus y1. So you have x equals 3 and then y should be 4, right? Look. So you have y minus y1, y1 is 4, right? Minus 4 equals the slope. The slope is negative 8 right here. Times s minus 3, right? So you have f of 2.5 equals negative 8 times 2.5 plus 28, right? It's going to be 8, right? Now question B. Write the third degree Taylor polynomial for f about s squared 3, so c equals 3, right? So we have third degree is going to be p sub 3 of s equals. Now we're going to simplify this one. C equals 3, so you have f of 3 equal 4, right? F prime of c equals negative 8, right? So minus 8 times s minus c. F double prime of c is going to be 14 right here. Plus 14. 14 divided by 2 is going to be 7, so plus 7 times s minus c, which means minus 3 squared, right? So right here I just write 3, right? Now f triple prime of c is going to be negative 22, right? So minus negative 22 and this is 6. Divide the top bottom by 2. So negative 11 over 3, right? Times s minus 3 cubed, right? Now you need to approximate f of 2.5, right? So f of 2.5 approximately p sub 3 of 2.5, right? So it's going to be, if you use the calculator, the answer is going to be around 10.208, right? Now question C. Is there enough information to determine whether f has a critical point as s squared 2.5? In order for s equals 2.5 to be a critical point, you need f prime of 2.5 equal to 0, right? So we look at this one right here. We only have f of 2.5. We don't have f prime. And we look at the table right here. We actually don't have it, right? So we're going to say no. Now question D. the fourth derivative of f satisfies this inequality. For s greater than 2, use the Lagrange error bound to show that the approximation found in part B differs from f of 2.5 by no more than 1 over 8. Now this question is similar to question 10b. I'm going to leave this one for you to practice. Now let's move on to question E. What is the coefficient of the s minus 3 cubed term in the Taylor series for f prime, the derivative of f about s equals 3? Now remember that the n degree term in a Taylor polynomial is this guy right here, right? Where this guy is the coefficient, right? So we have, now observe that this guy right here is the derivative of the function f, right? So in order to get this guy, the function f must have the s minus 3 power 4 terms, right? So when you take the derivative, you're going to use the power rule. So it could be 4 times s minus 3 power 4 minus 1 is going to be 3, right? So, and in this situation must be 4, right? So we have f for derivative of c over 4 factorial times s minus 3 raised to the 4, right? Because it's center right here, right? So I'm going to look at the table right here. F for derivative of 3 is given in this table right here, 30, right? So you have 30 over 4 factorial times s minus 3 raised to the 4, right? Now I need to take derivative of this one, right? So I have f prime equals, bring 4 to the front, so it will be 30 over 4 factorial times 4 times s minus 3 raised to the third, right? Now the question asks you to find the coefficient only, so you only worry about this guy, right? So the coefficient is algebra 30 times 4 over 24, right? Now 4 and 24 cancel out, so 30 over 6 is going to be 5. That is the final answer. We're going to explore topic 10.13, radius and interval of convergence of power series. Alright, so in previous topic, we learned how to expand the Taylor polynomials, right? So remember, e to the s can be expressed as this guy right here, right? So this guy right here is called a power series, right? Now we're going to talk about the definition of power series. If S is the variable, then an infinite series of the form series a sub n s to the n, when n goes from 0 to infinity, equals, substitute 0 for n, we get the first term, 1 for n, we get the second terms, etc. Right? This one is called a power series. More generally, an infinite series of the form a sub n times s minus c to the n. Alright? If n equals 0, we get this guy. N equals 1, we get the second one, etc. Right? It's called a power series center SC, where C is a constant. The first one, center equals 0. Right? Now, let's take a look at the first example. State the values of C where each power series is centered. Alright, so we just rewrite this one as the series s minus 0 raised to the n over n factorial, right? When n goes from 0 to infinity, right? So in this situation, we're gonna match this guy and this guy up, right? So we have s minus c, right? So that means c equals 0, right? Now same thing, we have s minus c, right? So we just match this guy up. So c equals -1, right? Now we have s minus c, right? Match this guy up. So c equals 1, right? Now we're gonna talk about the radius and interval of convergence. There are three types of convergence of a power series. The first one, the power series converges at a single point. That's called the center. The second one, the power series converges at an interval. Right? It's gonna be center right here. Right? Go to the right, you add R. Go to the left, you subtract R. Right? R is called the radius of convergence. Number 3, the power series converges on the entire real number line. Right? So it could be the whole thing right here. Now we're going to talk about the theorem of convergence of a power series. For a power series center at C, precisely one of the following is true. Number 1, the series converges only at the center. Number 2, there exists a real number r greater than 0, such that the series converges absolutely for absolute value of s minus c less than r. Now we're going to expand this one. It turns out to be s minus c less than r, or greater than -r, right? Now I'm going to add c 3 sides, so I'm going to end up with c minus r less than s less than c plus r, right? And we look at this one right here. It's actually this guy right here, right? And diverges for absolute value of s minus c greater than r. This guy is the same thing as s minus c greater than r, or s minus c less than -r. Number 3, the series converges absolutely for all values of s, right? The number r is called the radius of convergence of a power series. Now, if the series converges only at the center, the radius of convergence is 0. If the series converges for all values of s, the radius of convergence is infinity. The set of all values of s for which the power series converges is the interval of convergence of the power series. Alright, so this theorem right here is extremely important. Alright, now we're going to apply this theorem into the example number 2. Find the radius of convergence for each power series. Question A. We need to use the ratio test, right? So we're going to set up the limit a sub n plus 1 over a sub n when n approaches infinity, right? So it's going to be limit when n approaches infinity of absolute value of n plus 1 factorial times s raised to the n plus 1 over n factorial times s raised to the n, right? Now we're going to simplify this one, so it could be limit when n approaches infinity absolute value of n plus 1 factorial can be written as n plus 1 times n factorial. So this guy cancel out, right? So you have n plus 1 left right here. Now this guy cancel out, you have s left right there, right? Over 1, right? So it's going to be limit when n approaches infinity. Now s not related to this one, I bring it to the front, right? So it could be absolute value of s right here. Absolute value of n plus 1, right? So it's going to be absolute value of s times infinity, right? So we conclude that the limit is infinite for all s different from 0. So the series diverges for all s different from 0, right? Now, when s equals 0, the series becomes n factorial times 0 raised to the n, right? So it could be 0, which is convergent, right? Therefore, the series converges only at s equals 0, and the radius of convergence is 0. Now let's move on to question B. We need to set up the limit, right? So it could be limit when n approaches infinity of absolute value of a sub n plus 1. It could be 3 times s minus 2 raised to the n plus 1 over a sub n. It could be 3 times s minus 2 raised to the n, right? Now 3 and 3 cancel out. This guy cancel out. You only have limit when n approaches infinity of absolute value of s minus 2, right? So it could be absolute value of s minus 2, right? Now, in order for this one to be convergent, this one must be less than 1, right? So we have s minus 2 less than 1 greater than negative 1, right? Now, we're going to add 3 sides. So it could be 1 less than s less than 3, right? Now, we're going to draw the number line. This one is the center, right? The center equals 2 right here, right? And then 3 right here, 1 right here. The distance from here to here is the radius, right? This is the radius. So the radius of convergence is 1, right? Now question C, same thing, right? We need to set up the limit. Absolute value of negative 1 raised to the n plus 1 times s raised to the 2n plus 1 like this over 2 parentheses n plus 1 and then plus 1 altogether factorial, right? Divide by a sub n, right? A sub n is this one, right? So we just check reciprocal of this one. So it could be 2n plus 1 factorial over negative 1 raised to the n times s raised to the 2n plus 1. Alright. Now, negative 1 raised to the n plus 1 can be written as negative 1 raised to the n times negative 1, right? This guy right here can be written as raised to the 2n plus 3, right? And then this one is going to be s raised to the 2n plus 1 times s squared, right? Now this guy can be written as 2n plus 3 factorial, right? So it could be 2n plus 3 times 2n plus 2 times 2n plus 1 factorial, right? Now we're going to simplify. Negative 1 raised to the n and negative 1 raised to the n gone, right? When you take absolute value of negative 1 right here, it becomes positive, right? So this guy gone. S raised to the 2n plus 1 right here and s raised to the 2n plus 1 right here cancel out, right? You only have s squared left, right? So we have limit of absolute value of s squared, right? When n approaches infinity. Now 2n plus 1 factorial and 2n plus 1 gone. You have this guy on the bottom, right? Now this guy right here not related to n right here. I bring it to the front, right? So have absolute value of s squared. Limit of 1 over 2n plus 3 times 2n plus 2, right? Don't forget to put this guy inside the absolute value side when n approaches infinity, right? Now n approaches infinity, this guy approaches 0, right? So 0 times s squared is going to be 0, right? 0 less than 1, right? So by the ratio test, this series converges, right? So we have radius is infinity. Now let's move on to question D. We're going to do exactly the same thing, right? We're going to set up the limit. 2 parentheses n plus 1 factorial, right? Times s raised to the 2 parentheses n plus 1 over n plus 1 factorial, right? Multiply by this one reciprocal, right? Remember a sub n plus 1 over a sub n, right? We're going to use the ratio test. So it could be n factorial over 2n factorial s raised to the 2n, right? When n approaches infinity. We're going to simplify this one. It's going to be 2n plus 2 factorial, right? So 2n plus 2 is going to be 2n plus 2 times 2n plus 1 times 2n factorial, right? Now this guy is going to be s raised to the 2n plus 2, right? And it's turned out to be s raised to the 2n times s squared, right? Now this one right here can be written as n plus 1 times n factorial, right? Now you have 2n factorial right here and 2n factorial cancel out, right? So we have limit when n approaches infinity, absolute value of, you have 2n plus 2 times 2n plus 1 left on the top, right? Now this one, this guy equal this guy, right? So you have s to the 2n and s to the 2n cancel out. You have s squared left, right? So s squared not related to this one, right? So I put absolute value of s squared in the front, right? Now you have n factorial right here and n factorial right here, right? So you have n plus 1 on the bottom, right? Now when n approaches infinity, the degree on the numerator is n squared, right? Degree on the denominator is just n, right? So this guy bigger than this one, the limit approaches infinity, right? So you have absolute value of s squared times infinity, right? So it's going to be infinity if s not equal to 0, right? So the series converges at s equals 0. And 0 is the center of this series right here, right? Because you can rewrite this one as s minus 0 raised to the 2n, right? Then by the theorem above, the radius of convergence is 0, right? Now when you find the interval of convergence, you must check the endpoints. So previously, we didn't check the endpoints until we learned this one right here, alright? So we have 6 different forms. First, the radius is 0 because it's convergent at the center C, right? The radius is infinity, which means the series converges on the real number line, right? The radius is R, right? You have the interval convergence, right? You have the open interval, right? You have the half closed interval right here, right? You have half closed interval right here, or you have the closed interval right here, right? Now example number 3, we're gonna find the interval of convergence for each power series, right? By the way, we're gonna find the radius of convergence, right? So we're going to use the ratio test, right? So we have limit absolute value of s raised to the n plus 1 over n plus 1 times this one reciprocal is going to be n over s raised to the n, right? When n approaches infinity, right? Now we're going to simplify this guy, right? So we have s left right here, right? We can print s to the front, right? So absolute value of s times limit of absolute value of n over n plus 1, right? When n approaches infinity, right? And then when n approaches infinity, number 1 right here doesn't really matter, right? So we have n over n, which means 1, right? So this is why I have f absolute value of s, right? Now in order for this one to be convergent, you need absolute value of s less than 1 by the ratio test, right? So then it's going to be -1 less than s less than 1, right? So this one is the interval of convergence for this power series, right? We're not going to stop right here. Be careful. We need to check the end points, right? We need to check this guy and this guy, right? Now, case number 1, s equals -1, right? So then we substitute -1 for s back to the original series right here. So we have -1 raised to the n over n when n goes from 1 to infinity. This guy actually alternating harmonic series, right? So it can be convergent. Now we're going to check the second case. S equals 1. So the series becomes 1 power of n over n when n goes from 1 to infinity. Now 1 power of n is actually 1, right? So I don't need this one, right? Now this guy divergent because this one is the harmonic series, right? Now we're gonna conclude. So we just rewrite this one. -1 less than s less than 1, right? We check the endpoints. This guy works, right? So we need to include the equal sign right here, right? This one doesn't work. We ignore it, right? So the answer is right here. This one is the interval of convergence for the power series, right? Now let's move on to question B, right? So we're gonna do the same thing, right? We're gonna set up the limit absolute value of -1 raised to the n plus 1 times s plus 1 raised to the n plus 1 over 2 raised to the n plus 1 divided by this one reciprocal, right? So 2 raised to the n over -1 raised to the n times s plus 1 raised to the n when n approaches infinity, right? Now we're going to simplify this one, right? -1 raised to the n and -1 raised to the n cancel out. You have -1 raised to the first left, right? So when you take absolute value, it's going to be positive, right? So I don't worry about this one anymore, right? Now, this guy and this guy cancel out. You have s absolute value of s plus 1 left on the top, right? I bring it to the front, right? I put limit when n approaches infinity right here, right? 2 to the n and it's 2 to the n plus 1. So I have absolute value of 1 over 2 left, right? So we have absolute value of s plus 1 over 2 like that, right? And then by the ratio test, this one convergent if this one less than 1, right? So then I'm going to multiply both sides by 2. So it could be absolute value of s plus 1 less than 2, right? It's going to be the same thing as -2 less than s plus 1 less than 2, right? I'm going to subtract 1 3 sides, so I'm going to end up with -3 less than s less than 1, right? Now I need to check the endpoints right here, right? So first case s equals -3, right? Substitute -3 for s back to the original one right here. So you're going to end up with the series -1 raised to the n times -3 plus 1 raised to the n over 2 raised to the n when n goes from 0 to infinity, right? Alright, so this guy is the same thing as -1 raised to the n. This one is -2 raised to the n, right? So I can combine them, right? It becomes 2 raised to the n, right? Over 2 raised to the n when n goes from 0 to infinity, right? And then this one equals, this series diverges by geometric series test because the common ratio is 1, right? Now we're going to check s equals 1. So the series becomes -1 raised to the n times 2 raised to the n over 2 raised to the n, right? When n goes from 0 to infinity, this guy cancel out, so it could be -1 raised to the n left right here, right? And this one diverges by geometric series because common ratio equals -1, right? Final answer is just this guy right here, right? Now let's move on to question C. So we're going to set up the limit, right? A sub n plus 1 equal to s raised to the n plus 1 over n plus 1 square times n square over s raised to the n, right? When n approaches infinity. So we're going to simplify this one. S raised to the n plus 1 and s raised to the n cancel out. We have s left, right? So absolute value of s outside. Limit when n approaches infinity of n square over n plus 1 altogether square, right? Now when n approaches infinity, you can remove number 1 right here by relative growth rate, right? So you have n square over n square is going to be 1, right? So you end up with absolute value of s, right? Now you need this one to be less than 1 so that the series converges, right? So then it's going to be the same thing as -1 less than s less than 1, right? Now you need to check the endpoints, right? So s equal -1. Substitute -1 for s back over here, so you have the series -1 raised to the n over n square, right? When n equals 1 to infinity, right? Now this one converges by alternating series tests, right? Now we're gonna check s equals 1, so we have the series 1 over n square. This one still converges by p series because p equals 2, right? Greater than 1. Alright, so finally the interval of convergence is -1 to 1. And you need to include the endpoints, right? Right here. This one is the final answer. Alright, now let's move on to question D. We do exactly the same thing. We're going to set up the limit, right? Absolute value of -1 raised to the n plus 2 times s minus 2 raised to the n plus 1 over n plus 1 times 2 raised to the n plus 1, right? Times reciprocal of this one, it could be n times 2 raised to the n over -1 raised to the n plus 1 times s minus 2 raised to the n, right? When n approaches infinity. Now this guy cancel out and you have -1 left. So when you take the absolute value of -1, it's going to be 1, right? Now this guy cancel out, you have s minus 2 on the top left, right? So we have the limit when n approaches infinity of absolute value of s minus 2 right here, right? N on the top and n plus 1 on the bottom, right? So we have n right here, n plus 1. 2 to the n and 2 to the n plus 1, you have 2 on the bottom, right? Now when n approaches infinity, this guy right here approaches 1, right? By relative growth rate, you can eliminate 1 right here. So n divided by n is going to be 1, right? So you're going to end up with s minus 2 over 2 absolute value, right? We need this one to be less than 1 so that the series converges, right? Now we're going to multiply both sides by 2. So we have absolute value of s minus 2 less than 2, right? This one the same thing as -2 less than s minus 2 less than 2. Add 2 three sides, so you have 0 less than s less than 4, right? Now we need to check the endpoints, right? So s equals 0. The series becomes, now we're going to simplify this one, so this one turns out to be the series negative 1 raised to the n times negative 1 raised to the first, right? So it could be negative 1 raised to the n times negative 2 raised to the n times negative 1, right? Over n times 2 raised to the n, right? So this guy right here, you can combine, it's gonna be 2 raised to the n, right? So this guy cancel out, right? So you're gonna end up with the series negative 1 over n, right? When n goes from 1 to infinity. This one diverges by the harmonic series, right? Now we're gonna check s equals 4. So we substitute 4 for s back to the original series. So we're gonna end up with the series n goes from 1 to infinity of negative 1 raised to the n plus 1 times 2 raised to the n over 2 raised to the n times n, right? This one cancel out, right? So we're gonna end up with the series negative 1 raised to the n plus 1 over n when n goes from 1 to infinity, right? This series converges by alternating series test, right? So we're gonna conclude the interval of convergence is 0 less than s less than 4, right? We need to include the endpoint right here, right? So this one is the final answer. Now let's move on to question E. We're gonna set up the limit of absolute value of 2 parentheses n plus 1 factorial, right? Times s over 3 raised to the n plus 1 divided by 2 n factorial times s over 3 raised to the n, right? So this guy turns out to be limit when n approaches infinity of absolute value of 2n plus 2, right? Factorial. Now s over 3 raised to the n plus 1, s over 3 raised to the n cancel out. You have s over 3 left on the top, right? The bottom is 2n factorial. So this guy turns out to be limit when n approaches infinity. The top becomes 2n plus 2 times 2n plus 1, right? And then you have 2n factorial cancel out, right? Times s over 3. Now when n approaches infinity, this guy approaches infinity, right? So the series only converges at the center. The center of this series is 0, right? Differentiation and integration of power series, right? So if you given the power series right here, you can take derivative of this one, right? So we're gonna use the power rule. We can bring n to the front, right? And n subtract 1. We're gonna end up with this guy right here, right? Similarly, you're gonna take antiderivative of this one using the power rule again, right? So you have 1 over n plus 1, right? This one, okay? And the power right here should be n plus 1, right? And when you take antiderivative, don't forget to add the constant c, right? Now the radius of the convergence of the series obtained by differentiating and integrating a power series is the same as that of the original power series, right? However, the interval of convergence may differ as a result of the behavior of the endpoints. Alright, let's take a look at this activity. Question 1. Given the series right here, write out an expression that includes the first 5 terms of the series, right? Now substitute 0 for n. So it could be s power of 0, it's going to be 1. 1 over 0 factorial is going to be 1, right? Remember 0 factorial equals 1 factorial and equals 1, right? So 1 divided by 1 is going to be 1. N equals 1 is going to be s power of 1 over 1 factorial is still 1, right? So you have s left. N equals 2. You have s squared over 2 factorial plus s cubed over 3 factorial, right? Plus s to the 4 over 4 factorial, right? The first 5 terms we can stop right here, right? Plus etc. Now, question 2, find derivative of this series, right? So f prime of s equals derivative of 1 equals 0, right? Derivative of s equals 1, right? Bring 2 to the front, you have plus 2s over 2 factorial plus 3s squared over 3 factorial plus 4s cubed over 4 factorial, right? Plus etc. Plus the general terms is going to be right here. Bring n to the front, right? So it could be n s raised to the n minus 1 over n factorial, right? Now we're going to simplify this one, right? So we have 1. 2 factorial is going to be 2, so it could be s, right? 3 factorial is going to be 6, right? So it could be s squared over 2 plus 4 factorial is going to be 24, right? So we have s cubed over 6, right? 6 which means 3 factorial, right? And right here I can put 2 as a 2 factorial, right? Plus etc. Now, question 3. What do you notice about f of s and f prime of s? Actually, they're both the same, right? So we have f of s equals f prime of s. And then the function should be f of s equals e to the s, right? Because when you take f prime of s, it's still e to the s. They're both the same, look, right? Now let's move on to example number 4. Interval convergence for f of s, f prime of s, and antiderivative of f of s. Alright. Find the intervals of convergence for each of the following f of s first, right? We're going to use the ratio test, right? So we have limit of absolute value of s raised to the n plus 1 over n plus 1 times n over s raised to the n, right? When n approaches infinity, right? Now, s raised to the n plus 1 and this one cancel out. You have s left, right? So it could be limit of absolute value of s when n approaches infinity. This guy right here equals 1, right? So it could be absolute value of s only. So it could be absolute value of s, right? Now, in order for this one to be convergent, you need absolute value of s less than 1, right? Or negative 1 less than s less than 1, right? Now, we're going to check the endpoints. So s equals negative 1, right? Substitute negative 1 for s back to original 1. We have a series negative 1 raised to the n over n. When n goes from 1 to infinity, this series converges by alternating series test, right? Now, check s equals 1. So you have the series when n goes from 1 to infinity of 1 raised to the n is going to be 1 over n, right? This series diverges by harmonic series test, right? So final answer is you're going to include negative 1, right? So it should be negative 1 less than or equal to s less than 1 only. Now question B, we need to check f prime of s, right? So we're going to use this one to take the derivative, right? So it could be series when n goes from 1 to infinity of n times s raised to the n minus 1 over n, right? So then it's going to be the series when n goes from 1 to infinity of s raised to the n minus 1 only, right? Now we're going to use the limit of a sub n plus 1 over a sub n, right? So a sub n plus 1 of this one should be s raised to the n over a sub n is going to be s raised to the n minus 1, right? When n approaches infinity. So it's going to be limit when n approaches infinity of absolute value of s, right? And then in order for this one to be convergent, you need this guy less than 1, right? So then you have -1 less than s less than 1, right? Again, you need to check the endpoints, right? Now I'm going to check s equal -1 first, right? So we have the series when n goes from 1 to infinity of -1 raised to the n minus 1, right? And this one diverges by the n terms test or divergent test, right? Now we're going to check s equals 1. So it turns out to be the series n goes from 1 to infinity of 1 raised to the n minus 1. Alright, it's still the same, right? It still diverges by the n-term test or divergent test, right? So finally, your answer should be this one only, right? Now question C. We're gonna take n times derivative of this one. So it could be the series n goes from 1 to infinity of s raised to the n plus 1 over n plus 1 times n, right? Now we're going to use the ratio test, right? So we're going to have limit absolute value of a sub n plus 1 over a sub n, right? So it could be s raised to the n plus 1 is going to be plus 2 over n plus 1 times n plus 2, right? Times reciprocal of this one, n times n plus 1 over s raised to the n plus 1, right? When n approaches infinity. Alright, we're going to simplify this one. It's turned out to be limit when n approaches infinity of absolute value of s, right? And then n plus 1 cancel out. You have n over n plus 2, right? When n approaches infinity, this guy right here approaches 1, right? So it could be absolute value of s left, right? And we need this one to be less than 1 so that the series is convergent, right? So we have s less than 1 greater than -1, right? We need to check the endpoint, so s equal -1. Substitute back over here. So we have the series n goes from 1 to infinity of -1 raised to the n plus 1 over n times n plus 1, right? And this series converges by alternating series test, right? Now, s equals 1. So we have the series 1 raised to the n plus 1 is going to be 1, right? 1 over n times n plus 1 when n goes from 1 to infinity. This series converges by direct comparison test, right? Because you can directly compare this one with the series 1 over n squared, right? But this series converges by p series, right? So final answer is this one works, so we need to include the endpoints, right? So it could be -1 less than equal to s less than equal to 1. This one is the interval of convergence, right? Now let's move on to example number 5. The radius of convergence for the power series is equal 1. What is the interval of convergence? Alright, so we know that the center C equals 4, right? Right here. The radius is 1, right? So you have the formula absolute value of s minus c less than the radius, right? So we're going to substitute value, so absolute value of s minus 4 less than 1, right? This one is the same thing as s minus 4 less than 1 but greater than -1, right? So add for 3 sides, so it could be 3 less than s less than 5, right? Now we're going to check the endpoints. So if s equals 3, substitute 3 for s back to the original power series. So we're going to end up with -1 raised to the even power. It could be positive, right? So it could be the series 1 over n when n goes from 1 to infinity, right? And this series diverges by harmonic series test, right? Now, s equals 5, and then the series becomes, so it's gonna be 1 over n, and this guy the same thing, diverges by the harmonic series test. So the answer is just this guy. Now let's move on to example number 6. If the power series converges as equals 8 and diverges as equals 10, which of the following is true? Alright, so we're going to draw the number line. We're going to label from 0 to 10. As for 8, the series converges. You know that at equals 10, the series diverges. You know the center is 5. So then the radius of convergence could be between the distance from here to here, 3, right? But less than 5, right? Now you're pretty sure that this one is the radius, right? So you're gonna count to the left 3 units, right? 4, 3, 2, so it could be right here. So this interval right here is called the interval of convergence. You're pretty sure that. But you don't know if the series converges at s equals 2, right? The endpoints. You don't know a sub n. So you cannot check this one, right? So number 1 right here, wrong, right? Maybe true, maybe false, right? Now number 2, the series converges as equals 3. Yes, 3 is inside of the interval of convergence right here. Number 2, correct. Number 3, the series diverges at s equals 0. You actually don't know if these values make the series converge or diverge, right? So this one wrong. So the answer should be B. Now let's move on to example number 7. The coefficients of the power series satisfy a sub 0 equals 6. A sub n equals this. For n greater than or equal to 1. What is the radius of convergence? Alright. So I'm gonna call this one B sub n, right? In order to find the radius of convergence, I need to use the ratio test, right? So I have limit absolute value of b sub n plus 1 over b sub n when n approaches infinity, right? So it's going to be limit when n approaches infinity, absolute value of a sub n plus 1 times s minus 3 raised to the n plus 1 over a sub n times s minus 3 raised to the n, right? Now, you don't know a sub n plus 1, you don't know a sub n, but you given this one right here, alright? So we're going to use this guy right here. You have a sub n equals this guy times a sub n minus 1. Now, if we take a sub n plus 1, so what happens? Does that mean it's going to be 2 times n plus 1 on the top, right? Over 3 times n plus 1 on the bottom, right? Times a sub n, right? Now divide both sides by a sub n and simplify the 1 right here. So it's going to be a sub n plus 1 over a sub n equals 2n plus 3 over 3n plus 4, right? So I'm going to substitute this ratio right here back over here, right? So I'm going to have limit when n approaches infinity, absolute value of 2n plus 3 over 3n plus 4, right? Times, you're going to simplify this and this, you have s minus 3 left, right? Now, when n approaches infinity, we're going to use the relative growth rate, right? We can ignore this and this, right? So then we're going to simplify n and n. The answer is 2/3, right? So it could be 2 over 3 times s minus 3, right? Put this guy inside absolute value, right? So in order for this series to be convergent, this guy must be less than 1, right? So we have 2 over 3 absolute value of s minus 3 less than 1. This guy is the same thing as, now multiply 3 side by 3 and a half, right? And add 3 side. So you're going to end up with 3 over 2 less than s less than 9 over 2, right? So we're going to draw the number line, right? So we have, this one is 3 over 2. This one is 4 over 2. 5 over 2. 6 over 2. 7 over 2. 8 over 2. And finally, 9 over 2, right? And observe that the center is right here, right? The distance from here to here is the radius, right? So radius is 9 over 2, subtract 6 over 2, it could be 3 over 2. And this one is the final answer. Now let's move on to example number 8. The radius of convergence for the power series is 5. What is the intervals of convergence? Alright, so we have the radius is 5, right? We have the center right here is 5, right? And we have the formula absolute value of s minus c less than or, right? Substitute value, so you have absolute value of s minus 5 less than 5, right? It's going to be the same thing as s minus 5 less than 5 greater than negative 5, right? Now you're going to add 5 3 sides, so it could be 0 less than s less than 10, right? Now we need to check for the endpoints, right? 0 and 10 right here. S equals 0, substitute 0 for s back to the original series. You're going to end up with n equals 1 to infinity of negative 1 raised to the n plus 1 times negative 5 raised to the n over n times 5 raised to the n. It's going to be the series negative 1 raised to the n plus 1. Negative 5 right here can be written as negative 1 raised to the n times 5 raised to the n, right? Over n times 5 raised to the n, right? Now you can combine these two guys right here, right? So it could be negative 1 raised to the 2n plus 1, right? And this guy cancel out, right? So it's going to be the series negative 1 raised to the 2n plus 1 over n, right? And you're pretty sure that 2n plus 1 is odd, right? So negative 1 raised to the odd power is going to be negative 1, right? So it could be the series negative 1 over n, right? And this guy actually harmonic series multiplied by negative 1, right? But harmonic series always diverges, right? Now we're going to check the endpoint s equals 10. Substitute 10 for s over here. So we have the series negative 1 raised to the n plus 1 times 10 minus 5, it could be 5 raised to the n over n times 5 raised to the n. This guy gone, right? So you're going to end up with the series negative 1 raised to the n plus 1, right? Over n. Now if n is odd, and then this guy becomes even, and this becomes 1. If n is even, and then this guy right here becomes odd, and then the whole thing right here becomes negative 1, right? So this one actually alternating series, right? Specifically, this guy actually alternating harmonic series, right? So we're gonna let b n equals 1 over n, right? So we're going to use alternating series test, right? So we're going to find the limit of 1 over n when n approaches infinity it's going to be 0, right? Moreover, you see that the series 1 over n decreasing as n increasing, right? You're going to include 10 only, right? You exclude s equals 0, right? So the answer must be D. Now let's move on to example number 9. Let a sub n equals 1 over n ln of n. For n greater than equal to 3, let f be the function given by fs equal 1 over s ln s. So this guy is the representation of this guy, right? Now the function f is continuous, decreasing, and positive. Use the integral test to determine the convergence or divergence of this series, right? So we're going to review the integral test. It's going to be right here. Suppose fs is positive, continuous, and decreasing on this interval. If this improper integrals convergence, so is the series. If this improper integrals divergence, so is the series, right? Now k in this situation is 3, right? So we have the integral form 3 to infinity of a sub n. It's going to be this guy right here, right? 1 over s ln s, right? Alright, so it's going to be limit when b approaches infinity of the integral form 3 to be 1 over s ln s ds, right? Now we're going to use u substitution, right? So we're going to let u be ln s, then du equals 1 over s ds, right? We're going to change the lower bound and upper bound, right? So we substitute over here. We have limit when b approaches infinity integral form ln 3 to ln b of 1 over u du, right? So then it's going to be limit when b approaches infinity of ln absolute value of u evaluated from ln 3 to ln b, right? So it's going to be limit when b approaches infinity of ln absolute value of ln b, right? Subtract ln absolute value of ln 3, right? Now when b approaches infinity, this guy approaches infinity, subtract ln of absolute value of ln of 3, right? So it's going to be infinity, right? Which is diverges by integral test. Find the interval of convergence of the power series right here, right? So we're going to use the ratio test, right? So we're going to take the limit of absolute value of a sub n plus 1 over a sub n when n approaches infinity. So it's going to be limit when n approaches infinity of absolute value of s minus 2 raised to the n plus 1 plus 1, it could be n plus 2, right? Over n plus 1 times ln of n plus 1. Divide by this one, which is you're going to multiply this one reciprocal, right? So it could be n ln of n over s minus 2 raised to the n plus 1, right? Now we're going to simplify this one, so we have limit when n approaches infinity of absolute value of this guy, simplify. You have s minus 2 on the top left, right? Times n over n plus 1, right? Times ln of n over ln of n plus 1. Alright, now when n approaches infinity, this guy right here approaches 1, right? This guy right here you just rewrite, right? So we have limit when n approaches infinity of absolute value of s minus 2 times ln of n over ln of n plus 1. Right? Now I'm going to do this one on the side. Right? So I'm going to take limit when n approaches infinity of ln of n over ln of n plus 1. Alright, when n approaches infinity, this guy approaches infinity over infinity. So this one is the indeterminate form, right? So I need to use the last below rule, right? So it's going to be limit when n approaches infinity of 1 over n over 1 over n plus 1, right? So to be limit when n approaches infinity of 1 over n times n plus 1 over 1, right? So to be limit when n approaches infinity of n plus 1 over n, right? We're going to use the relative growth rate, right? So to be limit of n over n when n approaches infinity is going to be 1, right? So finally, you're going to end up with absolute value of s minus 2, right? And in order for this power series to be convergent, this guy must be less than 1 by the ratio test, right? So it could be s minus 2 less than 1 greater than negative 1, right? At 2 3 sides, so it could be 1 less than s less than 3. Now, we need to check the endpoints, right? Now, s equals 1. Substitute 1 for s, so the series becomes. Now, this series converges by alternating series test. I'm going to leave this one for you to check, right? Now, we're going to check s equals 3. Then the series becomes, and then this guy becomes the series 1 over n ln of n, right? Now we're going to use the integral test to check to see if this series convergent or divergent, right? Which we did before right here, right? And it can be diverges by integral test, right? So s equal 3 doesn't work, right? But s equal 1 works, right? So finally, the interval of convergence is 1 less than or equal to s less than 3. Right? We're going to explore topic 10.14, finding Taylor and Maclaurin series for a function. Alright, in topic 10.11, we will have a chance to explore Taylor and Maclaurin series for a function. Now, in this topic, we're going to review those topics we learned in topic 10.11. Alright, we're going to talk about the theorem 10.14, form of a convergent power series. If a function f is represented by a power series fs equals this series for all s in an open interval I containing c, then a sub n equals the n derivative of f of c over n factorial n. We have the Taylor polynomial expansion right here. Alright, now if c equals 0 and then this guy gone, right? And it becomes the Maclaurin series, right? Keep in mind, Maclaurin series has the center c equals 0, and Maclaurin series is a special case of Taylor series. We have a tip. It's important to understand that the theorem 10.14 is saying that if a power series converges to f of s, then the series must be a Taylor series. It does not say that every series from this way will converge to some f of s. Alright. Example number 1. Find the Maclaurin series in summation form for the following functions and the interval of convergence for each series as well. Whenever you see Maclaurin series, it means the center equals 0, even though the question does not explicitly say that. Alright, so keep that in mind. Now we have fs equals psi s, and we have the formula right here. Alright, so first we need to find the first derivative, right? So we have f prime of s equals cosine s, f double prime of s equals negative sine s, f triple prime of s equals negative cosine s. Default derivative of s equals sine s, so I'm going to write it over here. Right, it's gonna go back to original one. The fifth derivative of s is gonna be this guy, right? The sixth derivative of s is gonna be this guy, and the seventh derivative of s is gonna be this guy, right? And the eighth derivative of s is gonna go back over here, right? Now we need to calculate f of 0, right? Because the center equals 0, so it could be 0. F prime of 0 is going to be 1. F double prime of 0 is going to be 0. F triple prime of 0 is going to be negative 1, right? So, the function sine s can be expanded as f of c, which means f of 0 is going to be 0, right? Plus f prime of 0 is going to be 1 times s minus 0 power of 1, right? Plus f double prime of 0 is going to be 0 over 2 factorial, so it could be 0, right? F triple prime of 0 over 3 factorial is going to be negative 1 over 3 factorial times s minus 0 power of 3, right? Plus the fourth derivative of 0 is going to be 0, right? Plus the fifth derivative of 0 is going to be 1, right? So you have 1 over 5 factorial times s minus 0 power of 5 plus the sixth derivative is going to be 0, right? Right here. And the seventh derivative is going to be negative 1 right here, right? Minus 1 over 7 factorial times s minus 0 power of 7, right? Etc. Now we're going to simplify this one. S minus 0 power of 1 is going to be s, right? Minus s power of 3 over 3 factorial, right? Plus s power of 5 over 5 factorial minus s power of 7 over 7 factorial, right? Plus etc. Now, the first term right here, I can write this one as s power of 1 over 1 factorial, so that I can see the product, right? Now, I need to write this series right here in summation form, right? So how do I do it? It's gonna be sine s equals summation and goes from 0 to infinity, right? Now I look at the top right here, I see that s, so I put s on the top. The first term right here, n equals 0, right? This one, n equals 1, n equals 2, n equals 3, right? So we look at the power right here, 1, 3, 5, 7, right? So we're going to write over here 1, 3, 5, 7, right? So this one corresponding to n equals 0, n equals 1, n equals 2, n equals 3, right? Now, look at this one. In order to get 3 from 1, I'm going to add 2, right? I'm going to add 2. I'm going to add 2. So this guy actually arithmetic sequence, right? With the common difference d equals 2, right? So explicit formula you learn from Algebra 1. A sub n equals a sub 1 plus n minus 1 times common difference, right? So then a sub n equals a sub 1 is going to be 3 right here, right? plus n minus 1 times common difference is going to be 2. Now I'm going to simplify this one. It's actually 2n plus 1, right? So I have s raised to the 2n plus 1. Now, since the exponent right here and the factorial right here, they're both the same, right? So this is 2n plus 1 right here. The bottom should be 2n plus 1 factorial, right? I see that this guy print the positive side. This guy is negative, positive, negative, positive, right? Which is the sign alternating, right? So I put negative 1 right here. Now, you have two different cases, either negative 1 raised to the n or negative 1 raised to the n plus 1. So, which one works for this situation, right? So, we look at this guy here. When n equals 0, you get the positive side, right? Substitute 0 for n right here, we get plus side. Substitute 0 for n right here, we get the negative side. So we're going to pick this guy, right? So it could be negative 1 raised to the n. Now, to find the interval of convergence, I'm going to leave this one for you to practice. Please visit the video in topic 10.13 to learn how to do it. Basically, you just use the ratio test, right? Now, question B. We're going to expand this one using the result from question A. So question A is right here. Alright, so we see that this is S, this is S. Now this is S squared. So we have sine S squared equals summation notation, n goes from 0 to infinity of negative 1 raised to the n. Now instead of S, you put S squared, right? So we have S squared all together raised to the 2n plus 1 over 2n plus 1 factorial, right? So it could be summation notation, n goes from 0 to infinity negative 1 raised to the n. S raised to the 4n plus 2 over 2n plus 1 factorial. That's it. This one is the final answer. Now, question C, we're going to use the result from question A to find the expansion for cosine S. Alright, now we have three methods. Method 1, we're going to do directly. Alright, we're not going to use the result from question A. We do exactly what we did right here. Right? So I'm going to leave method number 1 for you to practice. Now, method number 2, we have sine S is given by this one right here. Now, in order to find cosine, basically you just take derivative both sides with respect to S, right? Alright, so it could be cosine S equals 1 minus 3s squared over 3 factorial, right? Plus 5s to the 4 over 5 factorial minus 7s to the 6 over 7 factorial plus etc. Right? Now we're going to simplify this one. 3 factorial equals 3 times 2 times 1, right? So it's going to be cosine of S equals 1 minus 3 right here and 3 right here cancel out. You have 2 left, right? So it could be S squared over 2, right? Plus 5 factorial equals 5 times 4 times 3 times 2 times 1, right? And you have 5 right here, cancel 5 right here, right? So you have 4 times 3 times 2 times 1, which is 4 factorial, right? So S to the 4 over 4 factorial, right? Now 2, which means 2 factorial, right? Minus 7 factorial equals 7 times etc. times 1, right? So 7 and 7 right here cancel out, right? So we have s to the 6 over 6 factorial plus etc. right? So you have cosine s equals summation n goes from 0 to infinity, right? Now n equals 0, we get this guy right here. This is n equals 1, n equals 2, n equals 3, right? Now we look at the power. N equals 0, this is power of 0, right? N equals 1, power 2. N equals 2, power 4. N equals 3, power 6, right? And observe that this guy is an arithmetic sequence, right? With a common difference 2, right? So we have the n term a sub n equals a sub 1 plus n minus 1 times common difference, which is 2, right? So it could be a sub 1 equals 2 right here. So you have 2 plus 2n minus 2, it could be 2n, right? So this guy becomes s raised to the 2n, right? Now look at the top and bottom, they're both the same, right? So it could be 2n factorial, right? Now we look at the side right here, it could be alternating, right? This is plus sign, this is minus, plus sign, minus, right? So we have two different cases, right? Either negative 1 raised to the n or negative 1 raised to the n plus 1, right? Now look at the first one, when n equals 0, we get a plus sign, right? Which is, we're going to pick this one, right? So we have negative 1 raised to the n, right? This one is the final answer for the cosine function. Now we have method number 3. I'm going to start from here, this one right here. I'm going to start from here. Now, in order to find the cosine, I'm going to take derivative both sides with respect to s. Alright, so the left one becomes cosine function, right? Now the right side becomes summation and goes from 0 to infinity. Now I'm going to use the power rule, right? So I have negative 1 raised to the n. This one you just rewrite. Remember, you're going to take derivative with respect to s only, right? This one not related, just rewrite, right? Now use the power rule, so it could be 2n plus 1 times s raised to the 2n plus 1 subtract 1, it could be 2n only, right? Over 2n plus 1 factorial, right? Now observe that 2n plus 1 factorial, it could be 2n plus 1 times 2n factorial, right? So this one cancel out, right? So you have cosine s equals summation notation, n goes from 0 to infinity, negative 1 raised to the n times s raised to the 2n over 2n factorial. This one and this one match, right? Now let's move on to question C. We're gonna find the Maclaurin series in summation form for this one, right? Using the answer from question C. Alright, so we get this one right here, right? So basically, you just replace s right here with s squared. That's it, right? So we have cosine s squared equals summation notation, n goes from 0 to infinity, negative 1 raised to the n. Now instead of s, you put s squared, right? So you have s squared all together to the 2n over 2n factorial, right? Now we're going to simplify this one, so it could be summation notation, n goes from 0 to infinity, negative 1 raised to the n, s raised to the 4n over 2n factorial. This one is the final answer, right? Now, question E, similarly, we're going to use the answer from question C to answer this question, right? Now, this is cosine square of s. Remember, this guy and this guy completely different, alright? So, we're going to use half angle formula, right? We have cosine square of s equals 1 plus cosine 2s over 2. Alright, so it's going to be 1 half plus 1 half cosine of 2s, right? So I'm going to copy this one down over here. To find the cosine square of s, I just replace s right here with 2s right here, right? So I have 1 half plus 1 half, right? Times the sum of -1 times 2s raised to the 2n over 2n factorial. Remember, 2n must be inside parentheses, right? And this one is the final answer. Now, question F, we're going to do this one using the result from question C. So it can be right here, right? So I copy this one down over here. Now, I will multiply both sides by s, right? So it could be s cosine s equals -1 times s times s to the n. It could be s to the 2n plus 1, right? Over 2n factorial, right? This one is the final answer. Now go back to question C. We need to find the interval of convergence of this series. Alright, so we're going to use the ratio test, right? So we're going to have limit of absolute value of a sub n plus 1 over a sub n when n approaches infinity, right? So it's going to be limit when n approaches infinity, absolute value of this guy right here times this one reciprocal. So it could be 2n factorial over -1 raised to the n times s raised to the 2n. Now, -1 raised to the n plus 1 is going to be -1 raised to the n times -1, right? So this guy cancel out, right? And then when you take absolute value side, this guy becomes 1, right? So I ignore it. Now, this one can be written as s raised to the 2n plus 2, right? So then I can simplify with this guy right here, right? So I have s squared on the top, right? Now, this one turned out to be 2n plus 2 factorial, right? So then it's going to be 2n plus 2 times 2n plus 1 times 2n factorial, right? So 2n factorial and this guy cancel out, right? So the bottom becomes 2n plus 2 times 2n plus 1, right? Now I can bring s squared outside, right? Because it's not related, right? So I have, and then when n approaches infinity, this guy approaches 0, right? So it could be 0, 0 less than 1, right? So by the ratio test, this series converges, right? The interval of convergence is a real number, right? Now let's move on to example number 2. Find the Taylor and Maclaurin series in summation form for the following functions and the interval of convergence for each series as well. Alright, so we have the formula right here. Now, we need to take the derivative, right? So, f of s equals e to the s. Then, f prime of s equals e to the s. F double prime of s still e to the s. All the way to, for the derivative, it's still e to the s, right? So, f of 3 equals e cubed, right? F prime of 3 still e cubed, right? Now we're going to substitute into the formula right here. So we have e to the s equals f of c, which means e cubed right here, right? Plus f prime of c is still e cubed times s minus 3, right? Because c equals 3. Plus f double prime is going to be e cubed s minus 3 squared over 2 factorial plus e cubed s minus c cubed over 3 factorial plus e cubed s minus c to the 4 over 4 factorial, right? I forgot to write 3 over here, plus etc. So, e to the s equals summation n goes from 0 to infinity. Now, every single terms have the same thing, e cubed, right? So I just write e cubed right here, right? Times s minus 3, right? Over. Alright, now I need to find the power right here and something right here, right? So I look at this one right here. This is n equals 0, n equals 1. We have power of 1. N equals 2. You have power of 2 right here, right? So you see that this guy and this guy, they are the same thing, right? So you have this is power of n, right? N equals 0, we get the first term. N equals 1, we get this one, right? And this guy must be n, right? Now to find the summation form for the Maclaurin series of e to the s, we just ignore this one right here and this one right here, right? Because center equals 0, so e to the 0, it could be 1, right? So it could be summation s to the n over n factorial when n goes from 0 to infinity, right? So this one is Maclaurin series. Now to find the interval of convergence and radius of convergence, we're gonna find the limit of a sub n plus 1 over a sub n, right? That is the ratio test. So it could be limit when n approaches infinity. This guy cancel out, right? This guy cancel out. So we have absolute value of s minus 3 left on the top, right? The bottom you have n plus 1, right? When n approaches infinity, this guy approaches 0, right? So the interval of convergence is all real numbers, right? And the radius of convergence is infinity, right? Now for the Maclaurin series right here, you do exactly the same thing, you still get the same answer, right? Now question B, we're gonna use the Maclaurin series result from question A to do this guy and this guy, right? So we have the Maclaurin series e to the s equals, now f of s equals s squared e to the s, right? So we're going to multiply s squared both sides, right? So it could be summation n go from 0 to infinity s squared s to the n over n factorial, right? We're going to simplify this one, so it could be s to the n plus 2 over n factorial when n go from 0 to infinity, right? Now to find g of s equals s squared times e to the negative s. First, you need to replace s right here with negative s, and then you multiply s squared both sides, right? So we have the summation n go from 0 to infinity s squared times negative s raised to the n over n factorial, right? So it could be summation negative s raised to the n can be written as negative 1 raised to the n times s raised to the n, right? So then I combine this guy right here and this guy right here, right? So I have s raised to the n plus 2 over n factorial, right? And I have negative 1 raised to the n left right here, right? When n go from 0 to infinity. This one is the final answer for this guy, right? This guy is the final answer for this guy, right? Now let's move on to example number 3. Find the Taylor series in summation form for Ls equals Lns, center SC equals 1, and its interval of convergence. Alright, so we have the formula. Now f of s equals ln s then f prime of s equals 1 over s, which means s power of negative 1, right? F double prime of s equals negative s power of negative 2, right? F triple prime of s equals 2 s power of negative 3. The fourth derivative of s is negative 6 s power of negative 4, right? And the fifth derivative of s is 24 s power of negative 5, right? Now, you have f of 1 is going to be 0. F prime of 1 is going to be 1. F double prime of 1 is going to be negative 1. F triple prime of 1 is going to be 2. The fourth derivative of f of 1 is going to be negative 6. And the fifth derivative of f of 1 is going to be 24, right? So ln of s equals, substitute this value into the formula right here, right? So you have f of c is going to be 0, right? So it could be 0 plus f prime of 1 equals 1. So you have 1 times s minus 1 power of 1, right? Minus 1 times s minus 1 square over 2 factorial plus 2 times s minus 1 cube over 3 factorial. Subtract 6s minus 1 to the 4 over 4 factorial, right? Plus 24s minus 1 to the 5th over 5 factorial minus etc., right? Now we're going to simplify this one, so ln of s equals s minus 1 raised to the first over 1, right? Minus s minus 1 square over 2 factorial is going to be 2, right? Plus 3 factorial is going to be 3 times 2 times 1. 2 and 2 cancel out, so you have 3 left, right? So it could be s minus 1 cubed over 3, right? Minus 4 factorial, it could be 4 times 3 times 2 times 1. And then 3 times 2 equals 6. 6 cancel out, right? So you have s minus 1 power 4 over 4, right? Plus 5 factorial, it could be 5 times 4 times 3 times 2 times 1, right? So 4 times 3 times 2, it could be 24, and 24 cancel out. So it could be s minus 1 to the 5th over 5, right? So the summation form is going to be sigma n goes from 0 to infinity. Now, n equals 0, we get the first term. N equals 1, n equals 2, n equals 3, n equals 4, right? Look at the power right here. This is 2, this is 2, right? When n is equal 1. So does that mean you get s minus 1 raised to the n plus 1, right? Because if n equal 1, you get 2. So 1 plus 1 equals 2, right? Over this guy the same thing. So it could be n plus 1, right? Now, look at the side right here. It's going to be alternating, right? Remember, you have two different cases. Either negative 1 raised to the n or negative 1 raised to the n plus 1. Now, how do we know which one we're going to choose, right? So, observe that if n equals 0, we get the positive side, right? So, substitute 0 for n right here, we get 1. Substitute 0 for n right here, we get negative 1, right? So, we're going to pick the first one right here, right? So, we have negative 1 raised to the n, right? Now, to find the interval of convergence of this one, we're going to use the ratio test, right? So we have limit of a sub n plus 1 over a sub n, right? So it could be negative 1 raised to the n plus 1 times s minus 1 raised to the n plus 2 over n plus 2 times n plus 1 over negative 1 raised to the n times s minus 1 raised to the n plus 1, right? When n approaches infinity. Now, negative 1 raised to the n plus 1, and this one cancel out. You have negative 1 raised to the first left, right? So when you take absolute value, it's going to be positive, right? So I just ignore it. Now, s minus 1 raised to the n plus 2, and this one cancel out. So you have s minus 1 left on the top, right? So I can bring s minus 1 outside, right? I only have this guy left, right? So n plus 1 over n plus 2, right? Now, when n approaches infinity, I can ignore this guy, right? So n divided by n is going to be 1, right? So I'm going to end up with absolute value of s minus 1, right? So in order for this one to be convergent, this one must be less than 1 by ratio test, right? So it's going to be s minus 1 less than 1 greater than negative 1, right? Add 1 3 sides, so it could be 0 less than s less than 2, right? So this one is the interval of convergence, right? And the radius of convergence is going to be r equals 1, right? Because when you draw the number line, you have 0, 2 right here, and the center 1 right here, right? So this one is the radius. Now we need to check for the endpoint of the interval of convergence right here, right? So s equals 0. Substitute 0 for s over here. So we have, so this guy becomes negative 1 raised to the n and negative 1 raised to the n right here. It's going to be negative 1 raised to the 2n. It's going to be even power, right? So it could be positive, right? So it could be positive 1. I don't need to write 1, right? So I only have negative 1 raised to the first left, right? Over n plus 1 when n goes from 0 to infinity, right? Now we can rewrite this one as the series. We're going to start from 1, n equals 1 to infinity of 1 over n, right? I put the negative side in the front, right? Because negative 1 raised to the first is going to be negative side, right? So then I'm going to use the harmonic series test. This one diverges, right? Now I'm going to check s equals 2. So the series becomes, now 1 raised to the n plus 1 is going to be 1, right? So I only end up with the series ends go from 0 to infinity of negative 1 raised to the n over n plus 1. Alright, so I can rewrite this series as the summation. I'm going to start from 1 to infinity. Then negative 1 raised to the n becomes negative 1 raised to the n plus 1 over this one becomes n, right? So then I can use the alternating harmonic series test. This series converges, right? So s equal to works, right? So finally, your interval of convergence should be 0 less than s less than or equal to 2. Be careful. Now I have g of s equals 1 over 1 minus s, right? So it could be 1 minus s power of negative 1, right? So I can use the power rule and chain rule to find the derivative, right? So g prime of s equals negative 1 times 1 minus s power of negative 2 times negative 1, right? So it could be 1 minus s power of negative 2. Now g double prime of s equals negative 2 times 1 minus s power of negative 3 times negative 1, right? So it could be 2 times 1 minus s power of negative 3. Now g triple prime of s equals negative 6 times 1 minus s power of negative 4 times negative 1. So it could be 6 times 1 minus s power of negative 4 right? Now g for derivative of s is going to be negative 20 for 1 minus s power of negative 5 times negative 1. So it could be 20 for 1 minus s power of negative 5, right? Now, since this one is the Maclaurin series, which means the center C equals 0, right? So, g of 0 equals 1, right? G prime of 0 equals 1. G double prime of 0 equals 2. G triple prime of 0 equals 6. G for derivative of 0 equals 24, right? Now we have the formula. Now we just substitute value, right? So we have g of s equals 1 over 1 minus s is going to be, now g of 0 equals 1, right? Plus g prime of 0 equals 1 times s only, right? Plus g double prime of 0 equals 2, right? So we have 2 times s squared over 2 factorial, right? Plus g prime of 0 equals 6, right? So we have 6 times s cubed over 3 factorial plus 24 times s to the 4 over 4 factorial, right? Now we're going to simplify this one. So we have 1 plus s squared plus s cubed plus s to the 4, right? So to generalize this one, we have the summation notation. N's go from 0 to infinity, right? We just put s right here. Now n equals 0, we get 1. N equals 1, we get s. So this guy must be s to the n, right? And this guy is the infinite geometric series where a equals 1 right here, right? And the common ratio r equals s, right? In order for this infinite geometric series to be convergent, absolute value of common ratio must be less than 1, right? So then negative 1 less than s less than 1, right? So then you have the radius of convergence equals 1, right? Because when you draw a number line right here, negative 1, 1, and the center 0, right? So this one is the radius, right? Now let's move on to example number 4, Taylor and Maclaurin series coefficients. What is the coefficient of s to the 6 in the Taylor series about s equals 0 for the function right here? Alright, so basically this is Maclaurin series, right? So previously we already explained e to the s equals 1 plus s squared over 2 factorial plus s cubed over 3 factorial plus s to the 4 over 4 factorial, etc. Right? So in order to find this one, we need to replace s right here with 2s squared, right? Then divide by 2, right? So we have e to the 2s squared divided by 2. It's going to be 1/2 times 1 plus, replace this one with 2s squared plus 2s squared all together squared over 2 factorial plus 2s squared all together cube over 3 factorial plus 2s squared all together to the 4 over 4 factorial plus etc. Right? Now the question wants you to find the coefficient of s to the 6, right? So s to the 6 it could be right here, right? Because s squared and cube is going to be s to the 6. Now you only need to find the coefficient, right? So we just ignore this one, right? So it could be 2 cube over 3 factorial. Don't forget to multiply by 1/2 because 1/2 multiplied by the whole thing right here, right? So it could be right here. So 2 cubed, it could be 8. 8 divided by 2, it could be 4. 4 over 3 factorial, it could be 6. So it could be 2/3. Now, example number 5, very simple, right? In previous example, we read this one, right? So we just rewrite the expansion for sine s, right? So sine s equals s minus s cubed over 3 factorial plus s to the 5th over 5 factorial minus s to the 7 over 7 factorial plus etc. right? Now you need 3s, so you just replace s with 3s, right? And then you multiply both sides by s, right? So I have s sine 3s, right? So instead of s right here, I put 3s, right? Minus 3s altogether cubed over 3 factorial plus 3s altogether to the 5th over 5 factorial minus 3s altogether to the 7 over 7 factorial plus etc. right? The whole thing right here multiplied by s, right? Now we just distribute this one, right? So we have 3s squared, 3 cubed, it could be 27, right? 27 s to the 4 over 3 factorial. Now 3 to the 5th, it could be 243, right? So 243 times s to the 6th, right? Because you have s and s to the 5th right here. Over 5 factorial. Minus 3 to the 7th, it could be 2187, right? S to the 7 and s right here, it could be s to the 8 over 7 factorial, right? Now, write the first 4 non-zero terms, right? So this could be 1, 2, 3, 4, it works, right? And the question say about s equals 0, which means this one is the Maclaurin series, right? Now question B, what is the Maclaurin series for 1 over 1 minus s squared, right? So we have 1 over 1 minus s altogether squared. It's going to be 1 over 1 minus s times 1 over 1 minus s, right? Now, in previous example, right here, we just did right here, 1 over 1 minus s. And we got this one right here, right? And the answer is right here, right? So basically, you have the summation n go from 0 to infinity of s to the n times summation n goes from 0 to infinity of s to the n, right? So it's technically it's gonna be 1 plus s squared plus s cubed plus s to the 4 etc. times 1 plus s squared plus s cubed plus s to the 4 etc. right? Now you need to multiply this one out using distributive property, and you need to write the first 4 non-zero terms, right? So when you simplify this one, the answer must be 1 plus 2s plus 3s squared plus 4s cubed, right? I'm gonna leave this one for you to verify. Now question C, what is the Maclaurin series for this function, right? So remember, we have the expansion for e to the s. It's gonna be, so e to the negative s, you just replace s with negative s, right? So we have 1 plus negative s plus negative s squared over 2 factorial plus negative s cubed over 3 factorial plus etc. right? Now observe that when you have the even exponent, this guy becomes positive. When you have the odd exponent, this guy becomes negative, right? Now if you add this guy up vertically, right? So you have e to the s plus e to the negative s equals 1 plus 1 equals 2, right? S and this one cancel out. The odd power terms is going to be gone, right? So we only have the even power terms, right? S squared over 2 factorial. This guy, the same thing. So when you add them up, you need to multiply by 2 here, right? Similarly, you have 2s to the 4 over 4 factorial, right? Plus 2s to the 6 over 6 factorial, right? Now we need 4 non-zero terms, right? And then you need to multiply both sides by 1/2, right? So I have 1/2 right here, multiplied by this guy. And then this guy must be divided by 2, right? So the final answer is 2 divided by 2 is going to be 1, right? Plus s squared over 2 factorial. Plus s to the 4 over 4 factorial. Plus s to the 6 over 6 factorial. This one is the final answer, right? Now, question D. Find the Markov series for the function ls equals cosine square root of s, right? So remember, we did this one before. Cosine s equals 1 minus s squared over 2 factorial plus s to the 4 over 4 factorial minus s to the 6 over 6 factorial, right? Plus etc. So you have cosine square root of s. You just replace s with square root of s, right? So it will be 1 minus square root of s altogether square over 2 factorial plus square root of s power 4 over 4 factorial minus square root of s power 6 over 6 factorial, right? Now we just simplify this one and we're done, right? So it could be 1 minus square root of s squared is going to be s, so s over 2 factorial, right? Square root of s power 4 is going to be s squared, right? So s squared over 4 factorial. And minus square root of s power 6 is going to be s cubed over 6 factorial. This one is the final answer. Now question E, similarly, right? You have the expansion for sine s equals, now you just replace s with phi s, right? So we have sine of phi s equals phi s minus phi s altogether cube over 3 factorial plus phi s to the 5th over 5 factorial minus phi s to the 7 over 7 factorial, right? Now, question F, very simple, right? I'm going to leave this one for you to practice, right? Basically, you just write out sine s, right? And then you divide both sides by s, right? I just give you the answer, right? So the answer should be 1 minus s squared over 3 factorial plus s to the 4 over 5 factorial minus s to the 6 over 7 factorial. It's your responsibility to verify this answer, okay? Now, question G, very simple. You just write out cosine s equals, right? And then you add both sides by 1 plus s squared. Alright, so I just leave this one for you to practice. Now, it's your responsibility to verify the answer. The answer should be 2 plus s squared over 2 plus s to the 4 over 4 factorial minus s to the 6 over 6 factorial, right? Now question H, similarly, right? So we have sine s, right? And then you just replace s with s squared. And then you divide both sides by s. And you write out the formula for cosine s. And then you add this guy up, right? And I leave this one for you to practice. I will leave the answer for you to verify, right? So the answer must be 1 plus s minus s squared over 2 factorial plus s to the 4 over 4 factorial. Now let's move on to example number 6. Find the sum of series. Alright, so for this one, it's going to be summation. N goes from 0 to infinity, right? N equals 0. This is n equals 1, n equals 2, n equals 3, etc., right? So you have the general terms right here, right? So you write 3 to the n over n factorial, right? Actually, 3 doesn't change, right? And you look at the power right here. The top and bottom should be the same, right? So this is n, this is n factorial, right? So you need to relate it to e to the s. Remember, you have the formula e to the s equals summation n go from 0 to infinitive of s to the n over n factorial, right? So we look at this one, we have 3 right here, so we just replace s with 3, right? So it turns out to be e to the third equals summation 3 to the n over n factorial when n goes from 0 to infinity, right? So the answer must be e cubed. So the answer must be B. Now question B similar to question A, right? It's same thing, right? So we have e to the s equal summation n goes from 0 to infinity s to the n over n factorial. You just replace s with ln 3, right? So it could be summation n go from 0 to infinity ln of 3 to the n over n factorial, right? So in this situation, you have e to the s becomes e to the ln of 3, right? So then it's going to be 3, right? Now question C. What is the sum of the infinite series, right? Now observe the general terms right here. This guy similar to the expansion of the sine function, right? So we have the sine function is going to be summation n go from 0 to infinity of -1 raised to the n s raised to the 2n plus 1 over 2n plus 1 factorial, right? And we look at the bottom right here, it's going to be the same, right? The top right here, this guy is still the same, right? Now look at this one, we only have the power 2n, this is 2n plus 1, right? So we just divide both sides by s, right? So we have sine s divided by s. It's going to be summation n go from 0 to infinity of -1 raised to the n s raised to the 2n over 2n plus 1 factorial, right? Now we have this guy the same thing, right? Look at the formula right here, actually s equal pi over 2, right? So we just let s equal pi over 2, right? So then you have sine of pi over 2 over pi over 2. Sine pi over 2 equals 1, right? So 1 divided by pi over 2 is going to be 2 over pi, right? Now let's move on to example number 7. Which of the following is the Maclaurin series for the function s cosine 2s, right? So first you need to write out the expansion for the cosine s, right? Then you replace s with 2s, right? So you have cosine 2s. And then you multiply both sides by s, right? So you have s cosine 2s. And then you get the answer, right? So I leave this one for you to verify, right? I just give you the answer. The answer must be C. Question B. Find the Maclaurin series of this one represent the function f of s, right? So it's give you the answer right here, sine s, negative sine s, this guy and this guy. Alright, so we already did this one before, right? Now first choice A, we have sine s is s minus s cubed over 3 factorial plus s to the 5th over 5 factorial minus s to the 7th over 7 factorial, right? And you look at this one, all positive side, right? So this is wrong, right? Now B, negative sine s, you just multiply both sides by -1, right? And you have negative s plus s cubed over 3 factorial, right? Etc. And you have the negative positive, the sign alternating, is still wrong, right? Now C, you have e to the s minus e to the negative s, and you multiply both sides by 1/2, right? This one you did it before. Example number 5, C. Alright, so I just leave this one for you to practice. The answer must be C. Now let's move on to example number 8. This one is the AP style question. The function f satisfies the function f prime of s equal f of s plus 1 and f of 0 equal 2. The Taylor series for f about the s equal 0 converges to f of s for all value of s. Question A. Write an equation for the tangent line to the curve y equal f of s at s equal 0. So remember we have y minus y1 equals m times s minus s1, right? And then it's going to be y minus f of 0 equals f prime of 0 times s minus 0, right? So we have f of 0 equals 2, right? And f prime of 0, we're going to use this one right here, equals f of 0 plus 1, right? F of 0 equals 2, so it could be 3. So equation should be y minus 2 equals 3 times s minus 0, or y equals 3s plus 2, right? Question B. Find f the program of 0 and find the second degree Taylor polynomial for f about s equals 0, right? So we have f prime of s is right here, right? F prime of s is f of s plus s plus 1. Then f double prime of s equals f prime of s plus 1, right? And then you have f double prime of 0 equal f prime of 0 plus 1. It's going to be f prime of 0 equals 3 right here. So 3 plus 1 equals 4, right? Now, second degree Taylor polynomial. So you have p2 of s equals f of 0 plus f prime of 0 times s plus f double prime of 0 times s squared over 2 factorial, right? Remember the center equals 0, which means this one is the Maclaurin series, right? So then you have f of 0 is going to be 2 right here, plus f prime of 0 equals 3 right here, and f double prime of 0 equals 4 right here. 4 divided by 2, it could be 2 s squared, right? Now find the 4 degree Taylor polynomial for f about s equals 0, right? So we need to calculate f triple prime of s. So we go back over here. It's going to be f double prime of s right here, right? And the 4 derivative of s is going to be f triple prime of s, right? So we need to calculate f triple prime of 0 equal f double prime of 0, and f double prime of 0 equals 4 right here, right? Now f for derivative of 0 equal f triple prime of 0 is still 4 right here, right? So you have p4 of s equals f of 0 plus f prime of 0 times s plus f double prime of 0 times s squared over 2 factorial, right? Plus f triple prime of 0 s cubed over 3 factorial plus f for derivative of 0 s to the 4 over 4 factorial, right? So we just plug in values, right? F of 0, the first 3 terms right here, we got it above right here, right? So we just copy them down. Plus f triple prime of 0 equals 4 right here. So you have 4 and 3 factorial, it could be 3 times 2 times 1. 4 divided by 2, it could be 2. So it could be 2 over 3 s cubed, right? 4 factorial equals 4 times 3 times 2 times 1, right? 4 derivative of f is going to be 4 right here. 4 and 4 cancel out. So it's going to be plus 1 over 6 s to the 4, right? This one is the final answer. Now question D. Find the n derivative of f about s equals 0 for n greater than or equal to 2. Alright, so we look back over here. We see that f triple prime of s equals f double prime. F for derivative of s equals f triple prime, right? So the n derivative of f is still 4 right here, right? Now we just generalize the formula, right? It's right here. This is expansion for f of s, right? So we have f of s equals 2 plus right here 3s plus 2s squared. Alright, f triple prime of 0 equal 4, right? So I have plus 4 over 3 factorial times s cubed, right? Plus 4 over 4 factorial times s to the 4, right? Plus etc., right? Now I need to calculate this guy, right? I know that e to the s equals 1 plus s squared over 2 plus s cubed over 3 factorial plus s to the 4 over 4 factorial, right? So then I multiply both sides by 4, right? So this guy 4, this guy becomes 4, this is 4, right? So I have f of s minus 4 e to the s equals 2 subtract 4, it could be negative 2, right? 3s subtract 4s, it could be negative s, right? Now 4 divided by 2, it could be 2, so I have 2s squared and 2s squared cancel out, right? Now 4 over 3 factorial, this guy 4 over 3 factorial, s cubed, this guy cancel out, this guy cancel out, so you only end up with this guy is the final answer, right? Now let's move on to example number 9. This question comes from IB Calculus BC Operation Exam FRQ number 6 in 2016. The function f has a Taylor series about s equals 1. Right? So first we need to write the formula. F of s equals that converges to f of s for all s in the interval of convergence. It's known that f of 1 equals 1, f prime of 1 equals negative 1 half, and the n derivative of f s equals 1 is given by the formula right here. For n greater than or equal to 2, write the first for non-zero terms and the general terms for the Taylor series for f about s equals 1. Right? So we need to calculate f double prime, right? Because you given the first two terms right here already, right? F double prime of 1, we're going to use the formula right here. Negative 1 square times 2 minus 1 factorial over 2 square, right? So it could be this one equals 1. 2 minus 1 equals 0. 0 factorial equals 1. So it could be 1 over 4, right? Now, f triple prime of 1 equals negative 1 cubed times 3 minus 1 factorial over 2 cubed, right? So it could be negative 1 cubed, it could be negative side, right? 3 minus 1, it could be 2. 2 factorial, it could be 2, right? 2 over 8 is going to be 1 over 4, right? So it could be negative 1 over 4. So we plug this guy into the formula right here, where c equals 1, right? So we have f of s equals f of 1 plus f prime of 1 s minus 1 plus f double prime of 1 times s minus 1 square over 2 factorial plus f triple prime of 1 s minus 1 cube over 3 factorial, right? Now we just plug in values, right? So we have f of s equals f of 1 equals 1. F prime of 1 equals negative 1 half, right? So we have negative 1 half times s minus 1, right? Now f double prime of 1 is 1 over 4, right? And you have 2 factorial right here. So it can be 1 over 4 times 2 factorial s minus 1 square, right? Now f triple prime of 1 equals negative 1 over 4, right? So minus negative 1 over 4 times 3 factorial, right? So I can rewrite this one as 2 over 8 times 3 factorial s minus 1 cube, right? Now question B. The Taylor series for f about s equals 1 has a radius of convergence r equals 2. Find the interval of convergence. Remember we have the formula as minus c. Absolute value of this one must be less than the radius, right? We just substitute values, absolute value of s minus 1, right? C equals 1 right here. Less than 2, right? It's the same thing as negative 2 less than s minus 1 less than 2. Add 1 3 sides, so it could be negative 1 less than s less than 3, right? Now we need to check for the endpoints right here, right? Now substitute negative 1 for s into this one right here. So we have, now we're going to simplify negative 1 raised to the n times negative 2 raised to the n is going to be 2 raised to the n, right? So this guy, and this guy cancel out, right? The top becomes n minus 1 factorial, right? And this is n factorial. If we simplify this one, it could be n minus 1 factorial over n minus 1 factorial times n, right? So it could be 1 over n, right? And this guy actually harmonic series, right? So it could be divergent, right? Now s equals 3 right here. So we have negative 1 raised to the n times n minus 1 factorial over 2 raised to the n times n factorial times 3 subtract 1 is going to be 2 raised to the n, right? So this guy cancel out, right? So it could be negative 1 raised to the n over n only, right? And this one convergent by alternating harmonic series, right? So the final answer is negative 1 less than s less than or equal to 3. Now let's move on to question C. The Taylor series for f about s squared 1 can be used to represent f of 1.2 as an alternating series. Use the first three non-zero terms of the alternating series to approximate f of 1.2, right? So the first three non-zero terms is right here. Right, so this guy is the same thing as p sub 2 of s, right? Look, the power right here, 2. So it could be 1 minus 1 over 2 s minus 1 plus 1 over 4 times 2 factorial s minus 1 square, right? So then f of 1.2 approximately p sub 2 of 1.2. So it could be 1 minus 1 half, 1.2 minus 1 plus 1 over 8 times 1.2 minus 1 square, right? So it's going to be 1 minus 1 half times 0.2, right? Plus 1 over 8 times 0.2 square, right? So it's going to be 1 minus 0.1, right? Plus 0.005, and it's going to be 0.905, right? Now question D. Show that approximation found in part C is within 0.001 is the same thing as 1 over 1000, right? Of the exact value of f of 1.2, right? So we have the general terms of the series is right here. And this guy actually the alternating series with terms decreasing to 0, right? Now we're going to check the limit of this one. So we have limit when n approaches infinity of 1 over 2 to the n times n. Now substitute 1.2 for s, so it could be 0.2 raised to the n, right? So it's going to be limit when n approaches infinity 0.2, I can write as 2 over 10, right? So I have 2 to the n over 2 to the n times 10 to the n, right? So then this guy cancel out, right? So I have limit when n approaches infinity of 1 over n times 10 to the n, right? And it's going to be 0, right? So we're going to apply the alternating series error bound, right? So we have absolute value of f of 1.2 minus e sub 2 of 1.2 less than the absolute value of the first omitted term, right? So that one is right here, right? Alright, so we're going to simplify this one. 0.2 cubed, it could be 0.008, right? 2 over 8 could be 1 over 4. 4 times 6, it could be 24, right? So 0.08, you can rewrite this one as 8 over 10 cubed times 24, right? Now 8 over 24, it could be 1/3, so it could be 1 over 3,000, right? And this guy actually less than 1 over 1,000, right? We're going to explore the last topic of AP Calculus BC. Topic 10.15, representing functions as a power series. Alright, in the last topic, topic 10.14, you already learned how to expand the following function using Taylor polynomial expansion and Maclaurin expansion. Now, you strongly recommend it to memorize the following function, as they commonly feature on the AP Calculus BC exams. Now, we're going to learn how to represent a function with a power series. We have geometric series given by this formula, right? If absolute value of r less than 1, then the series converges to the sum right here. Remember, r is the common ratio and a is the first term. If absolute value of r greater than or equal to 1, then the series diverges. Alright, this guy is the same thing as r less than 1 greater than -1. This guy is the same thing as r greater than or equal to 1 or r less than or equal to -1, right? Now, if we replace a with 1, r with s, then the series right here becomes this guy. So we can represent the function fs equals 1 over 1 minus s with a power series. The sum of s to the k when k goes from 0 to infinity, where absolute value of s less than 1, then the power series converges. Alright, let's take a look at the first example, finding a geometric power series center h0. Find a power series for Ls equals 4 over s plus 2, center h0, and state its interval of convergence. Alright, now we have f of s equals 4 over s plus 2, right? Now we look at the power series right here. Alright, the bottom right here must be in this form 1 minus s. Alright, so I'm going to rewrite this one as 4 over 2 minus -s, right? And then I'm going to divide the top and bottom by 2, so that I'm going to get 1 right here, right? So it's going to be 2 over 1 minus -s over 2, right? Now I'm going to compare this guy right here with the formula right here, right? So does that means -s over 2 equivalent to this guy right here, right? So you can conclude that this guy is an infinite geometric series with a equals 2, right? It's right here. And the common ratio r right here equivalent to this guy right here, -s over 2, right? So f of s can be written as the first term is 2, right? Plus the next term is going to be the first term multiplied by common ratio, which is -s over 2 right here, right? Plus 2 times -s over 2 power of 2, right? You're going to multiply by -s over 2 each time, right? Plus 2 times negative s over 2 power of 3, right? Plus etc. Plus 2 times negative s over 2 power of n, right? So we're going to simplify. So it could be 2 and 2 cancel out. It could be minus s, right? 2 and 4 cancel out. So it could be 2, right? And then negative s squared, it could be s squared, right? So it could be plus s squared over 2. Similarly, it could be negative s cubed over 2 squared, right? Plus s to the 4 over 2 cubed, plus etc. Plus, now the general term, it should be s to the n. You look at this one right here. The power right here and the power right here, difference by 1, right? So this is s to the n. This guy must be 2 power of n minus 1, right? Now you look at the side right here, it's alternating, right? Look, positive, negative, right? So you're gonna put negative 1 right here. Now you have two different options, either negative 1 raised to the n or negative 1 raised to the n plus 1, alright? So we look at the first term right here. This is n equals 0, right? So n equals 0, substitute over here, it's going to be negative 1 power of 0, it's going to be 1, which is positive, right? This is negative 1, which is negative, right? But the first term right here positive, so we should pick the first case right here, right? So it should be n right here, right? Now you're gonna print up the calculator to check your work. Alright, you're gonna hit the button right here. Alright, pick the Taylor right here. Now you're gonna hit the button right here to pick the fraction right here. Alright, so you just input the function fs 4 over s plus 2. Now put a comma, then you're gonna define the variable s. Put a comma. Now the next number should be the highest degree of the power series, right? So I want to see the highest degree of the power series 5. I'm gonna put 5 here, right? And then I put 0. So I'm gonna press enter. It's gonna be right here. We need to find the interval of convergence, right? Now since this one is an infinite geometric series, right? So in order for this series to be convergent, the absolute value of common ratio must be less than 1, right? So it's going to be absolute value of negative s over 2 must be less than 1, right? So you're going to multiply both sides by 2. It's going to be absolute value of s less than 2, or s less than 2 greater than negative 2. This one is the final answer. Example number 2. Find a power series representation for the following functions and determine its interval of convergence. Alright, so remember we have the formula f of s equals 1 over 1 minus s, right? Now I just rewrite this one. It's going to be 1 over 1 minus parentheses negative s cubed, right? So I can say that this one is an infinite geometric series with common ratio equals negative s cubed, right? And a equals 1. F of s can be written as the first term is 1. The next term is going to be negative s cubed, right? You just multiply by negative s cubed each time, right? The next term should be plus s power of 6, right? The next one should be negative s power of 9, right? Plus s power of 12 minus, right, etc. Plus the general term. It could be negative s cubed raised to the n. Observe that n equals 0, we get the first term. N equals 1, we get the second term. N equals 2, we get this guy. So in general, we have negative 1 to the n times s to the 3n, right? Because I can split this one into negative 1 raised to the n times s raised to the power of 3 raised to the n, like that, right? Now we're going to use the calculator to check out work, right? So you're going to print up the calculator. You're going to press the button right here, hit the tailor, right? Now the first one, you need to hit the fraction right here, and you input 1 over 1 plus s cubed. Alright, you need to define the variable, so you need to put comma right here, put s, right? Now you want the highest degree is 10, so you're going to put 10, right? Put comma and then put 0 and then press enter. It's going to be 1 minus s cubed plus s to the 6 minus s to the 9, right? But we don't have s to the 10, so the highest degree, they're going to pick s, which is close to 10, right? We need to find the interval of convergence, right? So we know that the common ratio is right here, right? So we need this guy right here to be less than 1. When you take absolute value of this one, it's actually positive, right? So it can be absolute value of s cubed less than 1, right? Or absolute value of s must be less than 1, right? Or negative 1 less than s less than 1, right? Now let's move on to question B. I'm going to rewrite this one as 2s squared times 1 over 1 plus s cubed, right? So then I can replace this guy with this guy right here. We did this right here, and we got this right here. So it's gonna be, and then the radius of convergence should be absolute value of s less than 1, right? Now remember that 2s squared outside right here does not affect the interval of convergence. Alright, so the interval of convergence should be the same, right? So now we're gonna print this one inside, so it turns out to be summation ends go from 0 to infinity, right? 2 times this one is gonna be 2 times negative 1 raised to the n. Now s squared and s to the 3n can be combined. It turns out to be s raised to the 3n plus 2. Question C. Remember we have f of s equals 1 over 1 minus s, right? So I'm gonna rewrite this one as s times 1 over 5 minus s, right? Now I need this guy to be 1, right? So I'm gonna divide the top and bottom by 5, right? So I'm gonna have, so this one can be written as s times 1 over 5 times 1 over 1 minus s over 5, right? So I'm gonna compare this guy right here with this guy right here, right? So the common ratio must be this guy right here, s over 5, right? Now I need to rewrite this one as a power series, right? So remember I have the formula for this one should be, so this guy turns out to be s over 5 outside right here. Put this summation notation right here, and go from 0 to infinity of s over 5 raised to the n, right? Now remember this guy right here does not affect the convergence of the power series, right? Now we can print it inside, so it could be summation notation and go from 0 to infinity, right? S and s to the n, it could be s to the n plus 1 over 5 raised to the n plus 1, right? And the interval of convergence is right here, absolute value of s over 5 less than 1, right? So it's gonna be multiply both sides by 5, so absolute value of s less than 5, right? Or you can write negative 5 less than s less than 5, right? Either this one or this one works, right? And the final answer of the power series right here, right? Now let's move on to example number 3. Find a power series representation for the following functions and determine its radius of convergence. Now remember, if you take the derivative of 1 over s, it's going to be negative 1 over s squared, right? So if you take the derivative of 1 over 1 minus s, it's actually 1 over 1 minus s altogether square, right? So the function f of s equals 1 over 1 minus s altogether square can be written as derivative with respect to s of 1 over 1 minus s, right? But this guy actually has the power series d over ds, and then when we take the derivative of this one, it's going to be, we're going to use the power rule, right? So it could be n times s raised to the n minus 1, right? Now remember, this power series has the radius of convergence r equals 1, and then this guy still have the same radius of convergence r equals 1, right? Now let's move on to question B. Now remember, if I take derivative of ln of phi minus s, I'm going to use the formula ln of u prime. It's going to be u prime over u, right? So this guy becomes negative 1 over phi minus s, right? So if I take antiderivative of this one, it's actually ln of phi minus s equals antiderivative of 1 over phi minus s ds. I put negative sign outside, right? The power series of this function, we got it right here. Right? So we have negative antiderivative of, so it should be negative the summation notation ends go from 0 to infinity of s raised to the n plus 1 over phi raised to the n plus 1, right? And then you multiply by n plus 1 on the bottom right here, right? And don't forget to add the constant c when you take antiderivative, right? Now in order to find the constant c, I'm gonna choose s equals 0. I'm substitute over here, right? So I'm gonna let s equal to 0. Then the left hand side becomes ln phi, right? Equals negative the series s equals 0. It's gonna be 0 right here, right? So we have c equals ln phi, right? So finally, your answer should be ln of phi minus s equals ln phi minus the series ends go from 0 to infinity of s raised to the n plus 1 over n plus 1 times phi raised to the n plus 1, right? Now we're gonna go back over here. The power series right here has the radius of convergence right here, r equals phi, right? Right, remember if you draw the number line right here, this is negative phi, this is phi, center s0, right? So this is radius. So the radius of convergence of this one still r equals phi. Now we're gonna move on to the next one, operation with power series. Alright, so if the function ls is represented as a power series a sub n times s to the n, gos equals b sub n times s to the n. Now if you multiply by a constant k, alright, so you replace s right here with ks, so it's going to be like that, right? So we just distribute the power. Now if you replace s with s to the n, and then it's gonna be like this, and then we're gonna multiply the power, right? Now if we add these two series up, we just add a sub n and b sub n, right? And we factor s to the n outside. If we subtract, we do exactly the same thing, right? If you perform operation with power series like this, the interval of convergence for the sum right here will be the intersection of this guy and this guy, right? So for example, if you have the interval of convergence of the first power series is right here, the second one is right here, right? And then when we're gonna add this guy up, we need to take the intersection of this one to get the interval of convergence for the sum, right? So keep that in mind. Example number 4. Find the Maclaurin series for each of the following functions. Alright, be sure to list the first 3 non-zero terms and the general terms. Alright, this guy actually we did in topic 10.14. Now we just review, right? So we have the Maclaurin series for the sine function. It's gonna be, now you just replace s right here with s cubed, right? So we have sine s cubed equal this one s cubed, right? Minus this is s cubed altogether cubed over 3 factorial plus s cubed altogether to the 5th over 5 factorial minus s cubed altogether to the 7th over 7 factorial plus etc, right? And then we just simplify, right? So this guy turns out to be s cubed minus s to the 9. We're going to multiply the power, right? Over 3 factorial, right? Plus s to the 15 over 5 factorial minus s to the 21st over 7 factorial plus etc, right? Now we need to find the general term of this one. Now observe that this one n equals 0, right? N equals 1, n equals 2, n equals 3, right? So n equals 0, we get 3 right here. N equals 1, we get 9 right here, right? N equals 2, we get 15 right here, right? So we're gonna sketch the table. Alright, this is the linear function, right? We're gonna find the slope. So in order to get 9 from 3, we're gonna add 6. This one we're gonna add 1, right? So the slope is 6 over 1 is gonna be 6, and the y-intercept is 3 right here, right? So we have y equals ms plus b, right? Now it's gonna be m equals 6, so 6s plus the y-intercept is 3, right? 6s plus 3. Now in this situation, the variable is not s, the variable is n, right? So I replace this one with n, right? So 6n plus 3, right? So the general term is gonna be, look at this one, we have s, so we need to write s right to the 6n plus 3, right? And we look at the bottom right here, is 1 factorial, right? This is 3 factorial, this is 5, this is 7, right? So we write over here 1, 3, 5, 7. This guy actually the arithmetic sequence, right? Where the common difference is 2, right? A sub 1 is right here, 3, right? So it could be 3 plus n minus 1 times 2, right? So it's gonna be 2n plus 1, right? So finally, sine s cubed can be written as summation notation, and go from 0 to infinity of s right here right to the 6n plus 3 over 2n plus 1. Now we see that the side right here alternating, right? So we put -1 right here right to the something, right? Remember, you have two different cases, right? -1 right to the n or negative 1 raised to the n plus 1, right? Now, we're going to check this one. N equals 0, we get the plus sign. N equals 1, we get the negative sign. We look at this one right here. N equals 0, we're going to pick this one right here. Because this one brings the plus sign, right? So, we have the N right here, right? Now, we're going to use the calculator to check our work, right? So, we're going to print up the calculator. Alright, so I'm going to copy this one over here. Alright, so I'm going to input sine s cubed, right? So I'm going to hit trick right here, sine. This one should be s cubed, right? And modify the variable s, right? I need to see the highest degree 21st, right? So I put 21st right here. And the center 0, right? And then press enter. It's going to be right here. Right? Remember, you have the Maclaurin series for cosine s is 1 minus s squared over 2 factorial plus s to the 4 over 4 factorial minus s to the 6 over 6 factorial, right? So we're going to replace s with square root of s, right? So we have cosine square root of s is going to be 1 minus square root of s squared is going to be s over 2 factorial, right? Square root of s power 4 is going to be plus s squared over 4 factorial, right? Square root of s power 6 is going to be minus s cubed over 6 factorial, right? Now we need to generalize this one, so we have cosine square root of s equals, put the summation notation right here, and go from 0 to infinity, right? Now we put s on the top. Now n equals 0, we get 1, which means s power of 0 equals 1. N equals 1, we get s power of 1. N equals 2, s power of 2. So this is actually n right here, right? We observe that 4 right here equals 2 times 2, right? This is n equal to 2. N equals 1 right here times 1, right? 6 equals 2 times 3, right? So this guy should be 2n factorial, right? And we look at the side right here, it's going to be alternating, right? We have negative 1 right here. Now we're going to pick negative 1 raised to the n or negative 1 raised to the n plus 1. Now look at the first term right here, n equals 0, we get the positive side, right? So this guy must be n, right? Because the first term get the positive side. So this one is the final answer. Now we can use the calculator to check our work, right? So we're gonna print up the calculator. I'm gonna copy this one down, right? So I'm gonna input, this one should be cosine function, right? So I'm gonna hit trick right here, cosine. This guy should be square root of s, right? I wanna see the highest power of 10. So I'm going to put 10 here, the center 0, I'm going to hit enter. It's going to be right here, right? Number 5, binomial series. Find the Maclaurin series, which means the center equals 0, right? For f of s equals 1 plus s to the k, and determine its radius of convergence, right? So remember, you have a Maclaurin series expansion as follows. Now we have f of s equals 1 plus s to the k, right? So then we're going to take the derivative f prime of s equals k times 1 plus s to the k minus 1, right? F double prime of s equals k times k minus 1 times 1 plus s to the k minus 2. F triple prime of s equals k times k minus 1 times k minus 2 times 1 plus s to the k minus 3, right? Etc. Now we're going to generalize this one. So for example, and the derivative of s is going to be, we look at this one right here. We see that this is k minus 2, which is 2 right here is 1 unit less than this one, right? So it's going to be k times k minus 1 times k minus 2 times etc. K minus parenthesis n minus 1, right? And 1 plus s right here. Look at this guy and this guy right here, they're both the same, right? So this one should be k minus n, right? Now we need to calculate f of 0. So substitute 0 for s is going to be 1, right? F prime of 0 is going to be k, right? F double prime of 0 is going to be k times k minus 1. F triple prime of 0 is going to be k times k minus 1 times k minus 2, right? And the last one right here, the n derivative of the function f at s equals 0 is going to be k times k minus 1 times k minus 2 times etc. k minus parenthesis n minus 1, right? Now we're going to substitute the coefficient right here into the formulas right here, right? So we have, now in order to determine the radius of convergence, we need to find the interval of convergence, right? So we're going to use the ratio test, right? So we have limit of absolute value of a sub n plus 1 over a sub n when n approaches infinity, right? So it could be limit when n approaches infinity, absolute value of, now the general term is right here, right? Now a sub n plus 1, so which means I need to change this one to n plus 1, right? So 1 and 1 right here cancel out, right? So it's going to be k minus n, right? So this guy actually k minus n factorial, right? So we have k minus n factorial right here over n right here becomes n plus 1 factorial, right? And you have s right here becomes s to the n plus 1, right? Now I'm going to multiply by this one reciprocal, right? So this guy turns out to be k minus n factorial, actually the next term of this one right here, right? So for example, if you have 1 times 2 times 3 times 4 times 5 right here, right? And this guy actually 1 times 2 times 3 times 4 times 5 times 6, right? So when you cancel out this guy right here, and you have the last term here, 6, right? Which means you have limit when n approaches infinity, absolute value of, now n factorial and n plus 1 factorial, you have n plus 1. Now s to the n plus 1 and s to the n right, you have s left right here, right? Now when n approaches infinity, you can eliminate this one, right? Because it doesn't really matter, right? You can eliminate this one, right? So you have negative n over n, which is negative 1, right? So it could be absolute value of negative s, right? And it could be absolute value of s, right? Now, in order for this series to be convergent, this guy must be less than 1, right? In other words, negative 1 less than s less than 1, right? So we're going to draw the number line right here, right? We have negative 1 right here, 1 right here, and you know that the center is 0, right? So the radius of convergence is 1, right? Now let's move on to example number 6. Find the power series for f of s equals cube root of 1 plus s. So this is actually 1 plus s raised to the 1/3, right? So we're going to use the formula we did in the previous example, which is k equals 1/3, right? So we just substitute 1/3 for k into this series, right? So it's going to be, now we're going to simplify this one. It's going to be 1 plus 1 over 3s plus, now 1 over 3 times 1 over 3 minus 1 is going to be negative 2 over 3, right? So I have 1 times 2 times s squared, right? Now I'm going to replace the positive side right here with the negative side, right? And I have 3 squared right here, right? So I'm going to bring this one to the bottom. 3 squared times 2 factorial, right? Plus, I do exactly the same thing, right? So I'm going to end up with 1 times 2 times 5 times s cubed over 3 cubed times 3 factorial, right? Minus 1 times 2 times 5 times 8 times s power 4 over 3 to the 4 times 4 factorial, right? Plus 1 times 2 times 5 times 8 times 11 s to the 5th over 3 to the 5th times 5 factorial, right? Now this one n equals 0, right? N equals 1, n equals 2, n equals 3, n equals 4, and n equals 5. Now we're going to look at the patterns on the top. So we look at this one right here, we don't see the pattern, right? But the pattern starts right here, and you see the side right here alternating. Negative, positive, negative, positive, right? So basically we're going to start from here, right? So we just rewrite this one right here. So it could be f of s equals 1 plus 1 over 3s, right? Plus, now we're going to put summation notation right here. We're going to start from n equals 2. Now we look at this one right here, n equals 2. Look at the second number right here, we have 2. N equals 3, look at the third number right here, we have 5. N equals 4, look at the fourth number right here, we have 8. N equals 5, look at the fifth number right here, it's going to be 11, right? So we just write over here, 2, 5, 8, 11, right? Now, in order to get 5 from 2, I'm going to add 3, right? So I'm going to keep adding 3 each times, right? So this guy actually common difference, right? And this guy actually arithmetic sequence, right? So arithmetic sequence is given by the formula a sub n equals a sub k plus n minus k times common difference, right? So have a sub n equals, now I'm going to pick this guy right here, right? So it could be 2. And observe that this one, k equals 2, right? Look at this one right here. So we have 2 plus n minus 2 times 3, right? We're going to simplify, so it could be 3n minus it plus 2, it could be minus 4, right? So we're going to put this guy over here, 2 times 5 times 8 times, etc. The general terms right here, 3n minus 4, right? Over. Look at this one right here. N equals 4, this guy, this guy, this guy are the same thing, right? And look at the bottom right here, you always have 3, right? So this guy should be 3 raised to the n times n factorial, right? And this guy must be s to the n. Now I have negative 1 right here because the sign changing, right? So remember you have 2 different cases, either negative 1 raised to the n or negative 1 raised to the n plus 1, right? So we look at the first term right here, it's going to be right here, right? And it's going to be negative, right? When n equals 2, it's going to be negative. So n equals even, it's going to be negative. N equals odd, it's going to be positive. But negative 1 raised to the even number, it should be positive, right? So we must pick this guy, right? So it could be n plus 1 over here, right? And this one is the final answer. the first three non-zero terms right here. Now you can check for the interval of convergence of this series is going to be absolute value of s less than 1, right? Now we can use the calculator to check our work, right? So we're gonna bring up the calculator, hit the button right here. Alright, pick the Taylor. Remember, it's gonna be expression, define the variable, the order, which means the highest degree you want it to show up, and the center, right? So I'm gonna hit Taylor right here. I'm gonna put the expression, it's gonna be 1 plus s raised to the 1/3. And then you're gonna put the comma, define the variable s, and then put the comma. You want the highest degree to show up, right? So I look at this one right here. I want to seize the 3rd degree, right? So I'm gonna put 3 right here, and the center 0, right? Press enter. The answer is right here, right? Now we're gonna move on to example number 7. Find the first 3 non-zero terms in the Maclaurin series for each of the given functions. Alright, so we know that the Maclaurin series for e to the s given by e to the s equals 1 plus s squared over 2 factorial plus s cubed over 3 factorial plus etc. S to the n over n factorial. Look at the pattern right here. We see that we have the general term right here, right? Now, for octangent s, it's going to be s minus s cubed over 3 plus s to the 5th over 5 minus s to the 7 over 7 plus etc. Right? Now we're going to multiply these two guys, right? 1 times this one, right? So I just rewrite this s minus s cubed over 3 plus s to the 5th over 5 minus s to the 7 over 7, right? Plus etc. Now s times this one is going to be plus s squared, right? S times this one is going to be negative s to the 4 over 3, right? Plus s to the 6 over 5 minus s to the 8 over 7, right? Now next one, s squared over 2 factorial times this one is going to be s cubed over 2 factorial, right? S squared times s cubed is going to be minus s to the 5th over 2 factorial times 3, right? Plus s squared times s to the 5th, it could be s to the 7 over 2 factorial times 5 minus s to the 9 over 2 factorial times 7, right? Now s cubed times this one is going to be plus s to the 4 over 3 factorial, right? Minus s to the 6 over 3 factorial times 3 plus s to the 8 over 3 factorial times 5, right? And minus s to the 10 over 3 factorial times 7, right? Now we're going to simplify. Alright, so we have s right here. We just rewrite s. Right? Next one, it could be s squared right here. Plus s squared. Right? Now we're going to move on to s cubed. So we have negative s cubed over 3. And you have s cubed over 2 factorial right here. So it's actually s cubed over 2, right? Minus s cubed over 3, right? So it could be 3s cubed minus 2s cubed over 6, right? So it could be s cubed over 6, right? So it could be plus s cubed over 6, right? Now next one we have s power 4 is right here, and we have this guy right here, right? So we're gonna put this one on the side. S to the 4 over 3 factorial, it could be 6 minus S to the 4 over 3, right? So it could be S to the 4 minus 2S to the 4 over 6, right? So it could be negative S to the 4 over 6, right? Now we can use the calculator to check our work. I'm gonna copy this one down over here. Alright, so we're gonna input the expression e to the s arctangent ask. And the highest degree you want to see is for the center 0. You press enter. It's gonna be right here. Now let's move on to question B. LS equals tangent s, and this is actually sine s divided by cosine s, right? Now the Maclaurin series for the sine function is the cosine function is going to be 1 minus s squared over 2 factorial plus s to the 4 over 4 factorial minus s to the 6 over 6 factorial plus etc. Right? Now since we only need 3 terms, right? Now we just perform long division, right? So sine s divided by cosine s is going to be s minus s cubed over 3 factorial plus s to the 5th over 5 factorial, which means 120, right? And 3 factorial right here actually 6, right? Divide by 1 minus s squared over 2 factorial equals 2 plus s to the 4 over 4 factorial is going to be 24, right? S divided by 1 is going to be s multiplied back is going to be s minus s cubed over 2 plus s to the 5th over 24, right? Now I'm going to do subtraction. This guy gone, right? So I put this guy on the side, negative s cubed over 6 subtract negative s cubed over 2, which means add s cubed over 2, right? I multiply the top bottom by 3. So this guy becomes 6, right? So it could be 3s cubed subtract s cubed, it could be 2s cubed over 6, which is s cubed over 3, right? So this guy s cubed over 3. Similarly, I have s to the 5th over 120 subtract s to the 5th over 24. Multiply the top bottom by 5, right? So this guy becomes 120. So this guy becomes negative 4 s to the 5th over 120. Divide the top bottom by 4. So it could be negative s to the 5th over 30, right? So it could be minus s to the 5th over 30, right? Now s cubed over 3 divided by 1 is going to be plus s cubed over 3, right? Multiply this one back, it's going to be s cubed over 3 right here. S cubed over 3 times negative s squared is going to be minus s to the 5th over 6, right? S cubed over 3 times this one is going to be plus s to the 7 over 72, right? This guy gone. Now negative s to the 5th over 30 subtract, which means add s to the 5th over 6. Multiply the top and bottom by 5. So this guy becomes 30, right? So we have 4s to the 5th over 30. It's going to be 2s to the 5th over 15, right? So this guy becomes 2s to the 5th over 15 subtract s to the 7 over 72, right? Now we need one more terms, right? 2s to the 5th over 15 divided by 1 is going to be plus 2s to the 5th over 15, right? And then we just multiply this one back and we do subtraction, right? So the answer is right here because we only need 3 terms, right? Now we can use the calculator to check our work, right? So we're going to print up the calculator. Alright, I'm going to copy this one down over here. Alright, so I'm gonna input the function tangent s, right? Now I need the highest degree should be 5 and the center 0. Press enter. It's gonna be right here, right? Now let's move on to example number 8. Find the power series by iteration. Alright, using the function g of s equals 1 over 1 plus s, find a power series center s1 for ls equals ln s. Alright, so we have g of s equals 1 over 1 plus s, right? Now we're going to rewrite this one as 1 over 1 minus negative s, right? So we can apply the formula, right? So remember we have the power series 1 over 1 minus s equals the series s raised to the n when n goes from 0 to infinity, right? Now in this situation you need to replace s with negative s, right? So it could be the series negative s raised to the n when n goes from 0 to infinity, right? So it's actually the series, if n equals 0, it's going to be 1, right? And then it's going to be positive, right? So it could be negative 1 raised to the n, s raised to the n, when n goes from 0 to infinity, right? And this guy actually geometric series with a equals 1 and common ratio equals negative s, right? So in order for this series to be convergent, we need the absolute value of negative s less than 1, right? This guy is the same thing as s less than 1 greater than negative 1, right? Now we have ln of 1 plus s equals antiderivative of 1 over 1 plus s ds, right? Now we can replace this guy right here with this guy, right? So it could be antiderivative of the series negative 1 raised to the n, s raised to the n, when n goes from 0 to infinity, right? ds. So it's going to be the series n goes from 0 to infinity of negative 1 raised to the n, this is a constant, right? S raised to the n plus 1 over n plus 1, right? And you know that this series center at s equals 0, right? Now, we need this guy, right? So ln of s can be written as ln of 1 plus s minus 1, right? So then I'm going to replace, look at this one right here, s right here with s minus 1, right? So this guy becomes the series n go from 0 to infinity, negative 1 raised to the n, right? Instead of s, I put s minus 1, right? So I have s minus 1 raised to the n plus 1 over n plus 1, right? And this series center at s equals 1, right? Now let's move on to question B. So we have 1 over 1 plus s squared can be written as 1 over 1 minus negative s squared, right? So it's going to be summation n go from 0 to infinity of negative s squared altogether raised to the n, right? And this one is the infinite geometric series with a equals 1, right? Common ratio equals negative s squared, right? So in order for this one to be convergent, we need absolute value of negative s squared less than 1, or absolute value of s squared less than 1, or -1 less than s less than 1, right? Now we need to find the power series of this guy, right? So remember, we have antiderivative of 1 over 1 plus s squared, actually arctangent s, right? So we have arctangent s equals antiderivative of 1 over 1 plus s squared ds, right? So I'm gonna replace this guy right here with this guy right here, right? So it'll be antiderivative of the series and go from 0 to infinity of -1 raised to the n times s squared raised to the n is going to be s raised to the 2n, right? ds. So I'm going to check antiderivative of this one. So it could be the series n go from 0 to infinity of -1 raised to the n s raised to the 2n plus 1 over 2n plus 1, right? Now let's move on to example number 9, approximation using a power series. Use the series for fs equals arctangent s. This could be right here. Alright, we calculated this one in example number 8b, right? To approximate arctangent 1 over 3 using the error bound less than or equal to 0.001, right? So we have arctangent of s equals, this series has the interval of convergence absolute value of s less than 1, right? Now we substitute 1 over 3 for s, so we have, now if n equals 0, we have 1/3, right? N equals 1, we have -1 over 3 power 3, right? Times 3, right? N equals 2, we have 1 over 3 to the 5th times 5. N equals 3, we have 1 over 3 to the 7 times 7 plus etc, right? Now we're going to simplify this one, so it's going to be 1 over 3 minus 1 over 81 plus 1 over 12 15 minus 1 over 15 309 plus etc, right? So this guy actually an alternating series with positive terms decreasing to 0, and the limit of this one right here equals 0, right? We can use the alternating series remainder theorem. It's gonna be right here. Alright. The error equals the actual subtract the estimate, which means s sub infinity subtract s sub n equals the error bound, and this guy must be less than the first omitted term, right? Right here. Remember, a sub n is this guy right here, right? Now we have a sub n plus 1, so it could be 1 over 3 raised to the 2 parentheses. Instead of n, I'm going to put n plus 1, right? And then you're going to add 1 right here over 2 parentheses n plus 1 plus 1, right? And you want this one to be less than or equal to 0.001, right? It's going to be right here. Now, this guy is the same thing as 1 over 3. Simplify, it's going to be 2n plus 3, right? Times 2n plus 3. This guy must be less than or equal to 0.001, right? Now I'm going to go back over here. A sub n is right here. I need to copy a sub n down over here. Now I'm going to test n equals 0, substitute 0 for n over here. So I have the value 1 over 3 times 1. So it could be 1 over 3, right? Now n equals 1. It could be 1 over 3 power of 3, right? Times 3. So it's going to be 1 over 81. N equals 2. It's going to be 1 over 3 to the 5th times 5, right? So it's going to be 1 over 12, 15, right? Now if you use the calculator to convert this one to decimal, it's going to be approximately 0.333. It's still greater than 0.001, right? Now this guy is the same thing as 0.0123, still greater than 0.001, right? Now this guy is the same thing as 0.0000823. This guy actually less than 0.001, right? So we stop right here, right? Now we're going to apply the alternating series error bound right here, right? So it's going to be this guy right here, right? S sub infinitive actually arctangent of 1 over 3 minus S sub n, which means the partial sum of the series, right? So I'm going to go back over here. I have absolute value of S sub infinitive subtract S sub n. It's going to be absolute value of arctangent of 1 over 3, right? Subtract the partial sum, which means the first two terms right here, right? Because we stop right here already, right? So the first two terms, which means 1 over 3 minus 1 over 81, right? Look at the first two terms, it's going to be right here, right? So this guy equals 26 over 81, right? So I put 26 over 81 over here. This guy must be less than or equal to the first omitted term, right? Which is the next term right here, right? 1 over 12, 15. And this guy less than 1 over 1000, right? And this guy actually 0.001, right? So the final answer is arctangent 1 over 3, the partial sum of the series, right? Which is 1 over 3 minus 1 over 81, and it's going to be 26 over 81, right? And this one is the final answer. Now let's move on to example number 10. Power series approximation of a definite interval. Use a power series to approximate the interval from 0 to 1 of e to the negative x squared dx with an error of less than 0.01. Alright, so we know that the Maclaurin series of the function e to the x equals. Now we're going to replace x right here with negative x squared, right? So we have e to the negative x squared equals. So this guy is the same thing as negative 1 raised to the n times s raised to the 2n over n factorial when n go from 0 to infinity, right? Now we're gonna integrate both sides, right? So if we take n times the derivative of this one, it's gonna be n times the derivative of this one, right? So this guy turns out to be, now this guy turns out to be s raised to the 2n plus 1 over 2n plus 1, right? You just use the power rule, right? Now, if you put the lower bound 0, upper bound 1 over here, 0, 1 over here, then you need to evaluate this one from 0 to 1, right? This guy turns out to be, now substitute 1 for s, it's going to be 1 over this one, right? Substitute 0 for s, it's going to be 0, right? So this one is the final answer for this, right? Now I'm going to expand this one. If n equals 0, I'm going to get 1. N equals 1, I'm going to get negative 1 over 3, right? N equals 2, I'm going to get 1 over 10. And n equals 3, I'm going to get negative 1 over 42, right? Now, you can convert this one to decimal, right? So it could be 0.0333. This guy 0.1, right? This guy 0.0238, right? Now this guy is still greater than 0.01, right? Now I keep finding the next term, right? So the next term right here should be 1 over 216 for n equals 4, right? Substitute 4 over here, it's going to be 1 over 216, right? And this guy actually 0.00463 if you use the calculator, right? This guy less than 0.01, right? So you can stop right here, right? Now since this guy right here is an alternating series with positive terms decreasing to 0, right? And the limit of this guy right here equal to 0, right? So you can apply the alternating series error bound, right? Which is the absolute value of the actual values subtract the estimate value, right? S sub infinitive subtract S sub n, right? Equals absolute value of R sub n less than or equal to the next omitted term, right? A sub n plus 1. Alright, this guy right here actually the integral from 0 to 1 of e to the negative s squared ds, right? Subtract the partial sum of the series, right? Remember we stop at n equals 4, right? So the partial sum should be this guy right here. Now if you calculate this guy on the side, it's actually 26 over 35. You put it over here, 26 over 35, right? This guy less than or equal to the first omitted term, which is right here, right? And this guy less than 1 over 100, and it's actually 0.01, right? So your final answer must be the integral from 0 to 1 of e to the negative s squared ds equals 26 over 35, right? Now let's move on to question B. Use a power series to approximate the integral from 0 to 1 of s cosine s cubed ds within 3 decimal places, right? So this one means the error must be less than 0.0005, right? Now we do exactly the same thing as the question A, right? So we're gonna start from the Maclaurin series for the function cosine s, right? So it's gonna be summation and go from 0 to infinity of negative 1 raised to the n, right? S raised to the 2n over 2n factorial, right? Now we're gonna replace s right here with s cubed right here, right? So we have cosine of s cubed equals, so we're gonna simplify this one, negative 1 raised to the n s raised to the 6n over 2n factorial, right? Now next we're going to multiply both sides by s, right? So if I put s right here, then this guy turns out to be 6n plus 1, right? If I take n times derivative both sides, so I have, now we need to take the interval from 0 to 1, right? So it's gonna be, now I'm gonna take n times derivative of this one using the power rule, right? So it turns out to be s raised to the 6n plus 2 over 6n plus 2 evaluated from 0 to 1, right? So I'm gonna substitute 1 for s, so it's gonna be times 1 over 6n plus 2, right? And substitute 0 for s could be 0, right? So the interval from 0 to 1 of s cosine s cubed ds equals, if n equals 0, substitute 0 for n over here, we get 1 over 2 times 0 factorial. N equals 1, we get negative 1 over 8 times 2 factorial. N equals 2, we get 1 over 14 times 4 factorial. N equals 3, we get negative 1 over 20 times 6 factorial, right? Now I'm going to convert this one to decimal. This guy actually 0.5, right? Minus 0.0625 plus 0.00297 minus 0.0000069, right? Now plus etc., right? Now we look back over here, we see that this guy must be less than 0.0005, right? So this guy right here less than 0.0005, right? So we're gonna stop at n equals 3, right? So the partial sum should be this guy right here, right? Since this series right here is an alternating series with positive terms decreasing to 0. And the limit of a sub n, which is this guy right here, equals 0. So we can apply the alternating series error bound. So the absolute value of s sub infinity subtract s sub n equals the error bound less than or equal to the first omitted term, which is a sub n plus 1, right? Now this guy right here actually the actual value, right? So actual value is this guy right here, right? So it can be absolute value of the interval from 0 to 1 of s cosine s cubed ds, right? Subtract this guy actually the partial sum of the series, right? The one inside right here, right? Now I'm going to simplify this one. So 1 over 2 times 0 factorial is actually 1 over 2 minus 1 over 16 plus 1 over 336, and subtract this guy right here actually 1 over 14,400, right? And etc., right? So if we sum this one up, it turns out to be 37 over 84, right? So we put 37 over 84 inside, right? And then this guy must be less than the first omitted term, which is this guy right here, right? And this guy actually less than 1 over 10,000, right? And this guy equals 0.0001, right? But this guy less than 0, 0, 0, 5, right? So by transitive property, we have this guy less than this guy, right? So your final answer must be the integral from 0 to 1 of s cosine s cubed dx equals this guy right here, right? 37 over 84. Now let's move on to example number 11. Given a function defined by fs equals cosine 2s minus 1 over s squared for s not equal to 0 is continuous for all real numbers s. What is the limit of the function fs as s approaches 0? Right? So when s approaches 0, the top approaches 1 minus 1. The bottom approaches 0, so it could be 0 over 0, right? So this one is the indeterminate form, right? So we can use L'Hospital rule, right? Now we're going to take the derivative on the numerator. So we're going to use the derivative of the cosine u. It's going to be negative u prime times sine u, right? So it's going to be negative 2 times sine 2s, right? Derivative of 1 equals 0, right? The bottom is derivative of this one is going to be 2s, right? When s approaches 0, right? When s approaches 0, you still have the indeterminate form, right? So we're going to apply the L'Hospital rule one more time, right? Limit when s approaches 0, take derivative on the numerator, right? So it could be negative 4 cosine 2s. Derivative on the denominator equals 2, right? So when s approaches 0, cosine approaches 1, right? So it could be negative 2. Now question B. Write the first 4 non-zero terms and the general terms of the power series that represents the function cosine 2s, right? So remember we have cosine s equals 1 minus s squared over 2 plus s to the 4 over 4 factorial minus s to the 6 over 6 factorial, right? The first 4 non-zero terms, right? So we're gonna add etc. Add now the general term negative 1 raised to the n s raised to the 2n over 2n factorial, right? Now you just replace s with 2s, right? So we have cosine of 2s equals 1 minus 2s squared is going to be 4s squared over 2, right? 2s raised to the 4 is going to be 16s to the 4 over 4 factorial. 2s raised to the 6 is going to be 64 s raised to the 6 over 6 factorial plus etc. plus negative 1 raised to the n 2s raised to the 2n, right? So I have 2s raised to the 2n. It's going to be 2 raised to the 2n times s raised to the 2n, right? So it could be 4 raised to the n times s raised to the 2n, right? So it could be 4 raised to the n times s raised to the 2n over 2n factorial, right? Now question C. Use the result from part B to write the first 3 non-zero terms for this one, right? So we have this one, we just subtract both sides by 1 and divide both sides by s squared. That's it, right? So I'm going to leave this one for you to verify, right? The answer must be negative 2 plus 2 over 3 s squared minus 4 over 45 s to the 4, right? Now question D. Use the result from part C to determine if the function fs has a relative maximum, relative minimum, or neither. Now, again, when it comes to maxima or minima, or increasing or decreasing of the function, think about the first derivative, right? So I'm going to take the first derivative of this one, right? So I'm going to use this one right here, right? Derivative of negative 2 is going to be 0, right? So this guy turns out to be 4 over 3s, right? Minus 16 over 45s cubed, right? So I need to let f prime equals 0 is the same thing as, I'm going to factor s out, right? So I have s times 4 over 3 minus 16 over 45 s squared equals 0, right? So then s equals 0, and then 4 over 3 minus 16 over 45 s squared equals 0, right? Now we don't really worry about this guy much because it say s equals 0, right? So s equals 0 is right here, right? So s equals 0 is the real number, right? Now we're going to use the second derivative to determine if this one is the relative maximum or minimum, right? So we're going to find f double prime is going to be 4 over 3 minus 48 over 45 s squared, right? So then we substitute 0 for s, right? So f double prime of 0 equals 4 over 3, which is greater than 0. The function f is concave up. Then you can conclude that s equals 0 is a relative minimum, right? Since f prime of 0 equals 0 and f double prime of 0 positive, right? And it's your time to stop. Thank you for watching. I hope you enjoyed the video. Remember that if you failing to prepare, you're preparing to fail.
We rise like tall buildings as the chemicals they take us higher. The night's young, it has just begun as she puts her hand in mine.